Sevgili katılımcılar, kıymetli hocalarımız ve canım meslektaşlarım, hepinize 5. Uluslararası Agenastro Konferansı'na hoş geldiniz diyorum. Bugün burada sadece bir bilgi paylaşımı yapmayıp aynı zamanda ortak bir meslek bilinci, ortak bir dil ve geleceğe dair ortak bir vizyonun içerisine adım atıyor olacağız. Bilim büyüyor, teknoloji ilerliyor, yöntemler gelişiyor, elimizdeki veriler çoğalıyor. Ama maalesef ki halen daha 2025 yılında olmamıza rağmen mesleğimizi savunan ve tanımlayan bir kanun bulunmamaktadır. Bizler sadece laboratuvarda değil, üniversitelerde, tanı merkezlerinde, sahada ve toplumun içerisinde çalışan bilim insanlarıyız. Ama bu, yani şöyle söyleyeyim, emek var, çaba var, yetkinliğimiz var ama maalesef ki bunu yönetecek bir meslek kanunumuz yok. 6. yılımızda umuyoruz ki meslekli haklarımızın tanımladığı, bizi koruyan yasal bir çerçevede kavuşmuş olmayı diliyorum ve bu şekilde tekrardan kavuşmayı diliyorum. MBG Türkiye ailesi olarak hep birlikte daha görünür, daha güçlü ve daha dayanışma içerisinde bir geleceği inşa etmeye devam ediyor olacağız. Ben lafı daha fazla uzatmadan çok sevgili Leyla arkadaşımıza sözü bırakmak istiyorum. Hepiniz tekrardan hoş geldiniz.
Herkese merhabalar. Ben MBG Türkiye Yönetim Kurulu Başkan Yardımcısı Leyla Büyükderili. Hepinizi saygı ve sevgiyle selamlıyorum. Bugün Agenastro ekibimizin düzenlediği 5. Uluslararası Astrobiyoloji Konferansı vesilesiyle sizlerle bir arada olmaktan büyük bir heyecan ve mutluluk duyuyorum. Sevgili Başkanımız Hannah Atrakçı'nın ardından sizlerle birkaç düşüncemi de paylaşmak isterim. Her şeyden önce Agenastro ekibindeki tüm arkadaşlarıma gönülden teşekkür etmek istiyorum. Çünkü onlar yalnızca bir konferans organize etmiyorlar. Aynı zamanda astrobiyolojiyi öne çıkararak bu çok disiplinli ve büyüleyici alanı biz genç araştırmacılar için daha görünür ve ulaşılır kılıyorlar. Ve bunu 5 yıldır büyük bir emek ve tutkuyla gerçekleştiriyorlar. Dünyanın dört bir yanından bilim insanlarını bizlerle bir araya getiren bu organizasyon aslında yalnızca bilimsel değil, aynı zamanda kültürel ve insani bir köprü de ortaya koyuyor. Aynı zamanda MBG Türkiye ekibi olarak bizler bilimi merkezine alan bu dayanışma ruhunun bir partisi olmaktan büyük gurur duyuyoruz. Bugün burada evrenin en temel sorunlarına merakla yaklaşan, farklı alanlardan gelen pek çok değerli katılımcıyla bir aradayız. Bu ilham verici buluşmanın yeni fikirlerin filizlenmesine vesile olmasını diliyorum. Hepinize verimli, keyifli ve bol keşifli bir konferans diliyorum. And for our international guests, we are truly happy to have you with us today. Thank you for being part of this global celebration of science and astrobiology. Also, a huge thank to my amazing team and fellow organizers who made all of this possible with their passion, dedication, and love for astrobiology. Our Agenastro team, we hope you enjoy the conference as much as we do. Thank you.
Hello, everyone. Good afternoon, and welcome to the 5th International Online Astrobiology Conference, organized by MBG Türkiye Agenastro team. My name is Zeynep. As you know from previous years, I'm Agenastro team leader, and I'm honored to open today's event and welcome you all, researchers, students, and astrobiology lovers from around the world, to this exciting day full of science, discovery, and imagination. As you know, astrobiology is a field that sits right at the intersection of many disciplines like biology, chemistry, geology, and planetary science, and more. But more than that, it represents humanity's shared curiosity. Are we alone? How did life begin? And where else might it exist? These are profound questions, and each of our speakers today brings a unique perspective to the conversation. Let me give you a quick overview of our program. We begin with Dr. John Blank from NASA, who will present the NASA Brave project, preparing for a mission to a Martian lava tube. This talk will take us into the heart of Mars and exploring how we might search for life, its surface in ancient lava tubes. After a short break, we will continue with Dr. Ahmet Talât Saygaç, who will take us on a journey through our own solar system, with the topic title Life in the Universe, Life in the Solar System. From isomoons to the Martian Soyuz, the possibilities are truly fascinating. Then we will have Dr. Tomasz Zajkowski, who will introduce us the intersection of biology and space research in his talk, Astrobiology at NASA and in Poland. Why do we study animals in space? This promises to be a very intriguing topic linking molecular biology with the space exploration. Later in the evening, Mike Toillon from NASA will share something a little different, a visual and creative approach to the science. His talk, The Search for Life Begins at Home, Astrobiyology Filmmaking at NASA, will explore how storytelling and filmmaking can help bring science to the life and inspire the next generations. Finally, today, we will close our scientific journey with Professor Ulrich Muller, who will present early stages an RNA world with catalyst and a mature RNA world with sophisticated ribosomes. This talk will deep into the origin of the life itself, how simple molecules might have evolved into complex biological systems. We are truly honored to have such an amazing lineup of speakers from both national and international institutions. On behalf of the entire MBG Turkey Agenastro team, I would like to thank them for joining us and sharing their work with our community. I also want to thank all of you who are attending. Your curiosity, questions, and patience are what make events like this meaningful. Let's enjoy a day of learning, connection, and exploration today together. And so let's dive in, let's ask big questions, let's imagine new words. Now, without further ado, let's begin. Thank you, and once again, welcome to the 5th International Astrobiyoloji Conference.
Sevgili bilimseverler, MBG Türkiye Agenastro ekibi tarafından düzenlenen 5. Uluslararası Astrobiyoloji Konferansı'na tekrardan hoş geldiniz. Benim adım Berra. Bugünün etkinliğini açmaktan ve hepinizi dünyanın dört bir yanından araştırmacılar, öğrenciler ve astrobiyoloji meraklıları, bilim, keşif ve hayal gücüyle dolu bu heyecan verici güne davet etmekten onur duyuyorum. Astrobiyoloji, biyoloji, kimya, jeoloji, gezegen bilimi ve daha fazlası gibi birçok disiplinin kesiştiği noktada bulunan bir alandır. Ancak bundan da öte insanlığın ortak merakını nasıl temsil eder? Yalnız mıyız? Yaşam nasıl başladı ve başka nerede olabilir? Bunlar derin sorular ve bugün konuşmacılarımızın her biri sohbete benzersiz bir bakış açısıyla geliyor. İsterseniz programımızın kısa bir özetini sizlerle paylaşayım. İlk oturumumuzu NASA'dan Dr. Jean Blanc ile başlıyoruz. Kendisi NASA Bradley projesi Mars Love tüpüne bir göreve hazırlık sunumunu bizlerle birlikte yapacak. Bu konuşma bizi Mars'ın kalbine götürecek ve antik lav tüplerinde yüzeyin altında nasıl yaşamı arayabileceğimizi inceleyecek. Kısa bir aradan sonra bizi evrende yaşam, güneş sistemimizde yaşam ile kendi güneş sistemimizde bir yolculuğa çıkaracak olan Doktor Ahmet Talât Saygaç'ın ile beraber olacağız. Buzlu uydularından Mars toprağına kadar olasılıklar gerçekten çok büyüleyici. Ardından NASA ve Polonya'da astrobiyoloji, uzayda ameliyotları ve neden inceliyoruz başlıklı konuşmasında bizi biyoloji ve uzay araştırmalarında en son kesişim noktasına tanıtacak olan Doktor Tomasz var. Bu moleküler biyolojiyi uzay keşfiyle ilişkilendirilen çok ilgi çekici bir konu olmaya söz veriyor. Akşamın ilerleyen saatlerinde NASA'dan Mike Toillon biraz farklı bir şey paylaşacak bizlerle. Bilime görsel ve yaratıcı bir yaklaşım. Konuşması yaşam arayışı ve evde başlıyor. NASA'da astrobiyoloji film yapımı, hikaye anlatımı ve film yapımının bilimi hayata geçirmeye ve gelecek nesillere ilham vermeye nasıl yardımcı olabileceğini inceleyecek. Son olarak bilimsel yolculuğumuzu katalizörlü bir RNA dünyasının erken aşamaları ve sofistike riboizmlere sahip bir olgun bir RNA dünyası sunumunu yapacak olan Profesör Doktor Ulrich Muller ile sonlandıracağız. Bu konuşma yaşamın kökenine ve basit moleküllerin karmaşık biyolojik sistemlere nasıl evrilmiş olabileceğine derinlemesine inecek. Hem ulusal hem de uluslararası kurumlardan böylesine harika bir konuşma kadrosuna sahip olmaktan gerçekten onur duyuyoruz. MBG Türkiye Agenastro ekibinin tamamı adına bize katıldıkları ve çalışmalarını topluluğumuzla paylaştıkları için onlara gerçekten içten bir şekilde teşekkür etmek istiyorum. Ayrıca katılan hepinize teşekkür etmek istiyorum. Merakınız, sorularınız ve tutkunuz bu tür etkinlikleri anlamlı kılan şeydir. Birlikte öğrenme, keşif dolu bir günün tadını çıkaralım. Büyük sorular soralım, yeni dünyalar hayal edelim. Şimdi daha fazla uzatmadan başlayalım. Ve bir kez daha 5. Uluslararası Astrobiyoloji Konferansı'na hepiniz hoş geldiniz arkadaşlar. Bir de son olarak şunu eklemek istiyorum ben ekstra olarak. Katılım belgeleriyle ilgili eğer şimdiden soru soracak olursanız ben buradan tekrardan size bilgi geçmek istiyorum. Katılım belgesi için yoklama formu her oturum sonunda hocalarımızın sunumu bittikten sonra YouTube chatte ve duyuru grubumuzda paylaşılacak. Ama şöyle bir ekstramız var ki biz sunum sırasında yoklama formunda sizden isteyeceğimiz bir anahtar kelime var. Bu anahtar kelime de her sunumda aşağıdan banner olarak, altyazı olarak geçecek ve bu anahtar kelimeyi yoklama formuna yazmanızı isteyeceğiz. Eğer bu anahtar kelimeyi yazamazsınız maalesef o yoklama formu geçersiz sayılacak ve katılım belgesi alabilmek için en az 3 sunuma katılmış olmanız gerekmektedir. Teşekkürler.
Teşekkür ederiz sana katılımın için. Leyla, sana da çok teşekkür ederiz güzel sözlerin için. Our first session will be moderated by Beranur Terkir. So stage is yours, Beranur. I'm taking you here. Okay, stage is yours.
Thank you, Zeynep. Hello, everyone. As part of the MBG Türkiye Agenastro team, I'm honored and excited to present to you the first part of the 5 International Astrobiology Conference. I'm Beranur Terkir. I'm continuing my education in the Department of Molecular Biology and Genetics at Uluslararası Kocaman University. I would like to welcome all viewers and speakers again, and I wish everyone a wonderful day. Today, I will be accompanying Dr. Jen Blank. I would like to express my special thanks to her. Right now, it's 5 a.m. on Easter morning in California. She didn't let us down and agreed to be speaker. Jen is a senior researcher working at the Blue Marble Space Institute of Science at NASA Ames Research Center. She leads a project called BRIL, supported by NASA. This project is a study that investigates life in volcanic caves and includes robotic missions simulations. Currently, she works on the chemistry of water and rocks that support microbial life and examines the mineral and chemical traces left behind by these organisms. Now, I invite her to the broadcast. Hello, Dr. Jen. Good morning. How are you doing?
Good afternoon, everybody.
Thank you. How are you doing, Dr. Jen?
Good. I'm just still getting set up for my presentation. Will someone guide me, please?
Okay. Zeynep can help you.
Yeah, okay, I can guide you. Can you see at the background under our pictures, you have present or invite button. You can click there.
Okay. And do I say slides? I have a PowerPoint presentation.
Okay, so from your computer, you can upload here or you can share your screen. It's 2 options.
Okay, I'll share my screen.
Okay, when you click the share screen, you have 3 options. So you can click window and select your PowerPoint presentation, or you can click entire screen. But please also click to share audio if you have audio.
Okay.
That's important.
I do have audio, and I see screen sharing with 2 monitors. No, screen sharing works best on a good computer. So share screen.
Yeah, share screen. And
okay. I don't see share window.
Window or entire screen, it's your choice. Yeah. Okay. At the window, you can, we can see now. I will take here. Okay. So, we can see it.
Okay. If you don't have information to add, you can start your presentation, Dr. Jen. Floor is yours.
Okay. Excuse me, everybody, while my voice warms up since it's morning time. I'm very happy to participate in the 4th annual MGB Turkey International Online Astrobiology Conference. And because in part, I'm so excited to support astrobiology around the world. And also one of my colleagues for many years has been a Turkish sociologist who's now based in Turkey. Today, I'm going to talk to you about the NASA BRIL project. This is a project I've been leading for some years now. And it was funded by NASA to help us prepare for a possible, there's nothing in the books yet, but a possible future mission to a Martian lava tube. So this is a planetary analog study.
I'm
What is
sorry,
it
but did you make it enter full screen? And if you are going, we cannot see it. Now it's at the first slide.
You cannot see the slide?
We can see the slide, but if it is moving further, we cannot see it waiting at the first slide. Is it true?
How do I move forward?
I don't know.
I'm clicking. Just a minute. Let's try. Here's the first slide. Here's the second slide. Do you see that
No,
one?
we just see first one.
Do you see that one?
We just see the first slide, not like.
Okay. Let's see. Just a minute.
Maybe because of full screen. If you are going at the full screen, maybe that's why we cannot see, because the window is PowerPoint inside.
Can you see now?
Yeah, we can. Yeah, now it's moving. Yeah.
Okay. Do you see the whole screen of slides on the left?
Yeah, we can.
So I need to have a different view. Excuse me, everybody. I think I have to say view. Let's see. Just a minute. Do you see that one?
Yeah.
Okay, let's see. There's some special setup in the software, and I'm not familiar with it. Layout. No, I don't need that one. I need to view. Presenter view.
Yeah, now it's okay. Yeah. It's moving, and we can see whole screen. Yeah. Thank you so much. I'm so sorry.
I don't see you, unfortunately.
Oh, that's bad. Oh, okay. So stage is yours. I'm so sorry to interrupt you.
No, I'm sorry that it, let's see. Still, so now do you see just the slides? Now do you see the slides?
Yeah, we can.
And now I can see you too. So will that work?
Yeah, but we can see whole slides, not page by page.
Okay, just a second.
Whole the page.
Yep.
Yeah.
Slide presenter view.
Yeah, that's working, but I'm so sorry you cannot see.
I can't see you. Okay, I'm going to go ahead this way. So again, my title is the NASA Braille Project, Preparing for a Mission to a Martian Lava Tube. NASA science supports work or studies of analog missions. These are to help us prepare for a possible future mission and practice on Earth, so for what one day may become a mission to another planet. So what is a planetary analog? There is no perfect analog on Earth for what we might expect to find one day on another planet. But these are places on Earth that allow us in part to approximate operational or physical conditions on other planetary bodies. So in other words, environments where we could practice working with robots or working in astronaut suits, or environments that have conditions that are extreme enough to be similar to what we might find, say, on the Moon or Mars or somewhere further away from Earth. Now, for my work, I worked on the Curiosity rover team for many years, more than 10 years, and it's so exciting to me that Curiosity just reported new studies locating or identifying carbonates on the red planet. This is very exciting. But my background is in geochemistry, and I focus on rocky bodies, so Earth, the Moon, and Mars. And so my analogs that I focus on Earth have to do with good settings to practice for operations and exploration on the Moon and Mars. I'm also very interested in astrobiology, and I work frequently with scientists from other disciplines, especially microbiology and robotics, to practice these in field settings on Earth and think about where we might and how we might search for life on other planets. So going back to my title, Braille. Braille is a NASA acronym. NASA likes acronyms. This stands for Biologic and Resource Assessment in Low Light Environments. And one of my team members, who is a NASA civil servant, came up with it. So here's a picture of the a Mars map, essentially, showing the difference in elevation colored with blue where it's low elevation and red where it's higher elevation. And you might notice that there's a lot of blue on the northern hemisphere and a lot of brighter colors on the southern hemisphere. This is because Mars has a sort of topographical dichotomy. The northern hemisphere is substantially lower relative to an average than the southern hemisphere. And these three dots, I don't know if you can see my cursor here, the three dots plus this bigger one represent, or they indicate volcanic areas in Mars. In fact, this independent or standalone volcano is the largest known volcano in our solar system. So I don't know whether or not you all think about this, but Mars has a lot of basaltic lava flows. And it's this kind of flow that creates lava tubes or volcanic caves. And that's what we study with Braille. Here's the same map showing red dots that indicate landing sites on Mars, where we've sent landers and rovers to Mars. Here's Curiosity, which is the lower right in Gale Crater, the right-hand side. And superimposed on this map also are little white dots, and those indicate potential openings into the subsurface. So in other words, skylights and breakdown openings into volcanic caves. And it's so exciting because there's so many of them. And these were actually found some years ago by someone looking at Mars imagery and selecting candidate cave sites. And so some of my colleagues and I have been looking at these in great detail with the HiRISE camera, and that's currently the highest resolution camera anywhere in our solar system. It allows you at 350 kilometers from the surface, allows you to resolve images down to about 30 centimeters. That's better than we can even do on the moon. So we've been looking at these candidate cave sites and trying to see whether or not, with our best ability, these could be actual openings. Now in this diagram, there are over 1,000 white dots, and we've narrowed it down to only about 16 actually, where we think we have a very good chance of seeing openings into the subsurface. So why is this interesting? Well, we haven't, at all these different missions, we haven't found evidence of life on Mars yet. And most people in our community believe that if we will find evidence of life on Mars one day, whether it's past life or present life, it will be in the subsurface or under crusts of rocks. And how do we get to the subsurface? Well, we can drill, and so far we've drilled about 5 centimeters, or we could look for, try to drill deeper, but we think we see evidence of water aquifers or aqueous materials quite deep in the Martian surface, maybe 100 kilometers down. So that will be hard technologically. But another way to get to the subsurface is through these entrances into volcanic caves. And so the Braille Project is focusing on studying these both with science and indirectly using robots and cameras to look for signs of life. So do we have lava caves on Earth? Of course we do. But from above, this is what they look like. In the top diagram, you see example from New Mexico, USA. You have we call them pit crater chains. So places where the lava tube has collapsed at the surface, revealing potential void space below. And in the lower figure, you see a partially collapsed pit crater from Arsia Mons, one of those 3 volcano regions in the high elevation on Mars. And just for comparison, we see the skylight in both of them. Here's that same Arsia Mons again on Mars on the left-hand side. And on the right, we see a very long chain of tortuous or sinusoidal pit craters. And these happen to be located in Northern California, where our field site is. You can find these all over the world, wherever you have lava flows. And once again, I'm narrowing in on our field site in Northern California. This is a place where we have a shield volcano, so sort of like Hawaii basalt, Hawaii lava. And instead of erupting the big ash cloud, the lava erupts and flows with gravity down. And as it flows, the hot lava continues to flow down, leaving behind a hollow shell, and that forms the lava tube, or eventually what becomes a volcanic cave. And I see, or I put also on this diagram, a star showing where I'm located in California, and then it's about a 7-hour drive up to the Lava Beds Field Site, which is a national monument in Northern California. So if you're just walking around and you don't know what you're looking at, you might not see all the caves, but in fact, there are over 900 known caves at this monument site. And we've mapped more than, the cavers have mapped more than 50 kilometers in the subsurface. So on the surface, it looks like high desert, rough terrain. And in the winters, there's snow and ice. In the summer, it's very hot. But the temperatures in the caves are relatively moderate, averaging about 6 to 16 degrees. It does get colder as you go deeper in the caves. We do find ice in some of the caves, and it does get warmer as you come to the cave opening. But basically, it's a much more temperate environment. So this is really cool, I think, thinking about future exploration in our solar system, because although Braille is focusing on a Mars analog site because we're interested in life, the moon also has a lot of lava flows and even more indication of subsurface void space. And just imagine if we're on the moon and we're setting up a habitat, where would you want to go? I may not think about where I'd want to go to look for life, but I'd certainly want to go to a cave to live or to have a habitat, because the caves on the moon and on Mars are much, much bigger than on Earth because of the lower gravity of these rocky bodies. And also, if you're in the cave, you have a sort of average temperature of the surface, and which on the case of the moon would be, minus 200 in the day and 125 in the day and minus 200 at night. So very, very cold. And you might be able to wear a sweater if you're in a habitat in the moon and be protected from that big temperature swing. You're also protected from radiation, and I can envision a scenario in which you have an enclosed environment that can be a large volume where you could walk around in your t-shirts. Anyway, so that's just an aside. So I do have a question for the audience, and that is, who's studying volcanic caves in Turkey? I've done a little bit of searching and seen some imagery, and most of the references I find refer to these 4 locations. And I put all 4 of them on, even though number 1, the Kapanış volcanic field, is the most likely because it's a big basaltic region. The Cappadocia region, which is more famous, and maybe some of you have visited, is our ignimbrites, or essentially a fall tough material. And these are erosional caves, so you probably don't find these on Mars, or ancient ones on Mars. And Mount Nemrut and Mount Ararat area, excuse my pronunciation, are areas that don't have quite the same geology to favor the formation of lava tubes. But I'd be really interested in knowing who's working in Kapanış volcanic field and whether or not they're looking for what we call secondary features, or features that form in the caves after the caves have cooled. So if you know, please text me or tell me. Here's an overview of Braille. It's a cartoon here, and Braille has 3 parts. It has a study of astrobiology science, in which we are crawling in the ground in the caves and collecting samples to take away to the lab and analyze later. It's also a platform or opportunity to test technology. So we've tested a series of instruments that have been actually developed for missions in flight off Earth, and evaluate how they perform in this all-dark environment. And then it's also an opportunity to practice science operations. In other words, how well do human operators communicate with robots or remote missions, or how well are they able to identify features in the caves that they're not able to see in person? So in this case, the most recently in Braille, we've compared how well a robot can operate in the cave versus how well a robot and a robot-human teaming can perform relative to one another. And I'm going to sort of show you different parts of this Braille project today. So the astrobiology study first, and we set out to answer these questions. what are characteristic morphologies of secondary features in the caves? Once again, the secondary features are those that form after the lava tube has formed. So they could be anything coating the wall or coming into the cave from fractures. Usually when a cave forms, it's very hot, molten, it supports molten lava. And then when it cools, usually in the first few years, the lava condenses and the tube fractures because it's shrinking a little bit. Just imagine putting hot glass in air or water. There's a good chance it will fracture. Anyway, and then we want to know who's there and what are they eating. By who's there, I mean not the bats, not the other mammals that inhabit the caves, but mostly the microbial features or microbial communities that are inhabiting the caves. Because we think when we find life out somewhere else, we think it will be in the form of microbes. And then finally, what dissolved nutrients in the water that's coming into the caves largely through the fractures can support microbial life there. So this is a lot of words, excuse me, but these are some of the tools we use to try to address the astrobiology aspect of Braille. What is that? We use photography, scanning electron microscopy, and microbe and X-ray diffraction to look at the geochemistry. We use 16 and 18S ribosomal RNA gene sequencing to try to identify the communities. And then we did a brief or a small sample of metagenomic analyses. There's a lot of room for further study. We also looked at lipid compositions with intact polar lipids and carbon isotopes to try to understand what sort of metabolic activity was present. And finally, we looked at dissolved organic material and light and trace element chemistry in the fluids that are in the caves, whether it's drips on the surface of the caves or puddles on the floor. So, as I mentioned, the astrobiologists, we call ourselves the foot scientists because we can go, right today, we're more agile than the robots. So we can go in a lot of caves. And of these 900 caves, we work with the National Cave Foundation in the US to help, they helped us select caves that would give the highest variation in these physical parameters: the age, the length of the cave, the depth from the surface of the cave, how many access points or skylights there are to get in the caves, what are the basic temperatures, the relative humidity and the wetness inside the caves, and finally, was there a lot of human visitation, or were these backcountry caves that only people in the Cave Research Foundation would know about, or explorers stumbling onto them? So I'm just going to walk through a few pictures, and there's so many more. It's just so fascinating to see the features in these caves. Here we see a yellow or golden biofilm, and it's so bright. Some people think it looks as though someone threw paint on the walls of these caves. It's just spectacular. Anyway, here's a finger pointing to the golden biofilm. And here's another picture showing a different sort of a silver or white biofilm. And a lot of the biomass in the films are concentrated on the cave walls and ceilings. And this is where water is entering the caves. And you see these interesting textures. Look at the upper right. It looks almost like a snake skin. It's really cool. But if you look even closer, you see a lot of little spherical droplets. And these are water droplets of water that is essentially interacting with the biofilm, which turns out to be homophilic. So it's oily, dominated by oils. And so the water beads up on the surface of the caves. What's kind of cool is that the size of these water droplets grow and shrink depending on the temperature of the surface. So in some ways, these water droplets serve to keep the humidity in the caves very constant, close to 100%. And this is a kind of an interesting biosignature in itself. So here are some other features in the caves. These on the upper left, you see ooze, and in between these sort of frozen or frozen features of the lava as it was flowing. And here on the right, there's another indicator of ooze. This is another sort of poorly studied feature in caves. And we also see mineral crusts. These are hard. You can't scratch them with a finger fingernail or with a chisel. You have to pound them with them. But they're crusts that show sort of this interesting patterns and form in different colors. And then we see these three-dimensional features. On the left side, we see coralloids, and you can see one that's broken art. You can see the striations of the lamina forming these coralloids, and these are maybe a few millimeters to maybe up to a centimeter in length, and they're mostly on the ceiling. But it's these mineral features that are most interesting to me, because I think it's these mineral features that have the highest chance of surviving over geologic timescales and could be waiting for us in caves on Mars. And finally, we see what we call cave polyps. And these compositionally are very similar to the coralloids, but they form on the floor and sides of the lava tubes. Excuse me. So here are just some more pictures of polyps, and you can see relative to my thumb how big they are, but they vary up to I've seen them in caves all over the world, but at lava beds, the longest ones we've seen are about 1 centimeter. And on the right-hand side, you see two thin sections showing these polyps. And two things to notice. One, first of all, the thin section, if you haven't seen one, it's about, 5 centimeters long? So that's the size. And if you see here in thin section, first thing you might notice is that they have striations or lamina, sort of alternating color bands. So this, in some ways, is reminiscent of a stromatolite that you see in the oceans. Although those are quite different, because stromatolites have a lot of photosynthesizing microbes, and here we're in the darkness. And also, stromatolites are growing underwater, and these are just right near the surface, so the contact between water and air. And these are actually growing in air with drips and splashes of water. So what the scientist team did is we set out to proposed something we called a mineral microbe continuum. We wanted to see whether or not, as we move from a more mineral-rich material, i.e. bare rock, which really wasn't bare, we looked using ATP to see how much metabolic activity was on the surface of these bare rocks, and found quite active indeed. Moving towards more microbe-rich material that was soft. So the mineral or the hard features, and going from bare rock, mineral crust, coralloids, which are usually kind of crumbly, and the polyps, and then onto the microbial film, which was soft and very thin, much less than much less than a millimeter in thickness, into the ooze, which you could move with your finger, and see whether or not there could be differences in communities living there, or the amount of biomass associated with the features. Well, of course, our proposed mineral microbe continuum, we thought, oh, maybe this will be a clue as to what we should look for, and it'll be very different. In fact, it wasn't that different. But now I'm going to excuse me again, there's a lot to go through here, but I just want to show you a short summary of a few discoveries we've made so far with some of the analytical probes we've used. With the microbiology, we found that the microbial communities associated with the mineral dominant features are distinct, just slightly distinct from those in the microbial dominant features, so the hard ones versus the soft ones. And this is based on prokaryotic diversity metrics, so sort of standard diversity analyses for 16 and 18S, as well as unique ASVs. So that's what we found from the metagenome assay. One difference is that the ooze is distinct from all of the other categories. We think that the actinobacteria, which was very prevalent in all of the other samples, and probably gives the biofilm that bright color. So the ooze lacks actinobacteria, and also taxa associated with ammonia and nitrate oxidation, or different species that are sort of participating in the nitrogen cycle. And finally, there's very little overall diversity between the caves. So we can look at a cave with a lot of human visitation versus a cave that's been undisturbed for most of its existence. We find very little difference in the microbial communities there. Where we do find variation is along the cave from the entrance down to the toe of the cave. And in terms of the eukaryotic community differences, we do see that we do find differences based on when we sampled, What did we sample in the summer or the autumn when it was wetter? Or do we sample when there was more, visitation from larger species into the caves? In terms of the lipid geochemistry, we found that biofilms contain very diverse and unusual fatty acid biomarkers. This is not unusual given the different microbial communities we're looking at, and many of you have probably studied and know that different domains have different types of cell membranes that are distinct and can be identified based on their fatty acid composition or lipid composition. So we looked at the IPLs, the intact polar lipids, and found a lot of branched, saturated, and trans-unsaturated isomers. Very interesting, because we can use these to isolate and identify just who's there. The fatty acids that are likely those produced by actinobacteria and biofilms have carbon isotopic signatures that require in situ subsurface carbon fixation. So in other words, they're very depleted in carbon-13. And this was interesting because we think that there's more fixation in the cave, or more autotrophic activity in the caves than heterotrophic activity. And this was also supported by the water geochemistry studies. Based on carbon isotope signatures, the biomass from these secondary mineral features is assimilating surface-derived organic carbon. In other words, the basalt or the lava tube walls don't have enough carbon to provide the carbon we're seeing along the walls of the carbon. So this material must be coming in from the surface, probably carried in by fluids along the major fractures in the caves. And overall, as I mentioned, the lipid geochemistry indicates that autotrophic activity is dominant over heterotrophic activity. And this was a very interesting discovery, because it shows that chemosynthesis is alive and well in the subsurface. In terms of the aqueous geochemistry, there's sort of an interplay between evaporation and splashing of water that's dripping from the ceilings. Now, if you put a drop of water on glass, what happens? It doesn't bead up unless there are fatty acids there. But if it's a clean glass or a clean basaltic glass surface, it essentially films a coating of water over the entire surface. So it doesn't have much surface tension on the glass. And but at some point, or if it's attached or getting stuck on the lipids or on the biofilms, then it can form these droplets, and eventually they become too heavy and drip down, and that helps feed the water to the organisms that are on the cave floor that eventually form the polyps. This is just a cartoon showing that. So the source of this water, and this is based on the oxygen and hydrogen, or the comparison with the meteoric water line in oxygen-hydrogen isotope geochemistry, it's regional meteoric water, falls right on that path. And the water chemistry reflects the local rock chemistry. So what's on the surface is very prevalent inside the caves. I mentioned that evaporation is important in the silica precipitation. What we find is there's a lot of silica dissolved in the water, and these features have a lot of these secondary features that are mineral rich, have a lot of silica in them. And there's also a lot of dissolved organic material, or DOM, from the cave waters. And because we find such a great source of carbon coming in from the surface, this does support the fact that there's not a need for that same heterotrophic metabolic activity, but that there's a source rather of carbon coming from the surface. So in terms of the petrography or the geochemistry, here's a thin section view of an example of these polyps. And I sort of let it slip before, but one thing is very interesting is that the dominant composition of these features, both the polyps and the coralloids, is not what you see in stromatolites where they're carbonate. It's actually silica. So you have bands of silica and carbonate forming together to form these lamina. It's really cool because we don't see that at all in the ocean environments and marine environments of stromatolites. But if the fact that these things are silica makes sense, because there's so much available silica that's dissolved in the water, probably from the surface. And also silica chemistry is more resistance to erosion than carbonate. So that's even a better indication that these features might have a chance of surviving longer in the geologic record or over geologic timescales, as an indication of recording it in the presence of life. Here's another example from a thin section showing that base. I've underlined the base in here. It's just the stems, as we call the lobes of the polyps. And this is the base in plane and cross-polarized light, showing in the center is that this polyp is forming on a basalt host base. And you can see these white little lays are pelagic lays, and they're abundant even though we can't see them with our eyes. But you can see, again, the amorphous or cryptocrystalline silica interspersed with some lesser amounts, but a significant amount of calcite. Now, we did look at these in more detail using electron microscopy, and this is that same image just blown up a little bit, that image of the boundary between basalt and the secondary mineral feature. And we see textures that have been indicated elsewhere by other investigators to be indicative of textural features that are formed by microbes. So these are high resolution images showing these sort of hollow or tubular structures that are mostly silica in the base of the speleothems or the secondary minerals. So I want to say that we did not prove, or we have not been able to prove that these secondary features, whether it's the biofilm or the mineral features, the coralloids and polyps, are actually produced by microbes. So we're inferring this based on the contact and the proximity and the composition that we analyze in the lab. Seems to be a pretty good assumption or interpretation, however. Okay, now moving on to the next part of Braille, which is the robotic study. So I mentioned that the foot scientists, and you have to be comfortable in tight situations, but the humans can go where robots can't follow. But that is changing little by little. But for this study, we worked first with wheeled robots and then eventually with legged platforms, legged robots, quadruped robots, because we found those were much more agile in the caves. So when we were working with robots, we picked caves that would deliberately to enable ease of access by the robots. So we sort of swayed our study a little bit because we wanted the robots to be able to walk around without crashing too much, both for the sake of our study, but also to protect the caves. Anyway, we picked 2 caves, and here is a Cave Research Foundation map of one of the caves of our study, the primary one called Valentine Cave. Now, if you visit lava beds yourselves, you can walk into Valentine Cave. It's been a tourist cave for 35 years, and it has a lot of human visitation. It's a fantastic cave. It is perhaps my favorite cave in the park, and it's about a little over ½ meter long from the entrance and the depth from the surface is very shallow, only about 20 meters. And in this diagram, you see both the map coming in from the surface at the bottom and moving out towards what we call the toe. And then below that, you see a cross section where you have the entrance at the left-hand side going down and down until you're about 20 feet below the surface. And this is the cave where we conducted the large amount of our robot studies. Imposed on this map, and this map was hand-drawn by cavers, is a LiDAR map that was made some years later by our team. And I'm so impressed by how well the cavers map. This one was done without using a LiDAR or a tool. This was done by hand with a team of 3 or 5 people, taking turns walking in the caves and using primitive tools like plumb bobs and rulers and well, I guess they did use a metric distance indicator, and then someone taking notes and drawing the cave as they went. It took about 3 days to make. By contrast, the LiDAR map took about, I think it took about half an hour. So here we are setting up in the entrance of Valentine Cave. We brought every day, some days we worked on the surface, but in the summer it was quite hot in the cave. And we brought all of our gear from a truck every day. It was a great workout and carrying it into this cave. This cave has steps to enter it. So the robot can walk into the cave, but for the purpose of our experiments, we started the robots already inside the caves. You can see the space station is a big computer with a big CPU to power the computers and communications with the robots. And here are our new friends. These are, you might recognize these. These are Boston Dynamics spot robots. And the Braille project was very lucky to partner with a team at the Jet Propulsion Laboratory in Southern California who were competing in a DARPA challenge, or the DARPA Subsurface Challenge, to operate robots and explore the subsurface environments autonomously in competition. So we were able to use all of the technology that the JPL team developed to compete in this global competition and apply that to lava tube studies in California. So in this case, these are considered off-the-shelf robots. So the big ad was the developing an autonomy solution, or a payload that we could put on top of the robots that would allow them to explore and communicate with one another and with humans back at the base station. In addition, we have cameras and environmental sensors that are also attached to the robot. And in this example with our friends here, the one on the far left is actually a camera that's created by Boston Dynamics that has a point, tilt, and zoom capability with a 30 times magnification. And we also walked in the caves with cameras that were not yet or have not yet been mounted to these robots to compare different fidelities of different cameras. Okay, let's see. How's this going to work? We weren't sure whether or not these quadrupeds would be able to walk in this environment. And now lava beds, here we have it walking into the cave. It's walking backwards, but it's maneuvering and walking by itself without help from a human operator. But in terms, even though these things have small feet that are only a few centimeters long, these robots were able to navigate over cracks, over irregular terrain, and when it got wet, we actually fitted the bottoms with bicycle tires to give them more traction. So overall, these robots perform much better than the wheeled robots that had a hard time getting down the maximum drop. Here we have a distance of about 2 meters, and the robot can navigate. In the 1 or 2 cases where it fell over, the robot can self-right itself, and this is really credit of Boston Dynamics and the JPL autonomy solution. Oops, I'm going to stop this now. Okay, so here again, to summarize, the legged mobility robot performed superbly in the lava tube. Low ceilings, it could crouch, it could walk over cracks, climb over boulders, crawl around rubble piles, go through narrow passages and up steep slopes. So this is, for our planetary exploration, it's my robot of choice. And in the case of this robot, it actually weighs maybe 1/10 the amount of a wheeled rover that's currently on Mars. So I'm actually, in this case, at 1/100th of Curiosity rover. So I can envision a scenario in which you have a whole pack of these robots for the same payload mass that you might have with a wheeled robot. Okay, so we use this, the capabilities, as I mentioned, developed by the JPL team, and they call it the nebula architecture. That's the nebular solution, partnered with the Boston Dynamics hardware. And now I'm going to show a couple of robot terms. We looked at 8 features to allow us to move in the caves autonomously. And the ones we focused on in this study are using the robots in the tubes, lava tubes, for understanding of place and being able to detect artifacts, mission autonomy, planning and interfacing with the humans, and also integration of new hardware and checking the mobility on the ground. So I'm going to just sort of walk through these kind of quickly, but if there are questions, please text me and I can send you the paper by the lead author of this JPL team project. State estimation is when a robot recognizes its environment and estimates its own position and orientation. So here the red and yellow colors indicate boundaries or the walls or obstacles in the cave, and the robot is able to figure out where it is. So it was really interesting working with this team because I had to manage my expectations for what robots can do. I am influenced by what I see in the movies and what I read in science fiction books. So it was really interesting to see how well this robot performed, and yet how primitive it performed based on what we see in the movies. So you know that we have been using autonomy and AI for many years now as missions on Mars extend past their initial NASA designated lifetime. This is in part because as the missions keep going, the funding to support the humans that work on the missions goes away. And so the robots, we've had to resort to robots picking targets to examine, picking pathways to travel, but this is on the surface where we can communicate and monitor them to a great degree and always step in if we need to. Anyway, number 2 is SLAM, which is a very familiar term to people who use robotics. This is simultaneous localization and mapping. So as the robot is figuring out where it is, it's sending out usually a LiDAR, a scan to figure out what the local environment looks like and creating a map, which it can then relay back to headquarters. Local planning, this is when the robot looks around and creates a precise trajectory to avoid dangerous area by coding, in yellow, orange, and red, essentially estimating the degree of danger if it chooses a certain path. And then it will plan. We can either make a waypoint saying where we want the robot to go, and the robot will determine its own path to get there, or the robot can just explore on its own, but creating its own waypoints or safe points along the way to allow it to explore an unknown area. Communication, robots and operator exchange data through these communication nodes that are ejected from the back of the robot, or as I like to say, the robot poops out a radio transponder to allow communication out of line of sight. And then finally, object detection. We're still working in this area where robots are able to use deep learning. In other words, we've created algorithms to help identify targets, and the robots can use deep learning to save bandwidth, or rather use of the bandwidth, by sending only selected interesting data back to the base. And then mission autonomy and interfacing, and the hardware integration. So this is a summary showing the fully loaded spot robot with the LiDAR, 5 cameras, thermal camera, ambient gas sensors, computers. The computers are about the size of a small shoebox, and radios for communication. You can see on the back, these are the communication radios. So we have plans to increase and add additional scientific instruments to this payload, but this has not happened yet. And here's an example of the front view of Spot, showing as it's moving down from the upper right, looking at possible waypoints to plan its path into the lava tube. So we wanted to test potential mission scenarios. So this is a ConOps for a cave exploration mission with 2 robots. And at the upper left, it says cave entrance, or maybe a lander. And then you're going down into the cave as you go down toward the right. And we have 2 different robots here working in collaboration autonomously, and communicating with the scientists and engineers and data scientists who are either at the mouth of the cave on Earth or perhaps in a remote operations center. And in this scenario, the vanguard, or the blue robot, goes fast and maps and indicates potential targets of interest. And then the second, or the rear guard robot, comes at a much slower pace and goes up to those targets and explores to see if they're worth looking at or if they can keep going. So here we conducted timed exercises evaluating the robot's ability to detect artifacts placed in the cave. As I mentioned, we were using the JPL software, and in this case, they trained on search and rescue artifacts. So in these experiments, we sectioned off a part of the cave for our experiments, and we took the radio transponders out of the equation by pre-positioning them in the cave so the robots can send data and information back. And then we time to see how long it would take one robot working by itself, two robots working together, one robot working with a team, a human, to help detect things versus two robots with a human. And can you guess who won? Rather, and the win was you succeeded if you detected the highest number of artifacts in the cave over the lowest time. And these were 20-minute experiments. So back to who do you think won? Well, with one exception, that is me, because I'm very familiar with this cave. The robots won in all cases. And this is because the humans take longer to make a decision, or we pause, and the robots just do their job. So that's sort of interesting. I'm going to skip this video, maybe I'll show this one. It's very short. It shows how the robot squats and then ejects a transponder. Boop. That's it. And here we are getting ready to go. I'm going to skip this video, I think. And then here's a plot showing the map that we're seeing at the base, the super base where the computer is, showing the LiDAR map of that's being generated in real time. And in all cases, the humans, the team is monitoring the robots as we go into the caves. And here's the artifacts. Here are the pictures of the artifacts. This is what we're seeing again from the base computer. We also have developed essentially a real-time virtual reality tool to be able to monitor the robots from afar. However, the resolution with this in real time right now is almost like that of Minecraft. So it's not very good, but when we take data back to the lab and reprocess it, it's regular full resolution. But it's potential for future missions on Mars. And finally, we are working separately to classify targets of scientific interest using machine learning and eventually AI. So in this case, we've collected thousands of images, both with Spot and also on our own, with the foot scientists taking pictures in the caves. And then we hand label these initially, and eventually the computer, there's a automation tool that will hand label this for us. And then we train them on a part of our collection. And then we test in the caves and we train again. And then now we can go into the field. We've tested on biofilm, on polyps, and on ice. And we've had a very high percentage, over 85% success in detecting these things in the caves with handheld cameras and Spot. But we have not integrated it into the JPL autonomy solution yet. So that's for future work. And here are two of our teammates. And you can see another close-up of the golden biofilm, which is very easy to distinguish in the caves, but it's hard to distinguish the boundaries. And in the larger picture, you see the water droplets there. Another picture of the polyps. And finally, we're testing with Boss Dynamics and others testing different features. So this is a robot where we have one of the Boss Dynamics technicians who's a super guru, super operator, and he's working with me to test the dexterity of the robotic arm on Spot to see how it could sample something or pick up something. And there's a lot of promise here. And we did also play around with multiple robots working collaboratively. In this case, we're actually using human operators to maneuver the robots, but we can see or envision heterogeneous or collaborative and complementary payloads on the different robots that could then collaborate together to, in this case, swab the side of the cave for a sample, or use different cameras and lights to work together, collect samples, and better study the caves. We have different scenarios that people on our team and others have developed for envisioning a swarm of legged robots on Mars entering into a cave. They're a little fantastical this time. In this one, we're actually using tethers or ropes to help the robots go into the caves, because not only are the caves much bigger on Mars and even larger on the Moon, but the entrances or the distance from the surface to the base of the cave, we expect to also be larger. Maybe we could use a helicopter in the future to help explore these caves initially before we send the robots in. And here's a cartoon. I'm wrapping up here, that these caves are really good sites for potential human habitats. And I've been so pleased to see in the past few years, in the movies, actually, National Geographic has a film on Mars, and it's a docudrama, and they set up their human base in a lava tube. So that's I like seeing that. I think the moon will be a necessary testing ground for missions to caves on Mars and beyond. And most of the concepts have focused on entry through a lunar pit, either with some sort of tether, or more recently with intuitive machines and astrobotic, thinking about a hopper or something that could hop into the cave. This is a concept called Moondiver that's been developed at JPL, where they actually have a four-wheeled rover. They separate the axle and lower that down into the skylight. Gives the team an opportunity to have instruments in that axle that could then look at the lava history or the geologic history of the moon before it gets to the base. So this is a very promising concept. And finally, I'll just say that it's been really great working with the robots in the caves. And these robots have a battery life of about 90 minutes, and then we can swap out the battery. But Alva said that we've accomplished a lot, and there's so much more to do, both at lava beds and around the world. And I hope some of you might be interested in pursuing studies in lava tubes that could help us prepare for off-world exploration. At the end of the day, though, we're quite tired, and Spot, or the robots, keep going. And finally, I just want to say that Braille is a big team of more than 45 people. And these are just names that I've put up here. I don't give you a chance to read them, but it's a collaboration effort, and I'm the team leader. So with that, I'll conclude and see if there are any questions from the audience.
Okay, thank you very much for the informative presentation, Dr. Jen. Now I will introduce you to questions from our audiences. Okay. Thank you, Dr. Jen, for this wonderful information. I'm curious about your thoughts on whether Mars will ever be livable for us human beings. All these research are very valuable, but I feel like we should pay more attention for saving our beautiful planet Earth, which is already very capable of renewing itself. Thank you.
That's a good question, and there's always it's always a challenge, because how can we not focus on saving our planet? So there have been, I guess, arguments for and against off-world exploration. And one thing I'll say is that in preparing for this off-world exploration, we see the money involved that looks like huge amounts. But for example, the Curiosity mission on Mars is essentially the equivalent of one movie ticket per American that covers the cost of the whole mission. And over the course, so it's very, very less than 0.0001% of the US annual GDP. But there's a lot of technology transfer that comes from learning how to operate in space and off-world. So I think what's really interesting is that technology can then be turned back on Earth. In fact, as we welcome more and more countries to the title of spacefaring nations, it's because they have satellites in space that are actually being used to help study agriculture or changes in the climate, and how that's affecting our own planet. So it's sort of a long-winded answer, but I think these are complementary efforts, right? So this is a little more romantic and exploratory. And when I was a girl, I wanted to go to the moon, and now I just want I want one of you to go to the moon, but anyway, or go to Mars, right? So I think the kids today, someone who's a child today will go to Mars, but I think in the development of technology to get us there, we'll develop a lot of things that will help us better understand Earth. I don't know if that answers your question, but.
Okay, thank you. diye another question. How have Braille's finding in lava tubes refined our strategies for detecting biosignatures on Mars?
That's a really good question. I think we have two things. We have the laboratory studies that use equipment and analyses that we aren't able to send on a flight mission today, but we can characterize them. And once again, we are introducing our own biases, that the biosignatures on Earth will be those that we might find on another planet. So we're hoping that if, for example, in our idea for a mission concept to Mars or a Martian lava tube, we would send in these robots that would do the same approach. They collect images and maybe chemical probes, chemical data, and then either send information back or investigate on their own to look for things we recognize as biosignatures on Earth, on Mars. Now, if there was something else, we won't see it, in which case we could use other tools, there's other AI and unsupervised learning to see what features there are different. But it's so cool to see and to learn about how these especially these secondary mineral features, preserve both a sort of a chemical record of the environment and also a record of the climate in the lava tubes.
Okay. Next question is, what were the most compelling insights ChemCam provided about Mars habitatly during the Curiosity mission?
Okay, what are the most compelling insights from ChemCam? So ChemCam, and this is I guess someone knows this, that I'm still part of the ChemCam team, and I worked on this team which has the first interplanetary laser, so that's pretty exciting. And it's been, I guess, superseded by SuperCam, which is a combination of LIBS and Raman, but ChemCam is LIBS. And ChemCam actually didn't provide a lot about habitability. What the exciting instrument there is the ChemMin. So ChemCam is like the geologic scout. So it's fired over many over 1 million times on Mars, and it gives us elemental information. So it collects light from a cooling plasma that's been generated, microscopic plasma generated by a laser firing on a target. But it complemented the mission by telling the robot where it should go. And so I don't know if any of you remember, but we landed in 2012, and a few months, 6 weeks later, I guess, we were over at an intersection, surface intersection between 3 different geologic boundaries, and we stayed there for 7 months because it was so exciting. So we stayed there for almost half of the nominal mission and drilled in, and ChemCam helped us identify these boundaries and helped us identify the sort of the element chemistry. But it was really this ChemMin instrument that allowed us to bring the whole rover itself brought material on board to the rover where they have this X-ray diffractometer. XRD, X-ray diffractometer, and allowed us to look at mineral patterns that gave us actual mineral, not just element, but mineral information about the environment. And those minerals were such that on Earth would have formed underwater or in the presence of water. So that's, and that would have been, based on our modeling and constraints, that would have been slightly alkaline, pH 7, very drinkable water. So we were so excited, and that's why we stayed there for such a long time. And there have been many discoveries since. Most recently, I mentioned looking at the drill data again and finding carbonates, because this has been a big mystery. Why don't we see carbonates if Mars had oceans? So I guess I would say ChemCam supported the mission by helping guide the direction of the robot, or help a scientist guide the direction of the robot. But it's really this ChemMin instrument that's on board the rover. It's the first time we've been able to look at mineralogy on another planet.
Okay.
But good question.
Yeah, another question. Yeah. Hello, Dr. Jen. I'm Aslı, studying astronomy and space science at Erciyes University. What do you recommend for those who want to be astrobiologists like you?
That's a great question. I think when I started in school, we didn't have the term astrobiology. We used exobiology. But advice, that the simplest thing would be to find a mentor or an advisor who is already working in this very interdisciplinary field. That's probably the most strategic way. Or you could do what I do, which is just be interested in many topics and then realize, well, how do they all come together? Well, they come together in this wonderful field of astrobiology that is very multidisciplinary and requires you're feeling uncomfortable as you talk with people who are studying or experts in other disciplines.
No. Okay, the another question, if you have. In what ways have analog Earth environments shaped current astrobiological exploration techniques for other planets?
That's a great question too. We have extreme environments on Earth, many, whether it's looking at current hot springs and ancient hot springs, and knowing what to look for. So I think a good example is we found a lot of silica in Gusev Crater with the Spirit rover, and we recognized by looking at paleo environments on Earth, i.e. environments where there's no water now, or very little water, and also comparing those with environments on Earth where there are active sinter and hot springs, and to be able to recognize the ancient features on Mars. And anyway, that was pretty exciting. But there are many examples of this. And also, we do practice field tests many times before we send a robot to another planet. And when I first started practicing field tests with the Curiosity rover team, we were very slow and very awkward, and we made many mistakes. But we practiced a lot, and then we practiced even harder during the 9 or 10 months it took for the robot to get to Mars. And so by the time we got there, we were a little more skilled, and we've gotten even better since. So there are operational, collaboration challenges. How do you run an operation that we can practice on Earth? And they're also looking at ancient geologic terrains on Earth for comparison.
Okay, thank you. Another question is there any other planet analog caves located in Earth apart from California?
Rasul, yes, there are so many. So I put that slide up there because I want to know about the caves in Turkey and Turkey, excuse me. And I have been to caves all over the world, and I'm sort of a caver. And what's so interesting is that when I go into these caves with my caver colleagues who are much more expert at being in the caves than I am, oftentimes they don't see these microbiology or secondary mineral or secondary features in the caves. They're looking at the shape of the cave. But every time I've gone into a cave, whether it's most recently in the Canary Islands or in Saudi Arabia or in Hawaii or in New Zealand, I see very similar features in all of these caves. So I'd like to know more locations. So if you know of any in Turkey, please tell me.
Okay. Another question is, what evidence suggests that actinobacteria are responsible for the production of unusual fatty acid biomarkers in cave biofilms?
I guess two things. One, we did separates, so we were able to, in some cases, actually make cultures of some of the actinobacteria, and that's the most direct way to determine this. But also, it's just based on comparing the abundance of actinobacteria present, and that we determined with ribosomal RNA assays, and then also looking at essentially the mass spectrometry, the GCMS or mass spectrometry of the samples themselves that identify the molecular weight of these fatty acids.
Okay. The another question, if we have, why does lipid geochemistry suggest that autotropic activity dominates over heterotropic activity in cave environments?
Two things. The first thing, which is not the more absolute answer, is that the archaea, which is autotrophs are often from archaea. They have a very simple cell membrane, and so simple fatty acid pattern. And that's one thing that we saw a lot of these dominating the biomass composition. But more importantly, we used carbon isotopes, or this is part of this thesis work of Matt Zielinski from Northwestern University. But when in the process of fixing carbon, the carbon-13 is depleted. So we have very negative carbon isotope signatures. So in this case, the signatures are around minus 45. If that means anything to people who study carbon isotopes, as opposed to, say, around minus 15. And so it's this very, very negative that suggests that we have autotrophy present. And the fact that these samples, especially the biofilms, showed very, very negative carbon isotopic patterns suggests that autotrophy was dominating over heterotrophy.
Okay, thank you for that. The other question, how do carbon isotope signatures indicate the presence of in situ carbon fixation in subsurface biofilms?
I think I've sort of answered this, but it's just what's known based on, honestly, on laboratory experiments to show that there's higher fractionation when you have autotrophy versus when you have heterotrophic activity. So, and that also very different from the photosynthetic composition or derived composition of carbon from the surface, which is not quite so extremely negative. So even carbon coming from the surface could be feeding the other organisms, the heterotrophs. But when we see this very negative, it's indicative of the chemosynthesis.
Okay, I think this last question. Could Braille's tech be adapted for future missions in icy moons like Europa? What's the farthest frontier you see Braille-inspired systems reaching in the search for life?
These are very good questions. I think Braille, well, again, it's baby steps. So what was interesting for NASA about Braille was not only looking for these mineral biofeatures, but also operating with absence of light. So here we are operating in the dark. So on Europa, and also we're operating autonomously. So in very far away places, I don't think these robots will be the ones that we'll send away. And in fact, these robots are not ready for space. We have data handling issues, thermal regulation issues on the planets. We have issues potentially with dust and operational challenges of operating in the high and low temperatures. But what we can learn from Braille is that these robots can operate collaboratively, out of line of sight of human operators, and they can form a very beautiful 3D picture in a dark setting. So I think that will help. And I think all of the work as we go further beyond Earth builds on the work of prior investigations. So if Braille can contribute to a mission one day to the moon or to Mars, or even beyond, we'll be very grateful.
Okay, I think we have run out the questions. Thank you again for this impressive presentation, Doctor. Wishing you a peaceful and joyful Easter. I hope to see you in our other events.
Thank you very much for inviting me. And if you have any additional questions, please don't hesitate to contact me.
Okay, thank you very much. See you soon.
Bye-bye.
Bye-bye. We have come to the end of this part. After a short break, Mr. Ahmet Talât Saygaç will be with us with his speech on life in the solar system in Turkish. See you after the break. Kısa bir aradan sonra Sayın Ahmet Talât Saygaç, solar sistemde yaşam konulu konuşmasıyla bizlerle olacak. Moladan sonra görüşmek üzere.
Tekrardan merhaba sevgili bilimseverler. Geleneksel 5. Uluslararası Astrobiyoloji Konferansımızın ikinci oturumuna hoş geldiniz. Bu oturumumuzda sevgili Ahmet Talât Saygaç hocamız Evrende Yaşam, Güneş Sistemimizde Yaşam başlıklı sunumuyla bizlerle birlikte olacak. Sizlerin de huzurunuzda Ahmet hocamızı davet ediyorum. Merhabalar Ahmet hocam, nasılsınız?
Merhaba Berra, teşekkür ederim hepinize davetiniz için. Kolay gelsin.
İsterseniz seyircilerimizin de sizi tanıması açısından kısaca kendinizden bahsedebilirsiniz.
İstanbul Üniversitesi emekli öğretim üyesiyim. Uzun yıllar astronomi ve uzay bilimleri bölümünde çalışmıştım. Daha sonra toplumda bilim-toplum ilişkileri üzerine bir hayli çalışmalarım oldu. Son zamanlarda da evrende hayat, güneş sisteminde yaşam, bu konulara biraz ilgi göstermeye başladım doğrusunu isterseniz. Bir kitabımız var bununla ilgili, yazmaya devam ediyoruz Mehmet Emin hocamızla beraber. Bu sunumda da kısaca size bu kitabın içeriğinden gelen bazı konulardan bahsetmek istiyorum. Berra dondunuz ha?
Dondum, evet, internetimde bir sorun var maalesef, kusura bakmayın. Davetimizi kabul edip geldiğiniz için çok teşekkür ederiz tekrardan hocam. İsterseniz sunumumuza geçebiliriz.
Ben teşekkür ediyorum. Bu sistemi ilk kez kullandığım için nasıl olacağını bir bakalım.
Sunumu tam ekran yapabilirsiniz aslında. Şu an her şey
Şu anda
gözüküyor.
yaptım. Görebiliyor musunuz rahat rahat?
Evet, görebiliyoruz. Hiçbir sıkıntı yok. Tam
Evet.
sunum yapın. Bakalım oluyor mu?
Şimdi nasıl?
Şu an görüntü...
Hocam şu an ilerliyorsanız biz görmüyoruz.
İlerlemiyorum. İlk sayfasını gösteriyorum. Görebiliyor musunuz?
Bizde 3. sayfa görünüyor hocam sunumunuz.
3. sayfa doğrudur. Evrende yaşam,
Evet.
güneş sisteminde yaşam.
Evet.
Tamam.
Tamam, doğru
Peki.
hocam. Şu an.
Peki hemen başlayalım. Biraz bolcana yazılarım var. İyice izleyebilsin seyircilerimiz diye. Türkçe anlatıyorum doğal olarak. Sunum planında evrende yaşamdan kısaca bir bahsetmek istiyorum. Güneş sisteminde yaşama daha sonra geçeceğim. Başkaları varsa sorusunun üzerinde azıcık duracağım. Ve sadece biz varsak durumlar nedir? Ondan bahsedeceğim. Sadece biz varsakın resmi de burada. Evet. Evren aslında her şey. Evren dediğimiz şey her şey. Tüm uzayı ve uzayın içerdiği tüm madde ve enerji içeriyor. Bunun içerisine siz de dahilsiniz, biz de dahiliz. Her zaman, hatta zamanın kendisi de buna dahil. Evren dediğimiz zaman. Dünya ve Ay, diğer gezegenler ve onların onlarca uydusu evrenin aslında bir parçası. Çok doğal olarak. Asteroidler.
Hocam çok özür dilerim, bölüyorum ama eğer şu an ilerliyorsanız biz hala sizin ilk yani 3. sayfanızı görüyoruz.
Anladım. İlerliyordum anlatırken. Peki yeniden vereyim.
Siz öyle yaptığınızda biz full screen görmüyoruz hocam. Hala PowerPoint'in kenarda slaytları gösteren haliyle görüyoruz. Sanırım az önce Jen hocamızın yaptığı gibi presenter mode kullanmanız lazım.
Onu nereden yapacağım çocuklar?
Hocam sanırım görünüm kısmından yapmıştı Jen hocamız. Ondaki İngilizceydi, şu an kafam karıştı.
Anladım. Tamam, ben de bakayım. Görünüm kısmından yapalım.
Yok, burada değil galiba. Slide gösterisi deseniz hocam, şuradaki animasyonların yanındaki.
Evet.
Burada olabilir.
Baştan diyor. Bir tıklayayım. Gördünüz mü herhangi bir şey?
Yok hocam.
İlerliyorum. Göremiyorsunuz değil mi?
Hayır. Şu an hala ilk sayfada kalıyor. Arkadaşlar F5'e basarsanız demiş chatten. F5'e basınca oluyormuş sanırım.
F5'te açtım tekrar. Görebiliyor musunuz?
Yok hocam. Görünmüyor.
Dur
Sanırım
hemen bunu
bu screen'i
çözmemiz
gösteriyor
lazım.
ya, ondan dolayı olmasın.
Evet. Hocam aslında sunucu görünümünü göster de tikli sizde.
Evet. Bu da tikli. Monitör
Evet.
otomatik. Başka ne var? Hay Allah. Bu provayı yapabilseydik çok iyi olurdu. Geçerli slayttan şunu bir deneyeyim bakayım. Görüyor musunuz?
Hocam şu an ikinci slaytı görüyoruz, evet. Işık kirliliği nedir diye
Devam
yazıyor.
ediyorum.
İlerlemedi.
İlerlemedi mi?
Hayır.
Bu kötü. Özel slayt çevrim içi sun. Bir de çevrim içi sunu düşünelim. Hay Allah. Bu iyi
Acaba
olmadı. Evet.
sunumu bize gönderseniz de ya da siz sunumu buraya direkt yükleseniz olur mu?
Hocam
Olur.
PDF'e çevirip hemen aşağıya upload yapabilirsiniz.
PDF'e çevirirsek canlı oynayan yerler var. PDF'de donar kalır,
Anladım.
gösteremem.
Onlar donacak, evet.
Sunumu size hemen yükleyeyim. Nereye yükleyeyim arkadaşlar?
Burada Slides and PDF kısmında Your Computer deyip yükleyebiliyorsunuz hocam. Present kısmını tıklarsanız Slides and
Evet.
PDFs yazıyor. Orada Your Computer var. Oradan buraya upload edebilirsiniz.
Dosyayı yükle diyorum.
Evet.
Seyircileri de bekletiyorum ama.
Hiç problem değil hocam. Seyircilerimiz bizim bu konularda anlayışlı. Çok teşekkür ediyoruz.
Ederim. Diyor ki daha küçük bir dosya seçin. Boyut sınırı 50 megabayttır diyor. Benim biraz dosyam büyük. Onun için demin bunu test etmiştim.
Evet, onu söylemiştiniz. Evet hocam az önce.
Peki nasıl yaparız?
Şöyle yapsak hocam, paylaşma biçiminizi değiştirseniz, ben bunu bir şu an stüdyodan çıkartayım.
Olur.
Siz paylaşma şeklinizi entire screen olarak değiştirseniz.
Nereden yapacağım?
Yine share screen deyip hocam. Window yerine, seçtiğiniz window yerine. Evet, share screen deyip orada entire screen seçerseniz hocam.
Seninkiler Türkçe ama söylediğin şeyin İngilizce. Ben bunu anlamaya çalışıyorum. Nereden yapabilirim diye.
Hocam stüdyoda İngilizce yazdığı için ben öyle söylüyorum.
Anladım. Benimki de Türkçe.
Büyük ihtimalle present'i sunum diye değiştirmiştir. Share screen'i de ekran paylaşımı diye değiştirmiştir. Ekran paylaşımına girdiğinizde yukarıda 3 seçenek var. Birinde Chrome tab yazıyor, diğerinde
PowerPoint'ten
pencere diyor.
bahsediyoruz.
Yok
PowerPoint'ten bahsediyoruz.
Yok, StreamYard'dan bahsediyorum.
StreamYard. Bende yüklü
aşağıda
değildi zaten.
var.
Şu an
olduğunuz oturumdan bahsediyorum.
Tamam.
Şu an olduğunuz oturumdan. Aşağıda Live Studio'nun yanında Present var. Present'tan Share Screen var. Ona basıyorsunuz. Orada pencere, tüm ekran, Chrome sekmesi gibi şeyler var. Oradan tüm ekran yapıp paylaş yapacaksınız.
Bir dakika, şimdi sunumu şimdilik durdurdum.
Evet hocam.
Present'ten ekranı paylaş var.
Evet hocam, ekranı paylaş yaparsanız orada 3 seçenek geliyor. Chrome tab, pencere ve tüm ekran.
Evet, ekranı paylaş diyorum.
Evet.
Sadece ekranı paylaş var bana gelen. Evet, ekranı paylaştığım zaman pencere var. Pencereyi paylaşıyorum.
Yok hocam, pencereyi paylaşmayın.
Tüm ekranı paylaşın.
Tüm ekranı paylaşın.
Tüm ekranı paylaşıyorum.
Evet. Tamam.
Paylaştım. Geldi mi?
Evet, biz şu an arka planda görüyoruz. Siz orada bir PowerPoint'inizi açarsanız, şimdi iç içe pencere gibi görünmesin diye ben onu şu an ekrana almadım.
Tamam, PowerPoint'imi açıyorum. 3. sayfaya tekrar gidiyorum.
Evet, ben şu an aldım onu ekrana.
Sunum moduna geçtim.
Evet, oldu hocam. Oldu.
Oldu mu?
Ama şu an tam ekran hala görmüyor. Evet, görüyoruz hocam, oldu, tamam.
Tamam, bir
Evet,
ikinci sayfaya
tamam.
geçeyim bakayım. Geçti
Tamam.
mi?
Evet, geçti hocam, çözdük.
Tamam, hızlanıyorum.
Tamam.
Evet,
Teşekkürler
aynı
hocam,
şeyleri
kusura bakmayın.
tekrarlayacağım. Rica ederim, çözdük ama bu testi daha önce yapmak daha iyi olurdu. Çünkü bilmediğim bir sistem olduğu için. Bunları hızlıcana geçeyim. Evet, evrenin her şeyi olduğundan bahsettim. Biraz önce sesim size gelmişti zaten. Tüm uzayı ve uzayın içerdiği tüm madde ve enerjiyi içerdiğini söylemiştim. Bu arada zamanın kendisi de, yani zaman dediğimiz, eğer o bir kavramsa, algıysa, bunu da içeren şey evrenin kendisi. Dünya ve Ay bizi direkt ilgilendiren iki cisim, diğer gezegenler dolaylı ilgilendiren cisimler ve onların onlarca uydusu evrenin bir parçası. Bunlar hepsi yaşamı aradığımız malzemeler aslında bizim. Asteroidler dediğimiz şeyler de aslında Güneş sisteminin kalıntıları, gezegenlerin arasında dolaşan kaya parçaları diyelim. Ve kuyruklu yıldızlar, onlar da bunlar gibi büyüklükleri biraz daha fazla, kilometreler mertebesinde. Bunların hepsi Güneş'in etrafında dolanan cisimler. Peki, Güneş, Samanyolu gökadamızdaki yüz milyarlarca yıldızdan birisi sadece. Ve bu yıldızların çoğu öte gezegenler olarak bilinen kendi gezegenlerine de sahip. Yani yüz milyarca yıldızdan bahsediyorsanız ve hepsinin en az bir gezegeni var diyorsanız yüz milyarlarca gezegenden, başka gezegenlerden söz etmemiz gerekiyor. Şimdi Samanyolu gözlemlenebilir evrenimizdeki 2,5 trilyon gökadadan sadece birisi. Bu rakamlar havada kalmasın. Şimdi resimlere geçince daha iyi anlayacaksınız. Ama gökada kavramını unutmayın ve bunun sayısının şu an için bizim hesaplayabildiğimiz 2,5 trilyon tane olduğunu bilin. Bizimki de dahil olmak üzere hemen hemen hepsinin merkezlerinde süper kütleli kara delikler de var bu gökadaların içlerinde. Gökadalardaki tüm yıldızlar ve astronomların gözlemleyemediği diğer tüm şeyler evrenin bir parçası. Basitçe evren her şey. Peki. Yaşı şu anda 13,8 milyar yıl. Biz bunu giderek daha uzaklardaki cisimleri gözledikçe zamanı hesaplayabiliyoruz. Değişik bir astronomik yöntemdir bu aslında. Ama bugünkü evrenin yaşının 13,8 milyar yıl olduğunu biliyoruz. Bilim bu sayıya en eski yıldızların yaşlarını ve evrenin genişleme hızına ölçerek ulaşıyor. Yani bir balon alın ve üzerine kalemle noktalar koyun. Sonra balonu şişirmeye başlayın. Çok basit bir örnek, bilinen bir örnektir. Balon şiştikçe o noktalarınız da birbirinden uzaklaşır. Evreni biz bu şekilde genişliyor diye düşünüyoruz. Evrende balonun üzerinde yer alan noktalar bizim gökadalarımız. Gökadalar şu anda birbirlerinden sürekli ve artan hızlarla uzaklaşıyorlar. Güneş sistemimize dönecek olursak 4,6 milyar yıl yaşında, büyük bir miktara benziyor. Ama tüm güneş ve gezegenlerin oluştuğu zaman bu kadarlık bir zaman içerisinde gerçekleşti ve tamamlandı. Dünyadaki yaşama gelecek olursak, cisimlerden çıkıyoruz şimdi, yaşama gelecek olursak, dünyamız da 4,6 milyar yıl yaşında, güneş sistemiyle aynı yaşta, ama dünyanın üzerindeki yaşamın hemen 4,6 milyar yıldan sonraki 1 milyar yıl içinde başladığını tahmin ediyoruz. 3,8 milyar yıldır var. Ve insanlar ise sadece birkaç yüz bin, belki de en fazla milyon yıldır dünyanın üzerinde varlar. Bu kadar gelişmiş bir canlılık olarak. Bunları nereden biliyoruz? Bunların hepsinin kanıtları var. Fosil şeklinde küçük canlılara ulaşabiliyoruz. Başka bir deyişle evren türümüzden yaklaşık 56 bin kat daha uzun bir süredir var olan bir şey. Yani bizim varlığımızdan 56 bin kat daha uzun bir süre önce gerçekleşmiş ve var olan bir şey evren. Eski mi? Eski. Bu ölçüte göre şimdiye kadar olan hemen hemen her şey insanlar var olmadan önce gerçekleşmiş şeyler. Burada bir zaman çizelgesi var. Şuralarda bir yerde 4,6 milyar yıl, 5 milyar yılı alacak olursak hem Güneş'in hem de diğer gezegenlerin ve dünyanın oluşumunu buradan başlatarak devam edebiliriz. 3,8 milyar yıla geldiğimizde yaşamın başladığını, fototropik bakterilerin, siyanobakterilerin ve sizin bildiğiniz, biyologlar olarak bildiğiniz bu canlılığın başladığını görüyoruz. İnsanın varlığı ise bu 4,6 milyar yılın neredeyse sonundaki sadece 1 milyon yıl veya birkaç yüz bin yıl öncesine dayanıyor. Daha öncesinde memeliler, damarlı bitkiler, kabuklu omurgasızlar vesaire oluşmuştu. Peki. Yalnız mıyız gerçekten? Dünya dışında yaşam arayışı aslında daha yeni başlıyor. Ancak bilimin cesaret verici bir cevabı var. Samanyolu'nda birçok gezegen var, birçoğu bizimkine benziyor. Bunları yavaş yavaş çıkartmaya başladık. Ancak bilmediklerimiz, bu konuda bilmediğimiz, yazılacak olursa ciltler dolusu kadar bilgiye ihtiyacımız var. Bilmediğimiz çok şey var. Burada yaklaşık olarak 500 tane başka yıldızların etrafındaki gezegenlerin gerçek boyutları ve olası biçimleri konusunda bir tablo var. Bunların hepsi bu renklerde, bu güzellikte çekilmiş değil. Elbette elle yapılmış cisimler bunlar. Ancak analizler sonucunda ortaya çıkan diğer gezegenlerin görüntüleri bunlar. Bu resimde 500 tane ama şu anda doğrulanmış yaklaşık olarak 5800 tane. Doğrulanmayı bekleyen ise toplamda 7500 civarında başka yıldızların etrafındaki gezegenlerden bahsediyoruz. Yani bunlar bizim yaşam için uygun olabilecek yerler mi dediğimiz şeyler. Biz yıldızların üzerinde canlılık aramıyoruz doğal olarak. Mümkün değil ama gezegenlerde aramalıyız. Ama hangi gezegenlerde? Bizimkine benzeyen gezegenlerde şimdilik. 20 Nisan itibariyle, bugün itibariyle 5856 tane bilimsel olarak doğrulanmış başka yıldızların etrafındaki gezegen var. Bunların 1997 tanesi Neptün benzeri gezegenler. Yani bizim Neptün gezegenimiz gibi. 1897 tanesi gaz devleri yani Jüpiter ve Satürn gibi ve Neptün, Uranüs gibi. 1738 tanesi süper dünya görünümlü. Yani dünyaya benzerlikleri var ama dünyadan çok daha büyük gezegenler. 217 tanesi karasal yapıları içeren gezegenler. Üzerlerinde kara var, sadece sıvı değil. 7 tanesi hakkında da net bir bilgimiz yok. Devam ediyor. Şimdi gök adamızda biraz önce söylediğimiz gibi 250 milyar yıldız varsa, ki öyle, irili ufaklı bu yıldızları sayacak olursak 250 milyar tane. Ama hepsi bizim güneşimiz gibi olsun, kütle olarak, büyüklük olarak diye kütlesini hesaplarsak gökadanın 450 milyar tane yıldız ortaya çıkıyor. Ama gerçeği 250 milyar civarında yıldız. 250 milyar yıldızın en az bir gezegeni varsa 250 milyar gezegen yapıyor ki bu bir gezegenden fazla olabiliyor. Hiç gezegeni olmayan yıldız olabilir mi? Bu çok zayıf bir ihtimal aslında. Çünkü yıldızlar oluşurken etrafında kalıntılar bıraktığı için bu kalıntılardan mutlaka bir şeyler ortaya çıkmış olması lazım. O şeyler de bizim bildiğimiz gezegenler. Ancak şimdiye kadar dünyanın ötesinde bir yaşam olduğuna dair hiçbir kanıtımız yok. Daha kendi sistemimizdeki yaşamın detaylarını bilmiyoruz. Biraz önce Yen Hoca anlattı. Mağaralarda yaşamı araştırıyoruz bir taraftan. Türkiye'de de varmış bunlardan. Evrendeki yaşam kolayca mı başladı ve sıradan mı gerçekten? Basit bir şekilde başlayabiliyor mu? Yoksa inanılmaz derecede nadir mi? Evrende başka canlılar var mı diye direkt sorarsanız %50 ihtimalle var. %50'si biziz, kalan %50'sini bilmiyoruz. Gerçekten sıradan bir canlılık mı oradakiler yoksa biz miyiz sadece? Bunlar hep tartışılacak konular. Peki hayatı nasıl bulacağız? Yaşam kendi mahallemizde ortaya çıkabilir. Bu bizim en çok üstünde durduğumuz kısım. Belki Mars yüzeyinin altında veya Jüpiter'in uydusu Europa'nın karanlık yüzey altı okyanuslarında, Venüs'ün atmosferinde, buralarda bulunabilir. Ve buralar sizin öğrenci olarak şu andaki yaşınız itibariyle yaşayacağınız hayatın içerisinde cevabını bulabileceğimiz sorular. Çalışmalar bu kadar hızlı gidiyor. Yani siz yaşarken şu anda, çalışırken, büyürken, olgunlaşırken, bir meslek edindikten sonra para kazanırken vesaire vesaire, Mars'ta bir yaşam var mı yok mu konusu çoktan netleşmiş olacak. Jüpiter'in uydusu Europa konusunda belki bir sürü çalışmanın içerisinde var olacak araştırmacılar olabileceksiniz ya da çok yakın bir zamanda belki Venüs'ün atmosferinde mikrobik bir yaşamdan söz ediyor olabileceğiz. Bu Mars'ın yüzeyinde kumulların kaymasıyla oluşmuş bir görüntü. Ben bunların kum olarak değil de su olarak böyle yapılar oluşturduğunu söylesem rahatlıkla inanabilirsiniz. Ancak büyük bir ihtimalle Mars'ın yüzeyi altındaki suların mevsimsel erimesi sonucunda kumlara sularla beraber karışan nemin böyle bir hareket vermesi, yapı vermesi, şekil vermesi söz konusu olabilir. Bu ise Avrupa'nın yüzeyinin altında, nispeten katı yüzeyinin, buzlu yüzeyinin altında oldukça kalın bir tabaka burası. 100 kilometre civarında olduğunu zannediyorum. Bir okyanus olduğu düşünülüyor. Avrupa'nın özelliği şu, etrafındaki dev gezegenden dolayı, Jüpiter'den dolayı gelgit etkileriyle sürekli elinizin altındaki bir oyun hamuru gibi sıkıştırılıyor devamlı. Dolayısıyla oyun hamurunun bir süre sonra ısındığını hissedebilirsiniz. Avrupa'da bu şekilde ısınmış olmalı. Gelgit etkilerinden dolayı. Ve su bu sıcaklığı yakaladıysa eğer bu ısınmadan dolayı ılık bir okyanustan, tuzlu bir okyanustan bahsediyoruz. Alın size yaşam için mükemmel bir ortam. Evet, ya da belki de çağların rüyası gerçek olacak ve dünya dışı medeniyetlerin iletişimlerini dinleyebileceğiz. Çok uzun yıllardır SETI dediğimiz Search for Extraterrestrial Intelligent projesi vardı. Büyük bir radyo teleskopla ve sonra daha başka radyo teleskoplarla uzaydan, evrenden gelebilecek akıllı canlılara ilişkin doğal olmayan radyo frekanslarını dinleyebilmeyi hedefleyen bir projeydi. Bir kısmı sonuçlandı, diğer bir kısmı şu anda devam ediyor. Şu ana kadar böyle bir dinleme henüz yapamadık. Bunlar çanak antenler, çok büyük radyo teleskoplar, yani evlerimizde kullanılan çanak antenlerin yüzlerce metre, onlarca metre olanları ve üstelik bunlar birlikte hareket ettiklerinde aralarındaki uzaklık kadar tek bir çanakmış görevini görüyorlar. Biz buna interferometre diyoruz. Bu bir tekniktir fizikte ve astrofizikte. Peki hayatı nasıl bulacağız? Hatta tekno imzaların veya teknoloji izlerinin kanıtlarını bile yakalayabilme imkanımız var mı? Ancak bu şanslarımız olmazsa işimiz çok daha zor. Şu anda çalışılıyor, siz de çalışacaksınız. Geleceğinizin içerisinde hangi işi yaparsanız yapın. Şu anda ciddi birer biyolog olarak çalışacak olsanız bile kaldırım mühendisliğinden tutun mimariye kadar, psikolojiden tutun medyaya kadar gelecekte, çok yakın gelecekte, 10 yıl içerisinde belki işleriniz mutlaka uzayla ilgili bir iş olacak. Işık bir anahtar. Öte gezegenlerin atmosferlerinden gelen ışığı, çünkü olayı şöyle açıklayalım. Bir lamba var, ona yıldız diyoruz. Lambanın önünden şeffaf bir kağıt geçiriyoruz. Üzerinde bir şeyler yazılı. Ona da gezegen diyoruz. Ve arka tarafta çok uzaktan bir dürbünle bu kağıdı izliyoruz ve üzerlerindekini okuyoruz. En basit örnek bu şekilde verildi. Biz buna spektroskopik çalışma diyoruz veya tayfsal çalışma diyoruz. Biz yıldız tarafından aydınlatılan gezegen atmosferlerinin içerisindeki yapıları bilebiliyoruz. Kimyasal olarak ortaya çıkartabiliyoruz. Hangi gazlar varsa. Eser miktarda veya bol miktarda. Geçiş sayfa adını verdiğimiz bu yöntem bize yaşamla bağlantılı olanlar da dahil olmak üzere, yani örneğin bir metan gazından bahsediyoruz. Yaşamla bağlantılı bir gaz. Bu dünyaların atmosferlerindeki gazların ve kimyasalların ciddi anlamda bir menüsünü sağlayabiliyor. Ve de sağlayacak bundan sonra. Teknoloji oldukça ilerlemeye başladı. Peki bilmediğimiz hayatlar ne durumda? Ekstremofiller, bunları çok iyi bilirsiniz. Yellowstone Milli Parkı'nın yakıcı kimyasal havuzlarında yaşayabiliyorlar. Antarktika'nın kuru vadilerinde yaşayabiliyorlar. Okyanus tabanındaki aşırı ısınmış menfezlerde yaşayabiliyorlar ve milyarlarca yıl önce bizimkinden ayrılan yaşam dallarına ait olan canlılar bunlar. Yellowstone'un yapısını görüyorsunuz. Gidenleriniz varsa, gitmeyenleriniz varsa orayı bir inceleyin. Muazzam bir alan. Bunlar Antarktika'nın kuru vadilerinde ortaya çıkan ekstremofillerin kalıntıları. Bu da okyanusların altında oldukça sıcak termal bacalar dediğimiz, yani ısı bacaları dediğimiz aslında birer okyanus dibi yanardağlarının boru şeklindeki bacalarından çıkan sıcak sular ve bunların etrafında yaşayan canlılar var bol miktarda. Bunları da genel grup içerisinde ekstremofiller olarak adlandırabiliriz. Peki nereye bakmamız gerekiyor? Gökadamızda 5856'dan fazla bugün için öte gezegenin, teyit edilmiş öte gezegenin var olduğunu biliyoruz. Ancak sayıları muhtemelen milyarlarca olması gerekiyor gökadamızda. Yani etrafta gezegen olarak bol miktarda gezegen olması gerekiyor. Bilimin yaşanabilir dünyalar arayışını daraltarak araştırmamıza başlamak için sahip olduğu en iyi araçlardan birisi de yaşanabilir bölge. Neresi? Bir gezegenin etrafında, bir yıldızın etrafındaki gezegenlerin dolandığı yörüngelerde ne sıcak ne de soğuk olmayan ılık bir bölgenin olduğu yerdeki gezegenlere biz yaşanabilir bölge gezegenleri diyoruz. Bu şimdi anlattığım açıklamadan sonra burada önemli olan yaşanabilir bölgenin özelliği şu: suyu sıvı olarak tutabiliyor oradaki gezegenler. Yani ne buharlaşmış gitmiş ne de donmuş kalmış. Sıvı su varsa olaylar çok daha kolaylaşabiliyor. Ayrıca birçok başka koşul da gerekli olacak bakacağımız yerler açısından. Uygun bir atmosfere sahip uygun büyüklükte bir gezegen ve hassas yaşamı yok edici patlamalar yapmayan bir yıldızı olması lazım. Yıldızın da sakin olması gerekiyor. Çok iyi bir gezegen babası gibi. Patlayarak etrafındaki gezegenlerin atmosferlerini dağıtmaması lazım. Yaşanabilir bölge aslında sadece ilk elemeyi yapmanın ve yaşanabilir koşullara sahip olma şansını en yüksek gezegenlere odaklanmanın bir yolu. Önce yaşanabilir bölgedeki gezegenleri bulabilmemiz gerek. Bunun resmi şöyle: gördüğünüz 3 resim yukarıdan aşağı doğru. Yeşil bölgeler, yaşanabilir bölgeler. Peki neden büyük ve küçük? Çünkü maviyle gösterilen üstteki yıldız sıcak yıldızlar. Bunlar nispeten çok sıcak yıldızlar. 30 bin 40 bin derecelere kadar çıkabiliyor yüzey sıcaklıkları. O zaman yaşanabilir bölge yıldızdan daha uzaklara bir yerlere gitmesi gerekiyor. Yani buralardaki gezegenlerin yörüngeleri, yeşil bölgedeki gezegenlerin yörüngeleri yaşam için elverişli gezegenler anlamına geliyor. Hemen ortada sarı yıldızı görüyoruz. Bu bizim güneş benzeri yıldızlar. Yüzey sıcaklıkları 5800-6000 derecedir. Dolayısıyla Merkür'ü geçtik, Venüs'ü geçtik, çok sıcak. Dünyaya geldik, yaşanabilir bölgedeki bir gezegen. Nispeten Mars'ta, o da onun kıyısında, dış sınırda yer alan bir gezegen. Soğuk yıldızlarda ise yaşanabilir bölge yıldızına çok yakın. Bunlar kırmızı yıldızlar nispeten. Yani yıldız maviden kırmızıya doğru gittikçe yüzey sıcaklığı açısından soğuyan bir yıldız anlamına geliyor. Yaşanabilir bölgede her türlü yıldızın etrafında var. Ancak belki daha sonra bahsederiz, bilemiyorum. Sakin olan yıldızlar, kararlı olan, dengeli olan yıldızlar, güneş benzeri yıldızlar ya da daha soğuk yıldızlar, kırmızımsı yıldızlar. Şimdi bu sunumun özü. Bu kadar büyük bir evrende, bu resmi biraz sonra göstereceğim, küçük kırmızı resmi. Bu kadar küçük bir nokta olan Güneş sisteminde, Güneşimizin bir miktarı bir pizza dilimi olarak gösterilmiş ve etrafındaki gezegenler uygun uzaklıklarda gösterilmiş, ölçekli değil. Küçük bir gezegendeki, yani dünyamızdaki gelişmiş bir yaşam, sağdaki dünya resmimiz ve gelişmiş yaşamımızda bir çifti gösteriyor. Neden bir şekilde etrafa bulaşmış olmasın? Bizim İncelediğimiz kısım burası, araştırdığımız kısım burası, kafamızın takılmış olduğu yer burası ve bunun için bir kitap yazmaya çalışıyoruz. Bir derleme kitabımız olacak. Canlılığı arayacağımız ilk yer yine bizim mahalle olmalı. Yani Güneş sisteminden bahsediyoruz. Evren çok büyük, her şey var. karman çorman birçok şey bulunabilir, öte gezegenler de dahil. Ama önce bir etrafımıza bakmamız lazım. Bu evrenin en geniş haliyle bir simülasyonu. 2 veya 2,5 trilyon gökadanın bir kısmı burada görülüyor. Beyin hücreleri gibi sanki. Burada hiçbir yıldızı görmüyorsunuz tane tane. Hiçbir gökadayı yani galaksiyi görmüyorsunuz tane tane. Ama kümelenmiş galaksi kümelerini görüyorsunuz. Gökada kümelerini görüyorsunuz. Bu yoğun yapılar bu kümeleri veriyor. Biraz daha ilerleyecek olursak bu çok büyük evren resminin içinde bir yerlerde ben rastgele şurayı seçtim. Bir ok çıkarttım. Böyle bir çift bulunuyor. Şu anda bizi dinleyenlerden 2 kişi veya bizler. Burada bir yerlerdeyiz. Ama orada bir yerlerde ne var? Daha yakından bakıldığında orada bir yerlerde burada gördüğünüz her nokta yıldız değil. Her nokta bir gökada veya bir galaksi. Sadece ortada ışınlar saçmış, 6-7 ışın saçmış bir yıldız var. Benim görebildiğim. Bir de sol tarafta kenarda bir yıldızın ışınları var. O da şöyle, camdan dışarıya baktığınızda uzaktaki dağları seyrederken camın üzerindeki lekeler gibi bu yıldızlar. Yani biz gökadamızdan evrenin resmini çekerken kendi gökadamızın yıldızları da evrenin resminin içerisinde kalabiliyorlar. Yani yıldızlar bize çok çok yakın olan cisimler şu anda ama arkadaki gökadalar gerçek bu. Abel 2744 adını verdiğimiz Pandora gökada kümesi özel olarak söylediğim bir şey. Bunun içerisinde binlerce ve binlerce gökada var. Her gökadanın içerisinde milyarlarca ve milyarlarca yıldız, her gökadanın içerisinde milyarlarca yıldızın yanında milyarlarca gezegen var. Yani ortalık karman çorman ve kalabalık. Biz de bu gökadalardan birini şu okla gösterip sanki orada bir canlılık varmış gibi hayal edelim ve gerçekten de gökadalara baktığımız zaman cinsiz gökadalar var. Samanyolu gökadası diye yazdığımız bizim kendi gökadamız içinde 250 milyar yıldızı içeren ve 250 milyardan çok daha fazla gezegeni içeren gökada şöyle küçük bir gökada. Onun yanında Andromeda var. Onun yanında M87 gökadası var. Onun yanında IC 1101 gökadaları var. Bunlar gerçek büyüklükleri karşılaştırdığımız zaman evet, biz de bu gökadanın içerisinde bir noktada bir yerlerdeyiz. Bir çift olarak en sağda onu göstermiş durumdayım. İşte o gökadayı birazcık büyütürsek eğer bu bir çizim resmidir. Kendi gökadamızın çizim resmidir. İçinde olduğumuz için bu resmi göremiyoruz. Yani bir tabağın içerisindeki bir sıvının içerisinde tanecik gibiyiz. Tabağın gerçek şeklini göremiyoruz. Yükselebilsek bir drone gibi tabağın içerisinden tabağın gerçek yapısını göreceğiz. Ama bizim testlerimizde ve diğer benzeşimlerle, diğer gökadalardan aldığımız örneklemlerle kendi gökadamızı böyle seçebiliyoruz, çizebiliyoruz. Ve güneş dediğimiz yıldız da gözle görülemeyecek şekilde bu gökadanın sarıyla gösterilmiş okunun ucunda bir yerlerde olsa gerek. İçindeyken, tabağın içindeki bir tanecikken yani dünyanın üzerinden gökadamızı böyle görüyoruz. Biraz şekilsiz, biçimsiz bir şeymiş gibi görünüyor ama gördüğümüz parça bu bizim. En yoğun gördüğümüz parça burası. Ve işte bu güneşin bulunduğu yerde de soldaki şekilden orada bir yerde canlılar var. Samanyolu'nda büyüklü küçüklü birçok yıldızımız var. Güneşten de küçük yıldızlar var bu şekilde görüldüğü gibi. Belki bu resimde görülemiyor bile güneşten daha küçük yıldızlar. Güneşimiz büyük bir yıldızmış gibi görünüyorken en sağda ondan çok daha büyüklerinde var olduğunu biliyoruz. Binlerce kat daha büyük yıldızlar var. Her biri bir sistem oluşturabilir. Her biri gezegenleriyle beraber yaşıyor olabilir. Örneğin en büyük yıldız olan Uy Scuti sol altta ismi yazılıyor. Bunun yaşam bölgesi bundan çok çok çok çok daha uzak bir yerlerde olması gerekir etrafındaki gezegenler açısından. Güneş için ise bu çok yakındı. Peki tekrar Güneş'ten bir ok çıkartarak evet bu yıldızın etrafında bir yerde canlılık var dedik. Gelelim hemen hemen gerçek büyüklüklerde karşılaştırmalı en sağda bir dilim şeklinde Güneş. Üzerinde bir leke var, Güneş lekesi. Bunu her zaman görebilirsiniz. Özel teleskop kullanarak. Daha sonra Merkür, Venüs, Dünya Ayı ile birlikte gösterilmiş. Mars, Jüpiter, Satürn, Uranüs, Neptün. Plüto'yu göstermiyoruz. Cüce gezegenler sınırında olduğu için. Bizim yerimiz burası. Güneş sistemi. Yani bizim mahallemiz burası aslında. Buradan bir ok çıkarttığımızda şu anda evrendeki yaşamın %50'sinin olasılık olarak var olduğu kesin bildiğimiz yer bu mavi nokta. Güneş ve Dünya'yı karşılaştıracak olursak bilmiyorum görebiliyor musunuz? Bende paylaşmayı durdur yazısının altında kaldı. Güneşin sağ altında bir dünya görüntüsü var. Güneş ile Dünya'nın karşılaştırılmasında gerçek büyüklükler böyle. Dikkat ederseniz Dünya'nın büyüklüğü Güneş'in üzerindeki lekelerden daha küçük olabiliyor yeri geldiğinde. Yaşam barındıran tek gezegen bildiğimiz dünyamız, Türkiye'miz, İzmir okulunuzun olduğu yer, sizin kampüs ve bazılarınız şimdi burada bir yerde yayın yapıyorsunuz. Bu da sizin konferans salonunuz. Bir hocamızın dersi sırasında. Şimdilik ve bizce bu kadar büyük bir evrende, bu kadar küçük bir nokta olan Güneş sisteminde, küçücük bir gezegendeki gelişmiş bir yaşam, neden sistemde şöyle veya böyle bir şekilde etrafa bulaşmış olmasın ya da bize yaşam bulaşmış olmasın bir yerlerden, bizim ortam çok uygun olduğu için bizde gelişmiş olmasın. Canlılığı arayacağımız ilk yer yine bizim mahalle olabilir diye düşünüyoruz. Peki nasıl düşünmeliyiz bunu? Güneş sistemindeki yaşamımıza biraz daha detaylı bakmalıyız. Bunun için Güneş sistemini Merkür'den Neptün'e uydularıyla beraber cüce gezegenlerden asteroid kuşağı, Kuiper kuşağı, Oort bulutuna kadar bunlar çok büyük yapıların olduğu astronomik bilgilerdir. Yeri gelince kısaca açıklayacağım. Bu kuşaklardan kaynaklanan kuyruklu yıldızlar ve yıldızlar arası ortamdan gelen cisimlere kadar yapı ve yaşamla ilgilerine bakmamız gerekiyor. Yazmakta olduğumuz kitabımızda bütün bunlara ince ince değiniyoruz. Okuyucu sıkmayacak bir biçimde ama bütün bilgiyi tek bir kitabın içerisine sokuşturmaya çalışıyoruz. Güneş sisteminde yaşamın bulaşabilmesi sorusu üzerinde de düşünmek istiyoruz. Nerede ne var? Güneş çevresindeki yaşanabilir bölge biraz önce gösterdiğim resimdeki gibi böyle. Venüs, Dünya ve Mars bu yaşanabilir bölgenin içerisinde kalıyor. Venüs şu anda 430 dereceler civarında bir yüzey sıcaklığına sahip. Çok yoğun kalın bir atmosferi var ve içi şu anda bir sera etkisini yaşıyor. Yani Güneşten gelen ışınlar bu bulutu geçiyorlar, aşağıya ısıtıyorlar, yansıyorlar yüzeyden, tekrar buluttan dışarı çıkmak isterken çıkamıyorlar. Çünkü dalga boyları büyümüş oluyor. Tekrar aşağıya dönüyorlar bulutların alt yüzeylerinden. Tekrar yüzeyden yansıyorlar. Yani ışık içeride hapsolduğu için yüzey sıcaklığı çok fazla artıyor. Dünya bu anlamda mükemmel. Mars'ın da işte çok daha zayıf bir atmosferi var. Merkür için herhangi bir şey söylemiyoruz. İnceleyeceğiz. Merkür'ün özellikleri şunlar. Eksi 173 derece ile 427 derece arasında değişebiliyor. Güneşe nasıl baktığıyla alakalı bu. 88 günde bir kez kendi etrafında dönmüş oluyor. 2 Merkür yılı geçtiğinde ancak bu gerçekleşebiliyor. Atmosferi çok ince bir atmosferi var. Ancak ilginçtir. Merkür'ün Güneşi almayan kutup bölgelerindeki kraterlerin içinde hala donmuş buz şeklinde su buzunun olduğundan bahsediliyor. Su bulunursa bu bölgelere sonda göndererek ilginç sonuçlar bulabiliriz. Bu bizim tahminimiz ki bu çalışmalar yapılacak. Peki buralara yaşam bulaşmış olabilir mi? Olabilir. Tekrar geriye geleyim. Merkür'de yaşam yazısının yanındaki soru işareti bizim bu düşüncemizi içeriyor. Yani bulaşma olmuş olabilir. İzlerini bulabiliriz. Venüs'te yaşamın yanında yeşil bir tik var. 464 derece, 430 derece değişik yerlerinde. Burada yüzeyde yaşam olmayabilir. Ekstremofiller olabilir mi bilmiyoruz. Ancak Venüs'ün soldan yoğun bulutları, ortada radarla elde edilmiş yüzey görüntüsü oldukça erimiş bir volkanik alan gibi görünüyor. Sağda ise kızılötesinde bulut katmanları elde edilmiş vaziyette bir Japon uzay aracı tarafından gerçek görüntüsü. Bu bulut katmanlarının yüzeyden yukarıya doğru 60 kilometre civarında çok güzel bir sıcaklık var. Yani yaşanabilir bir sıcaklık ortamı var ve bu ortamda acaba bir yaşam gerçekleşmiş olabilir mi asılı vaziyette? Bu da bizim şüphelendiğimiz bir şey. Sizin çok iyi bilebileceğiniz fosfin maddesine burada rastlanıldı. Şu anda Venüs'le ilgili çok ciddi çalışmalar sürdürülüyor. Uzay sondaları gerçekleştirilecek. Büyük bir ihtimalle gidilip Venüs'ün atmosferi incelenecek. Orada uçan araçlar vasıtasıyla analizler yapılabilecek diye tahmin ediyorum. Yani bunun süresi çok 1-2-10 yıl içerisinde gerçekleşecek bir şeye benziyor. Venüs bu anlamda çok kıymetli. Ayda yaşam, ay daha önceden çok gri alan olarak düşünülürdü bizim için ama şimdi artık ayda yaşamak için hazırlıklar başladı. Ve oraya gidecek sondalarımız var, oraya gidebilecek astronotlar var, uzun süre kalabilecek astronotlar var. Bu hazırlıklar devam ederken ayın güney ve kuzey kutup bölgelerinde güneşi görmeyen kraterlerin içlerinde donmuş vaziyette su olduğunu düşünüyoruz. Buraya su nereden gelmiş olabilir? Büyük bir ihtimalle kuyruklu yıldızlar tarafından taşınmıştır. Kuyruklu yıldızlar kirli kar topları gibidir. Buralara çarptıkları zaman hem çukurlarını oluştururlar hem de kendi sularını oraya bırakırlar. Donmuş vaziyette. Bu çok önemli ay için. Bize çok yakın bir cisim. Su varsa bizim için yaşam ve enerji kaynağı da gerçekleşecek anlamına geliyor. Mars'ta yaşama tik koyduk. Artık Elon Musk da dahil olmak üzere herkes Mars'a gözünü dikmiş vaziyette. Sizlerin yaşadığı sürece, çalıştığınız sürece, iş hayatına sahip olduğunuz sürece bazılarınızın Mars yolculuğu yapması bile son derece mümkün hale geldi. O kadar hızlı gidiyoruz. Hemen hemen her şey var. Donmuş sular var alt tarafta. Donmuş vaziyette su buzları var Mars'ın yüzeyinin altında. Daha da aşağılarda bunun çok daha fazla olduğu ile ilgili son zamanlarda çalışmalar var. Mars elimizin içinde, bizim için çok iyi bir aday. Jüpiter'de yaşama 2 tane ünlem işareti koyduk çünkü anormal bir atmosferi var. Çok bir gaz gezegen bu aslında. Aşağıya doğru indikçe dünya büyüklüğünde falan bir çekirdeği var. Jüpiter'de yaşayalım mı diye düşünmüyoruz şimdilik. İncelenebilir mi? İncelenebilir. Ama şartları çok sert olduğu için hem Jüpiter hem Satürn ve hem diğer gaz gezegenlerin oraların kendilerinde değil de etraflarında ne var ne yok diye bakıyoruz. Belki Jüpiter'in atmosferinde Kapadokya balonlarına benzeyen, tabii aynısı değil büyük bir ihtimalle, baloncuklar içerisinde yaşam mümkün olabilir. Bilemiyoruz. Bu kuramlar var çok eskiden beri. Jüpiter'in uydularında yaşam. Avrupa'ya 3 tane yeşil tik koyduk. Avrupa bizim ilk hedeflerimizden birisi gerçekten. Oksijen açısından insanların soluyamayacağı kadar son derece ince bir atmosferi olmasına rağmen buzu çok önemli. 100 kilometrelik bir derinlik var. Avrupa'nın içindeki su miktarı dünya okyanuslarının 2 katı büyüklüğünde. Dünyanın çok büyük bir okyanusu varmış gibi düşünebilirsiniz ancak derinliği az. Oysa Avrupa'da bu derinlik çok daha fazla ve uydu neredeyse tamamen suyla kaplı, dışında bir buz tabakasıyla kaplı vaziyette. Gelgit etkileriyle ılık bir okyanus oluştuysa ve bu suyun altında yaşayan canlılar varsa bu mükemmel bir buluş olacak. Ben de bunun yakında ispatlanabileceğini düşünüyorum açıkçası. Çünkü gerçekten çok güzel teknolojik ilerlemelerimiz var. İzleyebiliyoruz birçok şeyi. Avrupa'nın yüzeyinin 3 ila 32 kilometre kalınlığında olduğu tahmin ediliyor. Bazı yerlerde çok ince. Çatlaklar, sırtlar ve bantlar yanı sıra çukurlar var, noktalar var, kubbe gibi dairesel özelliklerle kaplı. Yani dinamik olarak çok canlı bir uydu. Yaşam için bol miktarda sıvı su, enerji ve doğru kimyasal elementler Avrupa'yı dünya dışında günümüzdeki yaşamı aramak için Güneş sistemindeki en iyi yerlerden biri yapıyor. Önce Ay, sonra Mars, biraz Venüs ama esas olarak hedeflerden birisi Avrupa. Avrupa'da bulaşma varsa canlılık için çoktan uygun ortamlar oluşmuş olmalı. Özellikle canlı bir okyanus yaşamı olabilir bunun altında. Herkesin en çok durduğu ve herkesin aklına çok çabuk yatabilen bir fikir bu. Şöyle bir yapı var. İçeride katı bir çekirdek var, küçük olmak üzere. Onun dış kısmında gene taşlı kayalıklı bir manto kısmı var. Onun dışında da çok derin ve çepeçevre uyduyu saran bir okyanus var. Dışında bir buzlu kabuk var ve okyanusun bazı yerleri çok ince, gelgit etkilerinden dolayı buralardan nispeten tuzlu ve sıcak suyun buhar halinde püskürdüğünü gözleyebilmiş durumdayız. Şimdi Jüpiter'in 4 tane uydusu Galileo uyduları denir. İlk kez Galileo tarafından görülmüş, İtalyan gökbilimci. Bundan 450 yıl önce. Bu uyduların hepsi de dinamik ve çok canlı uydular. Soldaki Io, volkanik, volkanları var şu anda. Hemen yanındaki Europa, şimdi konuştuğumuz. Ganymed o kadar göz ardı edilmeyecek bir uydu değil. Burada da bir sürü şeyler bulunabilir ve Kalisto. Hepsi özellikle ekstremofiller için bir zengin ortam içeren uydular bunlar. İşte bizim hepimizin çok sevdiği milimetre boyutundaki tardigratlar, ekstremofillerin belki de kralı diyebileceğimiz bir canlı türü. Her yerde bulunabiliyor. Satürn'de yaşamı Jüpiter gibi ünlem işaretiyle gösteriyoruz. Satürn'ün ortamı bildiğimiz şekliyle yaşama elverişli değil. Gezegeni karakterize eden sıcaklıklar, basınçlar, malzemeler organizmalar için uygun değil. Satürn'ü bu anlamda geçiyoruz ama uydularını geçmeyeceğiz. Satürn böyle bir şey. Burada gördüğünüz resimdeki üst taraftaki altıgen yapı hala tam olarak dinamik olarak çözülememiş nasıl oluştuğu konusunda. Bu bir tür yapı Satürn'ün kuzey kutbunda yer alıyor. Altıgen düzgün bir altıgen gerçekten geometrik bir şekil olarak yer alıyor. Neden dairesel değil? Neden yüzeyindeki daireler çemberler gibi görünmüyor? Bilmiyoruz. Bunu biraz daha yakından görüntüsünün hareketli hali. Bunların hepsinin cevapları önümüzdeki 10 yıllar içerisinde çoktan çözülmüş olacak. Halkalarında yaşam var mı dediğimiz zaman halkalar aslında çok ince, 50 metre ile 100 metre arasında bir kalınlığı olan, çok fazla olmayan ama genişliği 250 bin kilometre civarında olan, dünyada bilinen en keskin şeylerden daha keskin oransal olarak bir yapı. Zamanında burada büyük bir ihtimalle uyduları vardı, parçalandılar vesaire. Şimdi bu halkaların şu kesitini aldığımızda kırmızı ve mavi olan yerlerde, mavi beyaz yerlerde buzlu ortamlar çok daha fazla, kırmızı trak yerlerde ise kayalık ortamların daha fazla olduğu görülüyor. Satürn uydularında yaşamda Enceladus'u dikkate alırsak, Enceladus'a da çift tik koyduk. Bu da Europa'ya benziyor, yüzeyi buzlu ama çok daha estetik, çok daha güzel bir görüntüsü var. Fışkırmalar oluyor bunda da. Bunların görüntüleri çekilebildi rahatlıkla. Bundaki fışkırmalar çok daha belirgin. Europa'da da bunların olabileceğini biliyoruz. Bunlar sanki eline bir tarak alarak yüzeyi taranmış gibi görünen bir gezegen. Bütün bu etkiyi yaratan esas olarak Satürn'ün gelgit etkisi, çekim etkisiyle bu hale gelebiliyor. İçerisinde büyüyecek bir kayalık çekirdek var. Onun dışında tıpkı diğer uydumuzda olduğu gibi bolca su oluşturan bir okyanus ve dışında da doğal olarak bir buz kabuk var. Bunun altındaki okyanusta da canlılıkla ilgili bir sürü etkinin bulunabilmesi gerekiyor. Biz bu plum veya tüycük denilen fışkırmaları kimyasal olarak inceleyerek, spektroskopik olarak da inceleyerek kimyasal yapılarını ortaya koymaya çalışıyoruz bir taraftan. Güzel sonuçlar çıkacaktır diye düşünüyoruz. Sizin bildiğiniz malzemelerden sodyum, klor, bikarbonat, iyonları, çözeltileri var. Propan ve etan gibi gazlar var. Oldukça zengin. Bu da değişik biçimlerde alınmış görüntüleri, kuzey kutbundan, güney kutbundan ve değişik açılardan alınmış görüntüleri. Yüzey oldukça dinamik ve canlı neredeyse. Titan çok ilginç. Kalın böyle bu şekilde kalın bir pus var atmosferinde. Organik bir pus diyoruz biz buna. Yüzey şekillerine girdiğimiz zaman metan göllerini görebiliyoruz. Koyu bölgeler kumullu kara parçaları, açık bölgelerde metan gölleri şeklinde. Şuralar metan gölleri bildiğimiz. Şuralarda kara parçaları şeklinde. Başka bir dalga boyunda alınmış. Atmosferi görülebiliyor ince bir şekilde. Bir başka yapısı ve birçok açılardan alınmış değişik görüntüleri. False color dediğimiz farklı renklerle farklı özellikleri işaretlediğimizde ortaya böyle görüntüler çıkıyor. En orijinal görüntüsü olmamakla beraber yüzey şekillerini belirten bölgeler. Titan da bizim için hedeflerden birisi. 55 ila 80 kilometre yüzeyden aşağı indiğimizde bunun da altında bir okyanustan, sıvı su okyanusundan bahsedebiliyoruz. Burada yaşam potansiyel olarak uygun koşullara sahip olabilir. Ekstremofiller açısından çok önemli olabilir. Dünyada bu kadar zengin bir yaşam varken, Titan'da böyle ortam sağlıyorken, Enceladus böyle ortam sağlıyorken, Europa böyle ortam sağlıyorken ve aradan da 4 milyar yıl kadar bir zaman geçmişken niye bir şekilde kuyruklu yıldızlarla, asteroidlerle, çarpışmalarla, şunlarla bunlarla yaşam veya yaşamla ilgili malzemeler etrafa bulaşmış olmasın? En çok takıldığımız nokta burası. Titan'da henüz yaşam belirtisi olmasa da karmaşık kimyası ve benzersiz ortamları onu sürekli keşifler için bir hedef haline getirecek. Biz onu hissedebiliyoruz şu anda. Bir başka iç yapı görüntüsü var burada. YouTube'dan sonra detaylı olarak inceleyebilirsiniz diye kısa bir süre tutarak görüntüyü geçiyorum. Bu çok ilginç. Chelyabinsk, Rusya'nın Sibirya'daki bir şehri. Buna geçmiş yıllarda uzaydan gelen, daha önceden bilmediğimiz bir kaya parçası, yani bir asteroid çarptı. Güçlü bir asteroidti. İşte bilmem ne kadar atom bombası gücünde falan filandı. Çarpmadan önce havada patladı. Görüntüleri alınabildi vesaire vesaire. Ama esas söylemek istediğim şey, bu çarpmadan çıkan gazlar ve tozlar atmosfere yayıldı, çarpma bölgesinde. Daha sonra dünyanın etrafını dolaşarak bu gazlar ve tozlar bizim dünyamızın atmosferinin içerisine bulaşmış oldu. Bakın bu çok önemli bir kavram. Ve bu izlenebildi. Uzay istasyonu tarafından kimyasal olarak izlenebildi. Model ve uydu verileri parlak meteor patlamasından 4 gün sonra, 4 gün içerisinde patlamanın daha hızlı, daha yüksek kısmının kırmızı olan bölgeler, Kuzey Yarımküre'nin etrafından dolaşarak tekrar Rusya'nın Çelyabinsk kentine geri döndüğünü gösterir. Yani uzaydan gelen bir kaya parçası patlıyor, çarpmadan önce patlıyor. Bunun çıkarttığı gaz ve toz kendi atmosferimizin içerisinde dağılıyor, etrafa serpişiliyor. Yani buradaki olay bir bulaşma olayı. Bunlardan binlerce, yüz binlercesi, milyonlarcası gerçekleşti. Dünya içinde gerçekleşti. Başka cisimler içinde, Güneş sistemindeki cisimler içinde gerçekleşiyor. Yani buradan yola çıkarak bu bulaşmanın ne kadar kolay olabileceğini ve asteroid ve kuyruklu yıldızların aslında birer yaşam kargoları olabileceğini de söyleyebiliriz. Bir yaşam yoksa bile, yaşamla ilgili malzemeleri taşıyorlarsa bile bunları götürüp bir yerlere yayabiliyorlar. Bu ise 12 metre çapındaki o kayadan parçalandıktan sonra geriye kalan ve gölün içerisinde, orada bir buz gölü vardı, gölün içerisine düşen kaya parçası, yani biz bunu artık göktaşı diyebiliriz, çıkartılmış ve oradaki bir müzede sergileniyor. Diğer küçük parçacıklar da var. Bir gün yolunuz düşerse bunları izleyebilirsiniz. Şimdi birkaç küçük örnek vereceğim, çok fazla değil. Diğer yaşam adayları, Satürn halkasındaki çoban uydu Pandora örneği. Uyduya baktığın zaman o onun gerçek bir görüntüsü. Kötü bir görüntüsü değil, iyi bir görüntüsü. Ama niye bulanık? Çünkü yüzeyinde bir şeyler sanki kar yağmış gibi, eskimiş de toz olmuş gibi toz şeklinde muğlak, böyle yumuşak bir görüntü oluşturmuş. Bu şunu gösteriyor. Bunun üzerine çok fazla çarpışma olmuş. Çok fazla şey bunun üzerine gelmiş, yığılmış kalmış. Yani bunun üzerinde çok fazla bulaşma var anlamına geliyor. Bu cisimlerden çok fazla var uydular arasında. Cassini bir uzay aracı, uzay sondası, bunların yanında gidip bu resimleri çeken ve uzun yıllar çalışan Satürn'ün F halkası dediğimiz bir halkada, o halkaların içerisinde A, B, C, D, E, F diye değerlendirdiğimiz halkalar var. Çoban uydu dediğimiz bu halkaların içerisinde dolaşan bir uydunun görüntüsü. Yani bu uydunun yüzeyindeki ince granüler, ince parçacıklı toz yapıları buzlu bir maddeyle kaplı olduğunu gösteriyor bu maddenin. Bunu nereden almış olabilir? Satürn uyduların halkalarından almış olabilir. Halkalardaki çarpışmalardan almış olabilir. Yani bunun yüzeyine buna ait olmayan malzeme yığılmış vaziyette. Bir başkası Telesto. Bunda da aynı şey söz konusu. Bunun yüzeyinde de aslında çok keskin bir şey görmüş olmamıza rağmen, görmemiz gerekmesine rağmen kraterler gibi keskin kenarlı falan filan, bunlar sürekli üzerine yığılan bir maddeyle, tozla, şunla bunla, su buzlarıyla vesaireyle kapanmış vaziyette. Yani sürekli bir alışveriş var. Evet, çok hızlı bitirdim. Biz kitabımızda bütün bu cisimleri tek tek inceliyoruz, yüzeysel olarak inceliyoruz. Ve umarım bu yıl bitirebiliriz ve sizlere sunabiliriz. Şimdi astronomi ile ilgili ilgilenmek ve astrobiyolog olarak çalışmaya devam ederken birazcık gökyüzünü tanımakta yarar var. Bu bizim kitabımız, TÜBİTAK Popüler Bilim Kitaplarından yayınlandı, 18. basım. Bu kitap yayınlandıktan sonra ulaştığı insan sayısı 70.000. Bir astronomi kitabından bahsediyoruz Türkiye'de ve 70.000 adet basılmış anlamına geliyor. Bundan temin edebilirseniz memnun olurum. Çok güzel şeyler öğrenirsiniz. 7.77 okuyucunun okuma gözüne ve kulağına ve diline hitap eden basit bir anlatımı vardır. Bol resimli. Ve Nisan ayında, bugünlerde çıkması lazım, hangi gün olacağını bilmiyorum. Gezegenler kitabı, bu çıktı, bu var zaten. Bunların danışmanlığını yapmıştık. Gezegenleri özellikle alınız, bu da çok önemli bir kitap. Derin uzaydan biraz bahsediyoruz, evren nasıl bir yapıya sahiptir. Ve işte Nisan ayında bugünlerde çıkması gereken bir kitabımız, bunun da danışmanlığını yaptık. Yazarları dünyaca ünlü kozmologlar, Luke ve Grain bastılar bunları. Türkçe'ye çevrildi. Türkçe metnin danışmanlığını yaptık. Öğretim üyelerinin ve özellikle öğrencilerin de okuması gereken bir kitap. Büyük patlama ile ilgili her soruyu anlaşılabilir şekilde detaylı, ince ince anlatan güzel bir kitap. Hepinize çok teşekkür ediyorum. Büyük bir ihtimalle zamanında bitirdim. Belki biraz da geçmiş olabilir. Paylaşmayı durdurayım.
Tekrardan merhabalar hocam.
Merhaba.
Değerli bilgilerinizi bizimle paylaştığınız için çok teşekkür ederiz. İsterseniz soru cevap kısmına geçebiliriz. Bayağı da bir soru
Tabii.
geldi.
Ben teşekkür ederim.
Hemen bakayım. Bir saniye. İlk sorumuz şöyle. Değerli hocam, bir dakika gitti. Değerli hocam, ben işletme okuyorum. İleride uzay alanında çalışabilmek için ne yapmalıyım?
Öncelikle İngilizce gerekiyor. Çünkü bütün kaynaklara ulaşabilmek için günümüzdeki dil İngilizce. Sizler de buradaki öğrenciler olarak zaten İngilizceyi çok iyi biliyorsunuz. Bunun yanında uzayla ilgili işletme konularına yönelebilirsiniz. Bunlardan birisi uzaydaki navigasyon, taşımacılık. Bu alanda İngiltere'de güzel okullar var, alanlar var, Amerika'da var. Ama Türkiye'de de bunlar başlıyor. Bir taraftan kitaplarını okuyabilirsiniz, araştırmalarınızı yapabilirsiniz. İleride dediğiniz şey de çok ileride değil. Zaten hemen bu işin içerisine girmiş durumdasınız. Eskisi kadar kaynaklara ulaşmak zor değil. Çok çabuk ulaşabiliyoruz. Yani şu anda siz şimdiden uzay işletmecisi olabilirsiniz. Çok geniş bir alan. Bu alanların tamamı bakir alanlar. Yani daha henüz elemanları yok doğru dürüst. Sizler ilk olacaksınız.
İnşallah hocam. Bir sonraki sorumuza geçelim. Sayın Talat hocam, ben Tunağan. Güneş sisteminde yaşam arayışında hep su bazlı hayat düşünülüyor. Sizce farklı biyokimyasal temellere dayalı yaşam olasılıkları yeterince dikkate alınıyor mu?
Alınıyor. Bunlar da olabilir. Ama su bizim için öncelikle önemli. Eskiden, çok eskiden değil. Yani bundan 15-20 yıl, 30 yıl öncesinde belki suyun bu kadar fazla olduğunu düşünmüyorduk. Hep arayış içindeydik ama şu anda evren suyla dolu. Dolayısıyla su çok önemli bir kimyasal çözücü malzeme ve suyun olduğu yerde yaşam çok daha çabuk ortaya çıkabiliyor. Farklı biyokimyasallar olabilir. Mesela Titan'daki metanlar yaşam için uygun olabilir. Bunlar da ortaya yakında çıkacaktır zannediyorum Tuna Hanım.
Teşekkür ederiz hocam.
Ben teşekkür ederim.
Merhaba Talat hocam. Evrenin en geniş haliyle simüle edilmiş resmi oluşturulurken nasıl bir yöntem kullanılıyor?
Bunun için süper bilgisayarlar kullanılıyor ve bildiğimiz bütün astrofizik prensipler, yöntemler, gözlemler hepsi bunun içerisine konuluyor. Giriş malzemesi olarak çok fazla giriş malzemesi var. Çıkış malzemesi olarak da günler süren süper bilgisayarların sonucunda, çalışmaları sonucunda bu görüntüler ortaya çıkıyor. Ancak çok daha güzel bir şey olacak yakında zannediyorum. Kuantum bilgisayarları bu çözümlemeleri çok daha net, çok daha güzel yapabilecekler. Eli kulağında yani 5 yıl içerisinde bunlar belki de ilkel görüntüler olacak. Bunların çok daha iyileri ortaya çıkacak.
Teşekkür ederiz hocam. Yani aslında bunu cevapladınız ama tekrar sorayım mı bilemedim. Hocam ben de yazılım mühendisliği okumak istiyorum. Uzay ve biyoloji alanı için neler yapabilirim mezun olunca? Biyoloji okumamı önerir misiniz? Her ikisine de ilgim var.
Kesinlikle öneririm. Ne yazık ki okullarımızda biyoloji eğitimi son derece zayıf kalıyor. Bu çok uzun süredir böyle. Ancak biyolojiyi bilmeden hiçbir şey yapabilme imkanı yok. Hele gezegenlere açılıyorken artık biyolojiyle ilgili uzmanlara büyük ihtiyaç olacak. Yazılım mühendisliği de okuyabilirsiniz. Yazılım mühendisliğini her alanda kullanabilme imkanınız var. Biraz çabuk olmanızda yarar var. Çünkü AI dediğimiz sistem çok hızlı gelişiyor. Mühendislerin onun önünde koşması gerekir. Uzay ve biyoloji alanı için neler başardık dediğinizde Birçok şeyi başardık aslında. Hiç o kadar az malzeme yok elimizde. Olabildiğince İngilizceniz varsa kaynaklara yönelerek bunları öğrenmenizi tavsiye ediyorum. Ve zaman olarak çok fazla zamanınız yok. Yani ileride kelimesi artık geçti gitti. İleride diye bir şey yok. Her şey ileride şu sırada. Siz hep ileridesiniz. Onun için çok hızlı çalışın. Öncelikle sağlığınızı korumanız lazım. Sağlıklı kalabilmeniz lazım. Ona da dikkat edin. Demek istediğimi detaylı açmayayım daha fazla. Biliyorsunuz genç olarak sağlığınızı etkileyen şeyleri
Böyle.
bir tarafa bırakmanız lazım.
Sizce şu anda hayatın oluşumu hipotezlerinden en mantıklısı hangisi? Panspermi
Sanki
yoksa abiyogenez?
panspermi mi yoksa abiyogenez mi? Olabilir. Bu ortamına bağlı ama bizim güneş sistemimiz için panspermiya biraz daha mantıklı gibi geliyor bana en azından. Bunu göreceğiz zaman içerisinde. Güneş sistemimiz için özellikle.
Tamamdır hocam. Bir sonraki sorumuza geçelim. Güneş sisteminde yaşam arayışında en çok hangi biyolojik göstergelere, biomarkerlara odaklanılıyor? Sizce bu göstergeler ne kadar güvenilirdir hocam?
Son derece güvenilir çünkü bu güneş sistemindeki yaşam arayışında veya bu alanda çalışan astrofizikçiler sadece astrofizikçi olarak çalışmıyorlar. Biyologları var, kimyagerleri var, bilgisayarcıları var, teknolojistleri var. Bunlar hep beraber çalışıyorlar. En çok hangi biyolojik gösterge derken biz şimdilik ulaşabildiğimiz gösterge olarak yaşamsal öneme sahip gazlara bakıyoruz. Yani metan her zaman için çok önemli, bol miktarda var ve diğerleri de var. Çok güzel ciddi makaleler var. Bunlara erişebilirsiniz. Bunlarla ilgili bulunan bir sürü organik madde, özellikle organik maddelerin evrende, yıldızların çevresinde, gezegenlerin çevresinde, atmosferlerinde var olduğunu görebiliyoruz. Ancak kaynaklara yoğunlaşmanız gerekiyor. Ama önemli olan gazlar.
Bir sonraki sorumuza geçelim hocam. Güneş sistemi içinde yaşam için en uygun aday sizce hangi gök cismidir ve neden?
Biraz önce söylediğim gibi Mars yeterince suyu içerdiği ve geçmişte de canlılıkla ilgili izler barındırabileceği için ki bununla ilgili birkaç elimizde kaynak var. Doğru, yani bu izlerle ilgili bir şeyler gördük. Öncelikle Mars ama benim favorim Venüs. Venüs'ün atmosferinde çok ciddi böyle bir canlılık bulabileceğimizi tahmin ediyorum. Daha sonra da Jüpiter'in ve Satürn'ün bahsettiğim uyduları. Bunlar en güçlü adaylar. Hatta Ay bile, Ay'ın üzerine İsrailler bir sonda gönderdiler. Sonda dediğimiz şey bir uydu ama uydu gittiği yerde kalıyor veya oralarda çalışıyor. Bir sonda gönderdiler. İnerken ne yazık ki düştü, parçalandı. İçinde de bol miktarda tardigrat vardı. Onlar orada şu anda canlı mı değil mi bilmiyoruz. Normal olarak canlı olmamaları lazım. Ama ya yaşama tutundularsa bir şekilde Ay'ın üzerinde. Ay şu anda canlılık barındıran en önemli cisim haline dönüştü diyebiliriz.
Hocam peki tekrar Ay'a gidildiğinde onu oradan hani numune alıp bakabilme şansları var mı?
Çok büyük alanlarda çok küçük aletlerle çalışıyoruz. Aynı yere gitme ihtimali yok. Herkes farklı farklı yerlere iniyor. Ama Ay üzerinde dolaşabilecek, araştırma yapabilecek Mars'taki gibi araçlarımız olursa, Mars'a gönderilen bir sürü araç var, hep dolaşıyorlar. O zaman bizim önceki örneklerimize gidip bakabilirler. Yani 1969'da Ay'a iniş bölgesine bile gidip orada bıraktığımız malzemelerin resimlerini yeniden çekebilirler. Ne oldu, ne bitti onlara bakabilirler. Bu mümkün. Yani ben tahmin ediyorum bunlar artık çok uzun projeler değil, çok yakın zamanda bunların hepsi gerçekleşecek gibi geliyor bana. Yani siz yapacaksınız.
Evet hocam. Bir sonraki sorumuza geçelim. Salda Gölü'nde bulunan mineral yapılar ve mikrobiyal yaşam izlerinin Mars'taki benzer jeolojik oluşumlarla benzeştiği düşünülüyor. Sizce bu benzerlikler Mars'ta geçmişte mikrobiyal yaşamın var olduğuna dair güçlü bir ipucu sayılabilir mi? Yoksa bu tür yapılar tamamen abiyotik, cansız süreçlerde oluşmuş olabilir mi?
Evet, Mars'a gönderilen bu Sagittario kraterine gönderilen sondadan önce Türkiye'deki Savda Gölü'nde inceleme yapmıştı Amerikalılar bildiğim kadarıyla. Bu konuyu gayet iyi biliyorlar. Ve Sagittario kraterinde, yani geçmişte göl olduğu düşünülen bu kraterde abiyotik yapılar görülebilir. Birçok iz buluyor olabilirler. Şu anda aslında bunların hepsini açıklayamıyorlar. Açıklamadılar da daha doğrusu. Yoğun bir şekilde orada çalışılıyor. Kişisel olarak ipucunun bulunabileceğini düşünüyorum. Kişisel fikrim bu. Güçlü
Bence de.
ipuçları bulunabilir, evet.
Güneş sistemi için, yok bunu sorulmuştu pardon.
Benzeri sorulmuştu, evet.
Aynen, benzeri sorulmuştu. Evrenin büyüklüğü göz önünde alındığında başka yaşam formlarının var olması istatistiksel olarak mantıklı görünüyor. Ancak neden hala hiçbir iz bulamadık sizce?
Peki, soruyu soran arkadaşımızın şehrini bilmiyorum. Diyelim ki Hakkari'de yaşıyor. Sabahleyin evden çıkarken ayakkabısının altında sokaktaki bakterilere bastı ve ayakkabısına bulaştı bunlar. İstanbul'da gelip de buradaki bakterilerle onu karşılaştırabilmesi için Hakkari'den İstanbul'a bir yolculuk yapması gerekir normal şartlarda. Ve ayağının altındaki bakterileri buraya taşıması gerekir. Ancak öyle görüşebilirler. Yok, bu olmazsa Hakkari ile İstanbul'u etkileyecek tek büyük bir fırtınanın olması lazım. Toz dumana karışmalı, her şey birbirine karışmalı ve bunlar birbirlerini görebilsinler, birbirleriyle buluşabilsinler. Biz de evrende böyleyiz. Güneş sisteminde değil ama evrende böyleyiz. O kadar muazzam ve büyük bir ortamdayız ki bizim birileriyle buluşabilmemiz, birileriyle haberleşebilmemiz bile çok çok çok uzun zamanlara mal olabilir. Şu anda elimizdeki en hızlı haberleşme aracı ışık hızı. Yani ışık hızında hareket eden radyo dalgaları ve radyo dalgaları dünyada keşfedildiğinde 1940'lardan sonra keşfedildiğinde, o civarda keşfedildiğinde uzaya çıktı bu dalgalar ve şu anda hala yol alıyorlar. Alabildikleri yol yaklaşık olarak 60-70 ışık yılı uzaklığa kadar gidebildiler ancak. Oysa bizim Samanyolu içerisinde, Samanyolu merkezine gidebilmemiz için 26.000 ışık yılının geçmiş olması gerekir. En yakın yıldıza gidebilmemiz için 4 ışık yılının geçmiş olması gerekir. Dolayısıyla yalnızlığımız belki de muazzam büyüklükten kaynaklanıyor. Belki de değil, tamamen öyle. Çok muazzam büyük bir şeyin içerisindeyiz. Ve etrafta bir sürü canlılık olsa bile, haberleşebileceğimiz düzeyde olsa bile yalnızlığımız devam ediyor şu anda. Bilmiyorum. Benim düşünceme göre canlılıkla ilgili sinyalleri alabilmek için bizim çok daha fazla bekleyiyor olacağımızı zannediyorum. Ama bizim bizzat kendi çalışmalarımızda başka cisimlerin üzerindeki canlılığı bulma ihtimalimiz çok daha büyük diye düşünüyorum.
Hocam kusura bakmayın, internet bir anda gitti. Tekrar geri
Evet.
geldim. Siz soruyu cevaplamıştınız değil mi? Ben çünkü sonraki soruya geçebiliriz. Şu an hala geliyor mu acaba? Şu an sesim geliyor mu?
Geliyor kesik kesik ama Arya'nın sorusu ekranda görünüyor. Bunu cevapladık mı?
Bitti.
Evet.
Tamam. Tamam, o zaman bir sonraki soruya geçelim hocam. Venüs'ün üst atmosferinde fosil gazı tespit edilmişti ve bu bazı bilim insanları tarafından yaşam belirtisi olarak yorumlandı. Sizce Venüs gibi bir gezegende yaşamın olabileceği ihtimali var mı?
Evet, atmosfer için doğru, yaşamın olabilme ihtimali çok yüksek bence. Bu da kişisel fikrim, gene araştırdığım, bildiğim kadarıyla, ama yüzey yaşamı için Mars'taki kadar konforlu olamayacağız. Merkür'de yüzey yaşamı mümkün olabilir kutuplarında. Mars'ta mümkün olabilir, Ay'da mümkün olabilir ama Venüs'ün yüzeyi son derece sıcak olduğu için canlılık açısından orada en kuvvetli, en güçlü uzay araçları bile en fazla 40 dakika boyunca çalışabiliyor. Daha sonra eriyorlar. Yani Rusların araçları böyleydi. 40 dakika sonra yok olmuşlardı eriyerek. Hal böyle olunca Venüs'ün atmosferi çok konforlu. Yani balkonda yaşar gibi Venüs'te yaşayabilmek mümkün olabilir diye düşünüyorum. Yaşam vardır diye düşünüyorum veya uygun cihazlarla, uygun sondalarla Venüs'ün civarında, atmosferde yaşam sürdürebiliriz. Ama niye? Ne için? Tabii oradan gelecek bazı malzemeler için vesaire. Sen gene dondun. Peki bekliyorum açılsın diye.
Hocam ben devam edeyim Berra gelene kadar.
Evet.
Sizce warp motoru gibi bir teknoloji mümkün müdür? Yıldızlar arası seyahatte alternatif teknolojiler var mı? Berra, ben bir sonraki soruyu okudum. Sen devam edersin sonrasında.
Tamam. Warp
Tamam.
motorundan kastedilen
Tamam, şu an-
şeyin ne olduğunu bilmiyorum ama acaba kurt deliklerinde çalışan bir motordan bahsediliyor. Soruyu soran biraz daha açarsa onu memnun olurum. Yıldızlara seyahatte alternatif teknolojiler var mı? Yıldızlara seyahat etmek için şu anda herhangi bir şey yapmak durumunda değiliz. Alternatif teknolojiler var. Örneğin çok küçük gram büyüklüğündeki bazı cisimleri çok büyük uzay yelkenlerine bağlayarak bir başka yıldıza gönderme ile ilgili projeler var şu anda. Biraz teknik oldu konuşma, anlaşılması da zor olabilir ama kısaca bundan bahsedeyim. Soru soran beni anlıyordur diye düşünüyorum. Bu tip teknolojiler var. Bir de yeni motorlar var. İyon motorları var artık. Bizim eskiden kullandığımız motorlardan farklı olarak iyonları hızla püskürterek cismi hareket ettirebilen motorlar var. Türkiye'de bu teknoloji üzerine çalışıyor. Ay'a gitme konusunda bir iyon motoru kullanacak diye biliyorum. Yeni imkanlar ortaya çıkıyor. Kim çıkartıyor bunları? Nasıl çıkartıyor? Sizler. Yani biz bunları konuştukça, öğrendikçe siz bunların çok daha iyilerini yapabilecek insanlar olacaksınız. Teknik becerileri olan insanlar olacaksınız. Bilgisi olan insanlar olacaksınız. Yıldızlara seyahat o kadar şu anda cazip değil bizim için. En yakın yıldız 4,5 ışık yılı uzaklıkta. Hiçbir cismi biz ışık yılında gönderemiyoruz. Ancak radyo dalgalarıyla gidilebiliyor. Belki moleküler transfer, yani ışınlama teknolojisi gelişirse bu da mümkün olabilir. Duyduğumuz veya bildiğimiz kadarıyla bazı molekülleri ışınlama teknolojisiyle bir yerden diğerine aktarabiliyorlarmış. Bu da çok hızlı gelişecek bir teknoloji olabilir. Ama ciddi bir teknoloji, bunu herkes ha deyince elde edemeyecek veya öğrenemeyecek. Sadece elindekilerin gücü bunu kullanmaya yetecek diye düşünüyorum.
Teşekkür ederiz hocam. Bir sonraki sorumuza geçelim. Değerli anlatımınız için çok teşekkürler. Tadrigatlar gibi ekstremofil canlıların varlığı yaşam tanımımızı evrensel boyutta yeniden düşünmemizi gerektirir mi?
Gerektirmez. Son derece ender ve özel canlılarız. İnsan olarak birçok milyonlarca canlı türüyle dünyada yaşıyoruz ama bizim bilincimiz var. Bu bizi oldukça özel kılıyor. Tardigratlar gibi ekstremofil canlıların varlığı yaşam tanımımızı, evrensel boyutları yeniden düşünmemizi gerektirmiyor. Bunların da bol miktarda bulunabileceğini düşünüyoruz. Yani biz şu anda eğer hep beraber gidip Titan'da bir kamp kurup da Titan'ı inceliyor olsaydık gerçekten inanılmaz düzeyde bilgiye ulaşabilecektik tahmin ediyorum. Ama bunu dünya sistematik olarak şu anda yapıyor. Evrensel boyutları yeniden düşünmemizi gerektirmeyecek diye düşünüyorum. Ekstremofil gibi canlıların varlığı.
Bir sonraki sorumuza geçelim hocam. Sizce Satürn'deki şeklin altıgen yapıda olmasının altıgen şeklinin en sağlam, en dayanıklı geometrik şekil olmasıyla bir ilgisi var mı? Varsa nasıl bir ilgisi var?
Bunun matematiğini bilmiyoruz açıkçası veya ben bilmiyorum, biliyorlarsa ama uğraştığımız kadarıyla, araştırdığımız veya okuduğumuz kadarıyla bununla ilgili henüz bir çıkarım sağlanamadı. Altıgen yapının bu anaforlar şeklinde, fırtınalar şeklindeki Satürn atmosferindeki hızların içinde nasıl oluştuğu konusunda gerçekten ciddi bir fikri yok. Yani fikir de yok doğru dürüst. Bununla ilgili bir yaklaşım da yok. Ama varsa benimle paylaşırsanız memnun olurum. Yani bu çok güzel bir bilmece. Öyle bir görüntüyü gördükten sonra insanlar farklı şekilde düşünmeye başlıyorlar. Hem matematikçiler hem bilgisayarcılar hem astrofizikçiler bu niye böyle diye. Benim bilgim sınırlı bu konuda.
Yani ben de ilk defa duydum böyle bir şey ama. Bir sonraki sorumuza geçelim. Son sorumuza geçelim hocam. Hocam geçiş tayf yöntemiyle öte gezegen atmosferlerini incelerken yıldız lekeleri ya da parlamaları veriyi nasıl etkiler? Bu etkileri ayırt etmek için hangi yöntemler kullanılıyor?
Bu yöntemler çok eskiden beri kullanılıyor. Yani biz tayf geçiş yöntemiyle öte gezegenleri incelemeden önce benim uzmanlık alanım çift yıldızlar dediğimiz yıldızları incelerdik. Yıldızlar birbirlerinin etrafında dönerken birbirlerinin ışığını keserlerdi ve biz bu sırada yıldızların üzerindeki bütün dinamik yapıyı, bütün mekanik yapıyı, bütün kimyasal yapıyı vesaireyi ortaya çıkarabilirdik ve hala onları yapabiliyoruz. Dolayısıyla yıldız lekeleri veya yıldızların parlamaları, yani kısa süreli parlamalarının vesairelerinin etkilerini biz doğrudan doğruya atmosferin özelliklerinden ayırabiliyoruz. Onlar birbirleriyle karışmıyorlar. Biz bunlar konusunda çok detaylı bilgilere sahibiz. Bu yöntemlerde hiçbir sıkıntı yok. Özellikle çift yıldız çalışanları için kullanılan yöntemler. Uzun uzun burada anlatma imkanlarımız yok ama biz bunları rahatlıkla ayırabiliyoruz. Bir sıkıntımız yok.
Teşekkür ederiz hocam.
Rica ederim. Görüntün dondu. Evet, olsun, zarar yok.
Maalesef internet sorunu yaşıyorum. Evet hocam, ne olur gitmeyeyim. Ahmet hocam, bugünkü konferansımızda sizleri ağırlamak bizim için çok büyük bir zevkti. Bilgi ve
Ben
tecrübelerinizi bizimle paylaştığınız için çok teşekkür ederim. Başka bir etkinliklerimizde tekrardan sizi görmek üzere. Hoşçakalın hocam.
Çok teşekkür ederim. İnşallah görüşürüz. Sağ olun. Hoşçakalın. Kolay gelsin.
Sağ olun hocam. Sevgili bilimseverler, konferansımızın ikinci oturumu sona ermiştir. Kısa bir aradan sonra Sayın Tomasz Zajkowski, NASA ve Polonya'da astrobiyoloji, uzayda ameloidleri neden çalışıyoruz başlıklı sunumuyla bizlerle birlikte olacak. Dear science lovers, the second session of our conference has ended. After a short break, Mr. Tomasz Zajkowski will be with us with his presentation titled NASA and Astrobiology in Poland. Why do we study ameloid in the space? See you guys.
Hi everyone, welcome to our session, and let me introduce myself first. My name is Merve Cihangir. I am second year biology student at Gazi University. I am an active member of MBG Turkey and Agent Astro. Since I was a child, I've been very interested in space and biology. Learning about the micro and macro world is really exciting for me. And now let's meet our speaker, Dr. Tomasz Zajkowski.
He is an astrobiologist, synthetic biologist, and science communicator. He studied biology at the University of Warsaw and did his PhD in Poland. He worked at NASA Ames Research Center in Silicon Valley. He also worked with Stanford University. His research is about amyloids, life origin, and space biology. He is now a professor in Krakow and builds the first space biology lab in Poland. He is also the president of the Polish Astrobiology Society. Let's welcome Dr. Tomasz. Hello, Dr. Tomasz. How are you today? How are you today?
Amazing. I'm very, very grateful for this invitation. Definitely being here made my day.
Yeah. Okay. Great. It's great honor to have you here. We are very excited to hear your insight and learn from your inspiring journey. And welcome. The floor is yours. You can start.
Thank you so much.
You're welcome.
So hello, everybody. I'm very grateful, as I said, for the invitation, and thank you so much for a kind introduction. I'm particularly excited about being here because I'm the president, running a similar society as you guys are participating with, and I really admire the work of organizing a conference like that. I know exactly how challenging it is, and you've been running very smoothly from what I could see so far. So I hope that we could collaborate more with the Polish Astrobiology Society, but also today I am here to tell you about my past and my current research, and also a little bit of the activities of the Polish Astrobiology Society that I would like you to invite to. Without further ado, let's start with a little description of the Polish Astrobiology Society. So a very simple website, AstroBioPL, is where you can find information about us. In the lower left corner, there's going to be a little icon where you can change the language from Polish so you can understand a little bit more. And then one of the major events that we're organizing every year is a Life in Space conference. This year is going to be our 5th edition, so very similar like your event. We run it in December. So for now, what you see is an advert from the last year. We haven't made banners for the next edition yet, but the AstroBioPL website is where you're going to find information. Subscribe on Facebook, YouTube. We have links for the channels on the main website. And I would really appreciate collaborating more with the organizers and maybe send you all the invitations if you will be okay with that at the end of the year. As I was kindly introduced, I had an opportunity to do my postdoc in Silicon Valley in California in NASA Ames Research Center, which is located here at the very bottom of the San Francisco Bay. It's a very stimulating environment, an incredible base with a lot of history, lots of wind tunnels, the biggest wind tunnel on Earth, in the pre-pressurized ones, like the one you see on the top right. The parts of the shuttles were tested, and NASA Ames is also probably the most resembling university of all NASA facilities and at headquarters that they are. So a big team of people and big team of subjects, and among them there is Lynn Rothschild. And Lynn Rothschild was my supervisor over the 6 years of my postdoc there. She is a wonderful person, and she is the only synthetic biologist running the only synthetic biology lab at NASA Ames. She pretty much introduced this field to the space research. She was the host of the first APSICON, which is astrobiology science conference run in every second year in the US. Highly recommended to go there. Also, just to make you aware that in Europe we have Beacon, which is a biannual astrobiology conference this year in Iceland. I think there's still a chance to go there. and register. Now, my major subject was amyloids and prions in early life. I will tell you more during this talk about what amyloids and prions are. And here's a list of projects that I got a little bit engaged with, so you get a better idea of what synthetic biology is. And, you know, it's an astrobiology conference, so it doesn't hurt to remind that the astrobiology is about the search for life, but it's also about the life's origin, distribution, and future, including human space travel and how we can use biology to facilitate that, to help people survive in space and thrive on other planets. So in this regard, there were tests in the biotechnology, biological technologies in the orbit. They are a part of a big consortium called Build a Cell, run by Polish. So this is the first mention of an astrobiology scientist from Poland engaged in astrobiology research. As I promised in the title, it is going to be about the NASA and Polish astrobiology. Mycotecture for Mars, which is using mycelium to build constructions, astropharmacy using cells like bacillus, but also a cell-free systems to create drugs in situ when you need them so they don't expire. Very valuable for future space missions, but as well on remote places on Earth. Biomining, so using bacteria to extract the valuable metals. Nanowires, that's one of the projects where we tackle with the nanomaterials built by microorganisms, or using synthetic parts like DNA. And then plastic from microbes, so that's metabolic engineering, and algal biofuels, that's as well heavily engineered microorganisms that can help us produce biofuels or sequester carbon dioxide, produce oxygen. All of that is a synthetic biology approach within astrobiology field. And here is another Polish person, Monika Brandacz-Lipińska, who has been paid a visit to the lab, and she worked on the mycotecture. And recently, she finished her PhD in Newcastle, where she's actually an architect. So just to mention that astrobiology is not only molecular biologists and extremophile and extremophile scientists and astronomers, but also but many other fields, including the law and, as here, architecture. Astropharmacy, just one word more about that project. One benefit of being able of synthesizing drugs on demand is that the more of instructions for how to do that, like building a plasmid, for example, testing it within the lab, this kind of information can be emailed to future Mars settlement. And that way, if they have a DNA synthesizer, they can easily produce the DNA, so we can upgrade them on the capabilities of what they can produce with the bacteria culture that they already have. So you just synthesize DNA, you acquire an email with the sequence, synthesize the DNA, maybe clone it in a plasmid, maybe not, we could even omit that, and then you have a ready to go brand new drug without any delivery from Earth. So very flexible, and something that astronauts would definitely value because it gives them more independence. And very cheerful crowd of students coming in every year. Wonderful experience, wonderful environment. I highly recommend anyone trying to get to NASA Ames. There are official internships, but there's also, with the Polish Astrobiology Society, we're trying to establish a more common ground for exchange with the specific countries, so I could help you guys with that as well. And of course, the biggest moment when we finish our space mission, like satellite-based mission, and we can see the rocket launched, because it is in California. A lot of those launches are from Vandenberg Space Center. You get to see sometimes when the time is right, the separation event, which is very spectacular over the city. And now switching gears to Polish astrobiology, I have recently joined the University of Technology in Krakow, AGH, south of Poland, close to the mountains. We have a very new building within which we are establishing the first labs in space biology and astrobiology. And we already have some achievements on a technological end. The little HYPE satellite was launched and is operational. And now, very recently, just a few weeks ago, we started a master degree program in space technologies. That's so far only for engineers, but we plan to expand it for biologists and teach more about the astrobiology itself. And we work, this slide is just to show that we work hard on establishing collaborations within the European Union. So we recently been to ASTEC, before that to DRL and the Astronaut Training Center, where already Polish representatives work, and we'll definitely continue expanding on that. And that was the first part of my presentation. Now I'm gonna switch to the main part, which is what are amyloids, what are prions, and why are they interesting from the perspective of astrobiology? Why should we study them in space and in the regard of the origin of life and many other subjects and aspects that astrobiology deals with? So here is a short list: disease, biomaterials, biofilm formation, microgravity research, origins of life, epigenetic conduits of molecular memory, which is a mouthful for just microbial prions, and biosignatures. I will go through that points right now. So let's first make you familiar a little bit more with amyloids. What are they? These are protein-based structures, which are a higher order structure. It's a higher order assembly of proteins. So here on the right, if you see an arrow, is a singular protein, one copy of a protein that then attaches to another and another and another, building this perpendicular axis of a fiber, which twists around itself and around others. Here, like cryo-electron microscopy of that. On the left side, you see that with a little bit farther out, how they look under transmission electron microscopy. An interesting thing about it is that you can design specific sequences of amino acids and build them like really stiff. And so nanotechnology within cells, and it has a lot of implications, and I will try to show you some of them. So the amyloid assembly here is going to be a short video that should show you like how a protein can misfold, and this is actually the original, based on original prion protein, which can assemble into the amyloid fibers as many other prion-like proteins can do as well. So it changed its conformation, acquired a fold which has way more beta sheet structures in it, and it has an ability to influence the folding of other copies of the same protein, forcing them to adhere to the growing fiber. And that's important, this ability of changing the shape of other copies of the proteins, because it can be at some point. There are so many short fibers broken into parts, could be millions of them within a cell. So they're so efficient in attracting other copies of the protein that are floating around it in an evolutionary intended fold and 3D structure, and then suddenly making them to refold and join this inert, inactive pretty much fiber, which leads to the loss of function of the protein very often. They interlock with the side chains of amino acids. Here, as you can see, these are like side chains 1, 3, 5, lower right corner, and they just interact so tightly that these are not even strong interactions. They could be like hydrogen bound, or there are some amyloids that can be like electrostatic or hydrophobic, but these are like super stiff, like engineered to do that. Prions, on the other hand, are a subclass which are usually bound with very weak interactions. So it's easy to break this fiber, which lets it spread more, but we'll get to that point. One interesting from my perspective, something I didn't know for a very long time, is the amyloid fiber is the lowest energy state for any protein. So you can theoretically, if you find the right conditions, you can force any protein you have, unfold it, and then fold it into a form that promotes amyloid formation. So here you have a native state, which is a very, very low. It's a classic energy landscape for protein folding. But then at some point you can misfold it into a amyloid fiber, and the protein is going to be pretty much locked in this state for a long time. That also should convey that these are not only universal, they should be pretty stable because they are the lowest energy state for them. And amyloids, you probably might have heard about amyloid diseases. These are mostly neurodegenerative, but not only, they're systemic as well. And just a short list of them: Alzheimer, Huntington, Parkinson, different dimensions, dementias, and even type 2 diabetes has the amyloid component with it, the pathology and the development of the disease. Now, amyloids can be also utilized as tools. As I said, we can devise them, we can construct them, and then we can use this like bioinformatic data set that we have and produce them in plasmids with bacteria. Then in a bioreactor, we can purify it and make a long fiber out of it. And as you can see here, it's an industrial process that could be built around that. But also, very long time ago already, people started like labeling them with gold, which made them conductive. So you can create conductive nanowires out of this biological particles. And now here is an example why biofilms are very important in space travel, let's say, because bacteria use them as a scaffold for creating extracellular matrix, which is responsible for aggregating cells together and creating biofilms, which are a big problem. On the left is a famous photo of just a clogged piece of a life support system on an International Space Center. So a water processor, which is a trouble. Like, we really need to do something about it. One of the reasons why International Space Station is soon going to be decommissioned is because it's clogged. It's like a lot of bacteria. It's many years, and it's a closed environment, and we cannot really deal with bacteria well. So NASA and ESA are really looking for ideas how to prevent. So you can either change the surfaces, or you could even target amyloids. If in one of our ideas that got funded and rewarded by the NASA Innovative Reward, NASA aims was to target biofilms to destabilize target amyloids to destabilize biofilms. And now you could also think like, okay, these are assemblies, like how the space travel, how the microgravity and other conditions in space influence the formation of the fiber itself. Because now I just mentioned a lot of disease, I just mentioned the biofouling and the biofilm formation. So now if amyloid formation, like just the physical properties of it, are influenced by microgravity, then we better know about it. And because that could be a risk for astronauts, or maybe there is less risk and we should send people with amyloid diseases to space to prolong their life. I don't know. So there was not much research. One of the most famous one is the satellite mission from JAXA, which is the Japanese space agency, and they showed that actually amyloids form a little bit slower, but also they acquire different morphologies. And we want to follow up, and we started working on amyloid assembly and simulating microgravity conditions, which is we use for that a random positioning machine. So something that moves around in different vectors, nullifying the vector of the gravity in one direction to a level of microgravity. But we also study how that assembly changes in the presence or absence of nucleic acids like DNA, which we think is going to be important. Now, another field that I'm super interested in because of amyloids is the origin of life. And the role of amyloids in the origin of life, how I see it, is that they are just right for the prebiotic enzymes. On the left side, you're going to have the modern enzymes that are very long, and they probably did not form in prebiotic conditions because they have to be at least 80 amino acid long, and we didn't see any mechanism producing any 80 amino acid long polypeptide chain that can fold and create a hydrophobic space, which is usually a catalytic center of the protein. So that's not realistic from the point of view of the origins of life. On the other end, we have very short peptides, which can be found even on meteorites, like dipeptides could be identified. But definitely on Earth, on clay, there would be catalyzed formation of peptide bonds of short peptides, and at this point the consensus is about 8 amino acid long peptides are totally realistic without biology. You don't need ribosome to synthesize them, but they're too short. They cannot fold, they cannot create the hydrophobic core. But how about they assemble into a fiber? And we know short peptides can do that, and those fibers can twist around itself and themselves. And just a few years ago, people started finding some catalytical activities of those fibers, which is fascinating because maybe they are the first step toward in the evolution of enzymes, and maybe they provided this opportunity for catalysis before the ribosome evolved, or maybe somehow they had an influence on ribosomal development, or they just assisted ribozymes, which are RNA-based enzymes. Another idea that I started looking into recently because of amyloids, and I'm still trying to find out how should we do that, but I find a lot of arguments for amyloids to be potentially stable over a long time, and they could be good biosignatures. Maybe not very old biosignatures, but maybe signatures of life on Mars if it's a contemporary still living there and producing, let's say, biofilms, which is full of amyloids. And so they're very resistant. They can survive up to 284 Celsius, which is a problem for prion diseases. And that's why we now use, one of the reasons why we use single-use chirurgical tools like scalpels, because you could otherwise transmit a infectious prion from one person to another. Now, they also are very resistant in a broad range of pH. Here is an example of a paper that shows 2 to 7, but there are a few papers showing also going up with the pH. They has also produced an incredible amount. They could be more mass of amyloids around the cells that form biofilm than the mass of the cells itself. And they are a highly evolved mechanism of exporting them, even in E. coli, which has the curly fiber operon evolved, which consists of, as you can see here, like 7 different genes that operate this secretion of amyloid forming protein. And so, yes, if we're looking for life and there is so much abundance of amyloids, that could be a good indicator that maybe life is somewhere there. And they're also universal. They're universal across many evolutionary steps and distances. So very different bacteria like Rhizobium and Staphylococcus but also in archaea. People started finding extracellular amyloids in archaea. If we think about a long-term biosignature, maybe we wouldn't be able to detect the amyloid itself, but its influence on, for example, on the formation of minerals by calcium carbonate. And here's an example of an experiment in which calcium carbonate was crystallized in the presence of a amyloid-forming protein in a monomeric state and in its amyloidogenic or amyloid state, and you can see that the crystals are strongly different. So again, amyloids maybe not themselves, but maybe their influence on crystallization of other formation of minerals. Now, amyloids as biosignatures could be a good choice because we already have some of the methods for detecting them developed. Like, for example, in the context of Alzheimer's disease, there is an antibody that is developed for amyloidogenic state of the protein. And more recently, there are some biomarkers being created, fluorescent markers for biofilm-rich media, mostly to detect biofilm. So one more argument is that amyloids, they often coexist or colocalize with the DNA and RNA for some reason. And the observations show that amyloids can protect DNA and RNA from degradation, very useful from the point of view of the origins of life, but also DNA and RNA can stimulate the formation of amyloid. So it's like a double influence. So that's why the yin and yang symbol here. And here you can see the DNA on the electron microscopy and the amyloidogenic fiber, and they're attached to each other here. Here is even being held together by little pieces of DNA. And our current research in this regard, thinking about amyloids as biosignatures, we started irradiating them to see how the space radiation could influence them. If we're supposed to look for amyloids on Mars, there's a way more radiation than we experience here. There is not much information about how amyloids behave under strong radiation. So we developed this collaboration and a list of tests that I'm not going to read, but biophysical tests that we want to study the amyloids after the irradiation. So that's one of the current research going on. And I'm probably going to finish like in 10 minutes. We started with a slight delay, so I'm going to leave the time for questions as well. And our recommendation is to study the amyloids in space-related conditions, including amyloids as biosignatures in missions like the SOLID, which is a science of life detection, which is an instrument already based on antibodies. And the antibodies for amyloids can be created, so why not implement them? And missions like BioSign, which is the next generation of the EXPOSE mission, where a piece of equipment is put outside of the International Space Station and is exposed to the conditions outside. It's of course covered. It doesn't have to be the vacuum of space. There could be simulation of different atmospheres under this little glass, and the glass can have different transparencies, so it can cut out some of the wavelengths, or creating a simulation of different worlds within the solar system, including ocean worlds. And now we reached the prion phenomenon, which I'm probably not going to have enough time to tell all the details about it, but at least I want to make prions. One important message that I have and that I would like to take for you to take home is that prions are much more than just mad cow disease. They were discovered in the context of neurodegenerative disorder. That it's correct. There was historically they were found in the Papua New Guinea tribe. That's where the first study of prion diseases began, and there was a Nobel Prize for that study. But many years later, Stanley Prusiner at San Francisco University got another Nobel Prize for explaining what caused the disease, and that the infectious agent was purely of protein matter. There was no nucleic acid involved, and it is the first and only infectious agent known to not consist of nucleic acids. And what is revolutionary about this is that we always thought that nucleic acids, DNA and RNA, are needed to convey biological information. And from this point of view, a pathogenic process is an information. The disease is a phenotype that is a response to the biological information being spread within the patient. So prions are conduits of genetic memory purely based on proteins. So it seems at first to work against the central dogma of information. We have DNA, RNA, proteins, and so on. But what if proteins can transmit information between themselves? And that's exactly what prions did. And this is the animation that you already seen, how the protein can infect other proteins to form the fiber. Here is a kinetics of this aggregation shown, so monomers on the left and then mature fiber on the right. So we have a little lag phase that can be different in some cases, shorter, longer, depending on the protein, but eventually we get a complete depletion of monomers where we have just amyloid fibers, and that's important from this perspective. And so a lot of prions form amyloids. That's two terms that I've been switching and using a lot during this talk. So I could say that prions could be sometimes considered a subclass of amyloids. And prions don't have to be bad. I will get to that. But let's start with amyloids that as well do not have to be bad. So in the human body, peptide hormones are stored on amyloid protein scaffolds. There is the melanin, the PML-EL is a protein on which melanin is scaffolded, and the PML-EL is an amyloid-forming protein which doesn't cause any disease. It actually protects us from skin cancer. Then structurally, silk and spider web are rich in amyloid content. Biofilms, useful, sticking together. Immune response, boosting up immune response. Long-term memory. If you delete an amyloid-forming fragment of any of these proteins, you're going to create a problem with the long-term memory formation in mouse, which is pretty close to human already. And now a strong distinction between functional amyloids and prions. So what I just listed were amyloids that are not necessarily bad. They're called functional amyloids, and they're usually excreted and they're functional outside of the cell. So the green color here is the functional fiber amyloid, but within the cell, this protein usually doesn't have any function. It has to be secreted, it has to aggregate, and then it has a function of, for example, sticking cells together. Now, on the right side, it's something a little bit different. Prions are actually functional proteins that can misfold into non-functional fiber within the cell. And that fiber can either kill it, or it can be transmitted to another cell where it does the same. What it does is refolds the native state of the protein that it's made of, same protein, and depleting the soluble form of that protein, making something that looks like a deletion. So the phenotype of this cell looks like you just deleted the gene that codes for that protein, which is not true because the gene is all fine. What you did is you created a heritable state of protein aggregate. So pretty interesting. Now, and opens plethora of different possibilities. Here is just to show that these little fragments of amyloids can be transmitted, to, for example, to daughter cell in yeast. And in yeast, prions are studied the best. Like we know most of the prion-like proteins, more than 20, we already know in yeast. There is just maybe 2, if you really want to classify them as one, but one is pretty strong in bacteria. And in archaea, we've been working on looking for prions in archaea, and I'll get to this point within the next few minutes. Now, we can predict the aggregation of protein because prion-like proteins, they have this little long chain that is outside of the protein, and it can easily refold into this beta sheet root structure and convey the aggregation to other. And they are rich in glutamine, asparagine, they're depleted in charge and hydrophobic residues, and that's something that you can teach AI or like machine learning algorithm to look for within a UniProt database. Now, because I did this research in California, I had to bring up the former governor of California, which is, of course, Arnold Schwarzenegger, and cite him on "I'll be back" quote, because prions, they can be lost, but they will be back. And that's one of the very characteristic things of the prions. As I said, these are native proteins, something that you already have and synthesize. And let's say in yeast, in an example of yeast, which is easier to explain, 1 in a million divisions, you get a prion form. And then they can be cured. They can be cured by us, specifically by introducing, for example, lowering activity of chaperones. I'm not going to go too much into details with that, but we can cure it. Or, for example, the protein aggregate gets so stable that it is not transmitted to the daughter cell. So the daughter cell doesn't have the aggregate that changes it into the non-functional way. And so it is again green. It comes back to the original state. The gene was not lost. So it's a mutation, a reversible mutation, phenotypically, because it's not a mutation, right? It's just coming and going. So you can cure it, but it will be back, just like Terminator. And an interesting fact is, if you overexpress this protein, first you had 1 in a million acquiring the prion state, and now you have 1 in 10,000. So it is a statistical matter and how often the protein is going to acquire that form, and that can be engineered. So you can actually build molecular switches based on protein state, not on gene activity, which is, again, opening a lot of possibilities in synthetic biology. And now the mutant, that I already told about that enough, that it looks like a mutant, but it's actually not a mutant. So yes, a heritable molecular switch is what you can call a prion. And here is an example of how that looks in real life. So this is a strain which is red mostly, and then when it switches, it gets white. And a little bit of nomenclature, small letters for prion that is not in a prion state, not heritable, and the soluble one, and then the big letters for heritable. And if you look closely, there is actually a few white dots already, because some of those cells already switched. And if you then passage them, they will be sustained for some sort of generations, and they can be cured. And within the cell, they form foci. So those aggregates are actually visible under a microscope. How does that work under the hood, like in a molecular biology? I don't have time to explain all of that, but if someone brings it up in questions, I can come back to that slide for sure. It's a mess generally, but it's a logical mess that we can use. An interesting thing is that the majority of known prions are either transmission terminators, transmission repression, chromatin remodeling, RNA binding, some things that already regulate stuff. So that's why I think about prions as a epigenetic mechanism that regulates other mechanisms of regulation, and some of them are even epigenetic. So we have an epigenetic on top of another epigenetic level, which is methylation. So pretty fascinating. And just to mention how prions can help with adaptation, let's look at the environment number one. We have cells that grow and they have no prion state within them. Some of them we require, which is not beneficial at all. But as we just said, they can change, influence other regulators. So acquiring an amyloid state can lead to change in expression of many other genes. So this cell is actually phenotypically very different from the other cells, even though genetically it's identical. So there is a little bit of spread. They divide, and then eventually the environment changes into an environment number two that is not conducive to the original population of the cells, and most of them die. But prion-like, and the cells that have the prion aggregate are so strongly changed that they actually have a chance to survive and they multiply. And in that environment, there is still a standard Darwinian evolution. There are mutations going on, and at some point there is an evolution of the cell into a form which no longer needs a prion. And the next time it encounters this environment, it's going to be perfectly comfortable with it. So this is how prions can help with the adaptation to changing environments. Short summary. Untranslated region can accumulate genetic variants. That's actually going into details. I'm going to skip for now and give you a big picture summary that prion mechanism is an epigenetic mechanism that allow adaptations, what I just said, and can integrate diverse inputs and actuate diverse outputs. Very useful in biology, can provide immediate access to genetically complex traits. And so what is prion? A prion is a transmissible assembly of proteins that you, or microbe if you want, already have. So it's nothing, it's not a living thing, it's not a virus, it's something that you already produce, but it can go bonkers and start multiplying in the form of an aggregate. And so we recently seen a shift of perspective from a very rare neurodegenerative disorders to common behavior of many proteins. And my question is, how old are prions? So we did this study that is based on the fact that a lot of prions are amyloid based. So how old are prions depends on how old are amyloids. And actually you can make an amyloid out of double phenylalanine, but you can also make this peptide that forms amyloids. And all of these amino acids were found on Bennu, which is a primordial asteroid, right? Like, so you can actually find a asteroid. So they're pretty old probably. So what I used is a top-down approach. I wanted to see if we can find any prions in archaea, and we did bioinformatic distribution of candidates using the programs that I mentioned. Then we went to the lab, we tested 16 proteins, we found 8 of them forming amyloids, and 6 of them could transmit phenotypes in yeast. I'm running out of time. I'm sorry for rushing so much right now, but I'll be happily coming back to those slides if you want. This is a first step, how we check if something has a potential to form amyloids. Then we look at them under the electron microscope. Then we do biophysical analysis of that to confirm, for example, the beta sheet reach. And now you remember the plates with red and white colonies. We do the test where we substitute a prion domain, a fragment of a protein of a known prion with the one that we're testing. And now we see that some of them can transmit the information. So we use the yeast to show that our proteins from archaea, they can actually form prion-like proteins. So what we did, we kind of fill out this dot. And then this is my one before the last slide that shows that the next follow-up bioinformatic analysis that we did, we looked at the prion candidates, we assigned functions to them based on, again, bioinformatics, and we looked of what function of prion-like proteins within different domains are conserved. And we found 84 proteins with types of functions that can be which are conserved across all three domains, and they're prions. So I mean, we have to find out if they're actual prions, but they're predicted to be prions. So this is our next step in the lab, and where we will be testing those proteins to see if they're true prions. And thank you all for listening, and thanks to my most recent team. People here are engaged in the amyloid radiation research. Thank you so much.
It was really nice presentation, Dr. Tomasz Zajkowski. Especially the pictures were very interesting. Thank you very much. And we can start to answer questions if you want. Let's take a few questions now, please. And
do you think protein?
Yeah. And amyloids. Yeah, amyloids.
Do you want to read it, or I should read it?
Oh, okay. And Zeynep, burada destek isteyeceğim İngilizce için.
Hoca dedi ki ben mi okuyayım, sen mi okursun?
I can read the question if you want.
I'm reading. Okay. Ama İngilizce çevirmem gerekecek.
Okay, so if you want, you can read your questions, and then you can answer your questions.
I'm happy
Maybe
to do
can
that.
Just
but,
wait
you
here.
know,
okay, thank you so much.
When I'm reading it, I'm getting familiar with it, so I can already think about it. All right.
Okay.
So, do you think protein structure like amyloids or prions could help organisms survive in high radiation environment like on Mars? So, this is a part of our research. We don't know yet, but I believe so. I mean, well, that's my motivation to find out. They're dense in protons. They're very tightly packed. Very good radiation protection comes, for example, from water, which just have a lot of protons around. So being a dense biological produced structure, maybe, yeah. And the fact that it associates with DNA, maybe it will protect DNA from disassemble or for like double strand breakage. This is something we want to find out. Thank you for that question.
Okay, so next questions and the second questions, please.
All right, so how soon do you think synthetic biology could be used to support life on Mars? And what are the biggest challenges right now? I think it will have to be used immediately. We need to have a circular economy. We need to somehow treat our waste. We cannot afford wasting anything. So we need bacteria to do something useful with whatever we secrete and want to waste. I think there are going to be a lot of life support system as a help for life support system. Like there's a lot of algae research for sequestering carbon dioxide that could be something helpful. But another thing that comes to my mind is like just food production, right? The drug production is something I think very promising that NASA seems to be continuously funding the research on figuring out how to produce peptide-based drugs using synthetic biology. So I think from the very first mission, there should be some parts of synthetic biology and also materials like the bioplastics, or a friend of mine was inventing something which is component similar to the Kevlar material. So another something useful that could be made with bacteria. So I hope I answered your question, like how soon. I think as soon as we go there, we should already start implementing synthetic biology.
Oh, thank you. And I can read this with your permission, and if you want. And then another questions, please. And what are the main methods used to study amyloids in space? How do these experimental approaches differ from those on Earth?
Right. So there is not much. As I mentioned during the presentation, there was one study on a satellite. It was a biophysics-based experiment from JAXA. There was a few more. There were actually 2 missions to International Space Station. These were experiments made in a facility called Cubic, which is a really ingenious and I think, if I'm not wrong, it's a facility that generated the most number of papers from International Space Station, which is pretty much a well temperature controlled incubator with a centrifuge within it. And this, what you could think, like, why would we have a centrifuge on ISS simulating 1G, which is a Earth gravity? But the thing is, when you get a difference between the centrifuge on ISS and the steady true microgravity samples on ISS, you exclude any influence of transport, shaking, temperature, and all the other things that are going on ISS. And so there were 2, but they were made by Italian Space Agency, and they were called amyloids, and they were in the context of Alzheimer's disease. So the major take-home message from those experiments was that probably due to the convection and just lack of mixing, proteins have more time to assemble into more diverse morphologies. I didn't spend much time on that during presentation, but a single protein misfolding into an amyloid fiber can do that in several ways. So from one protein, you can get more than one morphology. It was one of the first slides. You could see like 4 different strands of amyloids, but they were all made of the same protein. So that's where the information is stored. So pretty interesting that we have something going on slower. So these are biophysical. We don't know how that is going to translate into disease or application. So we clearly need more study of that sort. So thank you for that question.
Oh, okay. Thank you for the questions, Zeynep, and that was a very nice answers. And any other questions, if you want? And, okay, and asked Yasemin, can epigenetic system like prion-based inheritance have life adapt to extreme space environments?
I don't see why not, and I'd like to test it for sure. We wouldn't know until we do that. And one of the simplest experiments that come to my mind, and I think we should be all, if you're interested in it, I'm super happy to collaborate on writing a proposal for ESA. They're going to open, I think, if not yet, then maybe at the beginning of May, a new round of ESA ideas, where you can drop an idea to them and see how they evaluate it. It's not a complicated proposal. And I think one of the ideas that I had so far, how to test that, would be just to take this yeast-based strain, which is either white or red. And as I was showing on the slides, that there is a very specific number of populations of generations of the number of division of the cell, for how long the prion state can be sustained within it. So it would be interesting to see if that changes in microgravity, right? I think we should be aware of that, because now we only discovered that many, which is not much. It's a pretty new field, but it seems like a lot of proteins, probably since the origin of life, are behaving that way. So we better know how our models behave in microgravity. So I think that could be one way to test how extreme environment, which space environment is considered extreme, would help adapt cells. We don't know. Let's try. Let's find out.
Okay, and thank you. It was a very interesting questions for me. And one more questions? Another questions? Okay, and Bara asked, do you think the behavior of amyloids in space could inspire scientific biology or bioengineering, for example, for next generation biomaterials?
I have not thought about it, but yes, it is always two-way process. So making an experiment, we shouldn't make much assumption on what we will discover, right? Well, let's observe and then use that observation into the first thing that comes to my mind is crystal formation. Amyloids could be, some people sometimes call amyloids just one-dimensional crystals because they form this fiber and just goes and goes. And so it has a lot of similarities with crystal formation. And we know that some experiments showed that you can get a better, more precise crystal structure, better quality crystal structures on ISS. So maybe improving the properties that we wish the amyloids to have. And in this regard, synthetic biology and bioengineering could be improved by space conditions in some regard. But again, not much research on that end yet. So I think it's a very good field to jump in and if you're interested in basic science.
Okay, and thank you. One more questions and another or next questions. Nargis is asked, is it possible that amyloids may represent an endosymbioses like theory on some craters in space or on Earth, or is this not possible?
Right. Kind of. So they're not independent. These are proteins that a cell has to already produce, right? On the other hand, we've been looking on amyloid formation of the prebiotic peptides. Endosymbiotic, yeah. So I have this perspective. How I see it is that maybe amyloids helped with protecting RNA and then the RNA world, and there is in the RNA peptide world that evolved into the self-replicating cells. Now, protein aggregation, because a lot of them do that, must have been a problem for early cells until a good protein aggregation handling machinery evolved, like chaperones. Then later in evolution, like eukaryotes, it actually became useful. The control of the aggregation became useful and is now used for the benefit of cells, especially in higher order organisms. But sometimes when it goes wild, it can cause neurodegenerative disorders, and that's how we notice that they're even there. So in this regard, this would resemble an endosymbiosis in a way that Luca already endosymbiosed it. Before it had a ribosome, it already had aggregating proteins within. You know, it's a matter of definition, but it's definitely more resembling the virus than another organelle. So,
okay, thank you.
That's
or another
best I could answer that, but it's a very interesting question. Thank you for that.
Oh, yeah, me too. And then thank you, answers. And another or next questions? And survey asked, Mr. Zajkowski, I have two questions. First one is, what factors trigger amyloid formation in certain individuals but not others?
Shortly, mutations in the genetic sequence that codes for the protein that can misfold. And so we have I will facilitate and use the prion, the classical prion disease and the mad cow disease. The mad cow disease is one of the types. It's Creutzfeldt-Jakob disease, the full name of it. And there are infectious forms of it. There are iatrogenic, which comes through the surgery when the infectious agent is passed on the tools. And there is also a genetically inherited version. And some of them can be really quick. So they differ in the time of onset. And what we found out is the specific mutations within the gene that codes for the original prion protein. So I did briefly mention that proteins usually have this little tail, which is Q and then N reach, so glutamine and asparagine. So for example, multiplication of glutamine within a sequence is likely to trigger protein to form aggregates more often. So,
Okay, thank you, survey, for questions. And another and finally questions, I think. Please on our. Oh, okay. And then questions. And the second one is, why do structurally similar amyloid fibrils exhibit different molecular architectures?
similarly, structurally similar. So they're pretty much identical when they folded in a way they were supposed to. If I'm again helping myself with the prion protein, the original causing the disease. So it misfolds into a form that exhibit different molecular architecture, right? So it can misfold into why do structurally similar amyloid fibers? So they actually not structurally similar, right? They have different morphologies, so they actually slightly different. So it makes it a little bit hard to answer that question, but different molecular architecture. So what could be interesting for you is that, well, during misfolding, different parts of the protein can be exposed on its surface. And the surface residues are gonna be responsible for how well they attach. What is, for example, the turn rate when you have multiple of them, just like a DNA, it twists. So depending on which part of the protein got exposed and get to interact, the twist is gonna be different. The number of fibers that can be attached are gonna be different. So yeah, this kind of things.
Okay, thank you. And the one final question is, okay, you must ask, when we encounter an extracellular life form, can we assume that these protein-like molecules also have the potential to misfold and form amyloid-like structures?
Yeah, and if yes,
what? If yes, what fundamental implications does this situation offer in terms of the evolution stability and detectability of those protein life forms?
Right. So it's a very new idea to look into amyloids as biosignatures. I am trying to promote that. I'm talking to other astrobiologists. I will be on a workshop this year and talk to people that professionally look for life and ancient life. And I hope I'm going to be more educated about what are the limitations of that. But from the list of arguments that I provided during the presentation, there is a lot of them that shows that amyloids could be as old as peptides, so way before life. So if that is a physical property of peptide assemblies in the universe, and the amino acids are present even on meteorites, well, they're probably universal across different kinds of life, including the one that we call alien life, but never found any yet. So even more interesting to look for amyloid-forming proteins in any bacteria that we bring back from Mars, and hopefully it's not going to be Earth life that we brought there in the first place.
Oh, okay. Thank you, and Dr. Tomasz. And your presentations was very nice and informative. Actually, after your presentations, I will look more into studies on epigenetics, especially on amyloids. And because it caught my attention, and I will research it. And thank you. We would love to see you again and see you soon at the next events, I hope.
Absolutely.
And,
I will stay in touch. Thank you.
Yeah, now we will have a short break and friends, okay? And thank you again, Dr. Tomasz. And take care of yourself. Have a nice day. Thank you.
Okay. Hello, everyone again. Now we are moving on a truly exciting part of our program. Our next speaker is someone who brings astrobiology to life in the most literal way through the power of storytelling and film. Mike Toillon studied visual arts at the University of California, San Diego, and joined the NASA Astrobiology program in 2012. Since then, he's been telling the stories behind the science, creating compelling short films and series like Our Alien Earth, Ask an Astrobiologist, my favorite one, and the early career Spotlight series and documentaries like The Australian Outback and The Search for Life. When he's not filming astrobiologists in the film, actually, you might find him hiking the Rocky Mountains with his very photogenic English bulldog, Mochi. Today, Mike will talk about the unique connection between science and art in his presentation titled The Search for Life Begins at Home, Astrobiology Filmmaking at NASA. Mike, it's a pleasure to have you here. Yeah.
Hello, thank you so much for having me.
Thank you so much for accepting our invitation. Finally, we got you for after 4 years. So I'm so sorry for delay. We had a bit so much questions on our audience, so that's why we had a bit delay. How are you today? By the way, it's Easter.
I'm very good. Yeah, happy Easter to you.
Yeah, thank you for you too. Okay, so you can start your presentation. I can guide you. Can you see the present button there?
Yes, I'm gonna do that. I just want to make sure I can share audio too, because I have some fun stuff to share with everyone.
Yeah.
Okay, great.
You can choose both share screen and entire screen part, or also you can upload your slides with that slides and PDF part. If you want, from your computer, you can upload here.
Okay,
it's your choice.
A Keynote, is that okay?
Okay.
It's Keynote, the program? Yeah, it seems like I can only share audio if it's a tab. Okay, so yeah, how do I?
Yeah.
Let's try that.
Okay.
Let's see, video slides. Okay, here we go. Your computer. I hope this works. I'm sorry.
Yeah, I hope so.
Let's see here. And okay, let's see if this goes. Oh, not supported. Okay, we'll just I'll share it, and then maybe we just won't do sound. And
okay, so you can share your screen.
Okay.
If we need audio, maybe
I can play the sound through my microphone. Maybe that'll work.
Okay, let's try that. Yeah. Okay. Yeah, I can see your screen. Oh, yeah. Okay, I'm going. Stage is yours. Thank you.
Thank you so much. Merhaba, benim adım Mike Toillon. My colleague Tahira taught me a tiny bit of Turkish. I hope that was correct. But my name is Mike Toillon.
Yeah, it was really good. Thank you so much.
Yeah, it's my pleasure to be here. As you said, I am a filmmaker for the NASA Astrobiology program. But as a lot of people who get their start at NASA, I found my way to NASA in a very strange way. And if you guys are happy to have a little bit of fun, I was going to show a little bit of my art school path that somehow got me a job at NASA. It's a little strange, but I think everyone will enjoy it. So a little bit about me first. As you said, I live in Boulder, Colorado. I absolutely love that area. I love the Rocky Mountains, and I hike what are called 14ers quite often, which are one of the 50 different peaks in the Rocky Mountain range that are above 14,000 feet, which is about 4,200 meters. And it's just absolutely gorgeous landscape. So I really enjoy photography and getting out into nature and capturing that. And as you said, I often hike with my English bulldog Mochi, as you can see here. And just love this planet, love the diversity and of environments and creatures and wildlife, and just really enjoy being out there and capturing it and telling that story. But this all started when I went to art school at the University of California, San Diego. And I was really into music and video and making short films, and couldn't really pick what I loved the most. I kind of loved doing it all. So I really got into this idea of remixing video to make music. So I would do weird things, like I would record myself playing video games, and then I would chop up the little videos recordings into little samples, and then remix those little samples to make songs. And this is what I did in art school. So if you'll indulge me, I'll just play a little bit of it, but this is one of the things I made. This is a visual song created with Nintendo clips. And I hope you can hear this. If you can't hear it, let me know.
We can hear. Yeah.
Okay.
Welcome. Welcome. Welcome. Welcome.
Okay, I think that's enough of that. But you kind of get the idea of, just kind of using old school kind of hip hop and music and remixing video to make new art, and that was sort of my thing. And then I got really into just everything. Like I was saying, I just have a hard time picking one thing that I like. So I started getting into programming, and I thought, what if I could take this idea and rather than editing video, what if I can make a musical instrument that did this thing?
Hi, my name is Mike Toillon, and I'm here to talk about my latest art project called The Sleigh Station. The Sleigh Station is a wooden arcade cabinet that houses a software patch I've been developing that interfaces between MIDI controllers and video samples. This idea is basically combining the roles of DJ and VJ into one coherent system. So one player can both cue sounds and visuals on screen.
Yeah, so this was basically, I built an arcade cabinet out of wood, and then I put, a monitor in there and a computer, and I wrote this software to basically take a keyboard or any musical instrument, and you can assign video clips to it. So when you pushed a key, it would pop up the video, and I essentially made a new musical instrument. And then once I did that, I thought, oh, what if I formed a band of people with all these musical instruments? So I got a couple of my friends who each had their own little controller, and I gave each person a different set of video samples that I think in this clip, they're all from the anime Ghost in the Shell, if anyone's a fan. And then we all kind of played music together. I'll just skip ahead here. So that was kind of fun. And then all my friends graduated ahead of me, and the band had to break up. So I thought, what if I could automate all of the band members and actually compose all this music and do solo productions? So this is a very loud, sorry. So this is a clip of me making a song out of just video clips of lightning and electricity and things like that. So all from popular movies. You'll might recognize some scenes from The Matrix, Planet Earth documentary and The Green Mile, for example. Okay, so all that to say, how did I end up at NASA? Because even I'm a little surprised. I was doing a lot of these weird art things, and I was combining video and music and a lot of audiovisual stuff. I knew my way around projectors and signal flow and audio mixers and all this stuff. I was sort of a jack of all trades in that realm. And at the time, NASA was trying to start the Astrobiology Institute. And the idea was that rather than build an expensive new building and try to get all these people to move to NASA Ames Research Center in Mountain View, California, which is really expensive and tough cost of living, and to uproot your whole lab and create new spaces and all this stuff, what if we just sent money to current institutions and NASA centers and teams where you could stay at your home institution, do your research, and then we'll create community by just connecting virtually with video conferencing systems. So they needed someone to do all that connecting, all the audiovisual stuff, the video conferencing, and that's really why I got hired. And even though my art stuff is kind of weird and a little bit out there, it does kind of demonstrate all those capabilities. So I joined NASA Ames, and it was great. It was a dream come true. I never thought I'd be working for NASA, and I was just so happy to be there. And frankly, they could have asked me to clean toilets at NASA and I would have signed up. But not only did I get to join NASA, I got to join the NASA Astrobiology program, which is the coolest department in NASA. And it was the first time I had heard of astrobiology, and I just immediately fell in love with it. To me, astrobiology is using the scientific method to ask and answer philosophical questions, like the big questions, you know? Where do we come from? What does it mean to be alive? Are we alone in the universe? I mean, these are questions I remember in college talking with my friends about over a couple beers and just like talking into the wee hours of the night. And these were people who, this was their job. They were really trying to get to the heart of the answers to these questions. And I was just absolutely blown away by this. So I really lucked out. So yeah, I got to join NASA and then learn about astrobiology. And just real quick about this image, this is by Jenny Motar, who's a NASA graphic design artist. And she did this beautiful image for our science calendar this year, and it's all about astrobiology. And you look carefully, there's about 50 different little Easter eggs, I mean, happy Easter, right? That you can hunt down and find that are astrobiology related. We've got hydrothermal vents, stromatolites, DNA, RNA, constellations, suns, all kinds of different cool molecules and things like that, and extremophiles. But yeah, so astrobiology, to me, this was like the story. This is like the story of everything about what it means to be human. And I was really excited to try to get into that and tell that story. So the first thing I did when I joined was a program called Ask an Astrobiologist that you mentioned earlier. So thank you for that shout out. This is all about just getting people used to the word astrobiology and meeting the people behind it. You know, like my path to NASA, which was very non-traditional and strange, a lot of people get to astrobiology in a very weird way. And we wanted to show those stories about how there are so many different ways to become an astrobiologist. And so every episode we have our host, Dr. Graham Lau. We bring on a new astrobiologist, we get into their work, and we find out how they became a scientist, what sparked their curiosity, what do they work on now, and where do they see the future of this field going. And we have a Q&A with the audience, and it's all about inspiring the next generation and getting people to realize that, hey, I too can become an astrobiologist. So real quick, I'm going to play the intro to the show. This is illustrations done by a NASA intern, Melissa Flowers, and animated by myself, and also includes some original music by myself. So I'll play that now. Yeah, so that's our show. As in the upper left, this is kind of what it looks like when we broadcast. We have all these incredible guests. We try to show the diversity of everyone in the field. There's people from just all walks of life. And they all find their own interesting way that they get to astrobiology. We have, writers, oceanographers, artists, cave explorers, mathematicians, physicists. And we also do some pretty interesting episodes too. In the bottom left, this was our first ship to shore episode where we got Doctors Lauren Seiler and Armando Azul Bustos to broadcast to us live from the deck of the Falcor 2, this research expedition that they were currently on. They're in the middle of the ocean, and we got to bring people to them. They got to get a tour of the ship, ask questions, and really get to see that scientists are so much more than just people in lab coats. They're explorers, they're adventurers, they do so many cool things. And it's not just, studying indoors and, doing lab experiments and things like that, although that's also very cool. But we want to show the full part of the scientist. And along those same lines, we also like to get into what they do outside of work. And astrobiologists are just really cool people. Dr. Morgan Capel, for example, here is a mountain unicyclist in her spare time. Morgan Capel is a brilliant astrobiologist out of NASA Jet Propulsion Laboratory, does incredible work, and is just an all-around cool person. Dr. Zibby Turtle, who's the principal investigator of the upcoming Dragonfly mission, also does dragon boat racing, which you can see in the upper right there, and she's a rowing champion. And then my friend, Dr. Luke Steller, who's an Australian astrobiologist, he in his spare time, he likes doing science stand-up comedy, which is just another kind of side of science that we don't really see a lot. So we love kind of showing the full person of what makes a scientist. I'm sure a lot of you in Turkey are familiar with what I think is just an incredible person and almost celebrity at this point, Batul Kajar, a dear friend of mine. She was the second interview I did when I started making a sort of longer interview films. This is a series I started called the Early Career Spotlight Series, which are sort of up-and-coming people who are doing incredible things. And I believe I shot this in 2017, where Batul could be considered an up-and-coming star, and now she is just this incredible Harvard graduate. She runs her own lab out of the University of Wisconsin, and I just think she's an absolute superstar. So it's kind of wonderful to grow with the community and meet people and then see where their career takes them, and it's just honestly such a pleasure and a privilege. So those were some of the first things I started doing at NASA, these live web shows. Started to interview some people, but I really wanted to get into real science storytelling. For me, science storytelling is sort of equal parts education and inspiration. You need to give people information, teach them something, but you also want them to feel something and tie that back to the human experience. So for me, those are equal parts that I try to get at: information, feeling, and how do those come together to enrich and tell the full story. So I wanted to kind of tap into what are the emotions behind astrobiology? And is anyone out there familiar with the overview effect? This is a term that Frank White came up with. And the basic idea is that You know, when astronauts go into space and they see Earth from space for the first time, they all report feeling this overwhelming sense of affinity for the planet, that they see it as this beautiful blue oasis in a sea of just vacuous, cold space. And while we're here looking up, it looks like the stars are just this incredible place to be. But most people miss Earth when they leave. And when they look back at it, they don't see any borders. They don't see conflicts. They don't see race. They don't see hate. They just see our beautiful planet. And this is sort of called the overview effect. And upon returning to Earth, a lot of them, you know, have completely different outlooks on life. So I mentioned my host, the host of Ask an Astrobiologist earlier. Oop, my slides aren't advancing. Oop, there we go. Let's back it up for a second. Sorry, folks. This is Dr. Graham Lau. He's the host of Ask an Astrobiologist. And he's been thinking about this for a lot of, you know, the overview effect is so powerful, but also the idea that we might find alien life someday is going to be very, very powerful in and of itself. And even just practicing astrobiology, even before we find alien life, he reports that he feels this like abundance of awe, and it changes how he sees the world just by studying astrobiology. But it got us thinking, and he coined this incredible term, the panzoic effect. So pan meaning everywhere and zoic meaning life. It sort of means the life everywhere effect. So he's referring to this idea that when we do find alien life, will there be a similar feeling where it changes us? Will we ever look at our lives the same way again once we know for a fact we're not alone? Will this panzoic effect change the way we view ourselves and our place in the universe? And this kind of idea really gets at the heart of what I want to convey when I'm doing science storytelling. I want to tap into this possible panzoic effect, this feeling that we will be forever changed knowing our true place in the universe, or the true possibilities of what might be out there. So I just want to share that with you for a little bit. Going from art school and all these things, I never really thought it would pan out, but a part of me always wanted to be a National Geographic explorer. I would see these cool videos of these expeditions and people going out into the jungle and making films, and I just thought that would be the coolest job in the whole world. And so at NASA, I slowly started planting seeds of like, I think I could do something like this. I was at conferences and hearing people report about all this cool field work they were doing. They were going to, you know, Australia and Svalbard and the Mojave Desert and Antarctica. And I thought, man, that would be so cool. But also no one was really talking about it. You couldn't really Google astrobiology field videos. No one was really sharing that experience with everybody. And I thought, this is the coolest stuff. It's like one of the coolest disciplines, astrobiology. They're going to some of the most remote, extreme environments on the planet. And they're featuring some of the most interesting, fascinating people. So I thought, this is a story I want to tell. So I pitched to the astrobiology program, please, I'll do the whole thing. You don't have to send a film crew, just send me. I'll travel, I'll do the shooting, I'll do the interviewing, I'll do the editing, the graphics, just send me and I'll get it done, I promise. And an opportunity came up to go to Iceland, and they said yes, and I got to go. So the first episode we did was Astrobiology in the Field Iceland with Dr. Amanda Stockton. I don't know if you can see my mouse, you probably can't, but on the very right of the Jeep, who's hanging off it, that's Dr. Amanda Stockton, and this is her team from Georgia Tech. The team is called Feldspar, and we went to Iceland and drove with this Land Cruiser 6 hours south from Akureyri, and went to a place called Holarhraun, which is a pretty popular astrobiology field site. It's popular because the rock types mimic that of Mars. It's very, heavy basalt and volcanic rock, and it's an active volcanic site. So they had been studying this site for a while, and it recently had a lava flow that just eradicated all the life around it. And the idea was, if all life gets eradicated from this environment, how quickly does it repopulate with life? And we're talking about microbial life here. So there's microbes on the volcano, it erupts, lava flows down, kills everything. How quickly does it come back? And does it have implications for looking for life on other planets? So again, this land cruiser, we cross rivers and deserts and all these rocky environments, and we get to this research shack in the upper left there. There's no power, no running water. I think there's maybe a propane stove that we brought to do some cooking. And this was summer in Iceland, so the sun just sort of never sets. It's just always bright. So there were actually wooden shutters that we had to put, these we'd slot in pieces of wood to completely block out the light so we could go to sleep because it was just bright all day. And yeah, we had an absolute blast. We drove out to the site. We hiked through this volcanic sand dune environment. I mean, it really felt like being on another planet. And our favorite mountain unicyclist, Dr. Morgan Cable, was there as well. That was part of our expedition. She's in the bottom right there with me while I'm holding up my little drone camera that I had a blast using. And it was just so wonderful to tell the story. And then every expedition I go on has one really big highlight. They're all very different expeditions, but there's always some story that just stays with me. And this one was our exit. So you can see this environment here. It's mostly that volcanic sand. And during the day, it's completely dry. We just drive out on the sand. We get to the site. We pack all our gear out and we go hiking. While the scientists are sampling and doing their work, there's a glacier nearby that is just slowly starting to melt. And the place we drove in on is now slowly being flooded while we're doing our work. And they know this. So they said, at 2 p.m., we have to leave no matter what. I don't care how many samples you didn't get or if you didn't stay on schedule, we need to leave by 2 p.m. And when we do, we are driving this Land Cruiser through almost a foot of water. And I will show some video of our dramatic exit through this site. So my favorite part was I was in the passenger seat of this vehicle. Amanda Stockton is driving, and I'm flying a drone chasing our vehicle as we're going through the water. And I can't land the drone. I have to keep up. So I'm just in the passenger seat, white knuckled with the remote, flying the drone, trying to get cool shots of the Land Cruiser before we get stuck out there. And she couldn't stop the vehicle. If she stopped, we might get stuck. So she was just plowing, and it was just really exciting and adventurous, and my favorite moment from the trip. So for episode 2, I asked again, hey, can I do another one of these? And they said, sure, why not? So next I got sent to Greenland, which was fantastic. This was an expedition by Dr. Abigail Allwood, who's in the upper left here. Abby is the expert on stromatolites, if you're not familiar with her. Stromatolites are the fossilized remains of ancient microbes that leave behind these interesting structures in the rock. So, millions of years later, we can look at rocks and see the structures they left behind and know that life existed at that point in time when we date the rocks. So it's a really great indicator for a biosignature, basically, and a good indicator of past life. And Abby's famous for researching these in Australia and rocks that are about 3.45 billion years old, which kind of tells us how long it takes for a planet to go from a floating rock in space to something teeming with life. It gives us a window to look at when we go search for life. So in Greenland, another scientist thought they had found stromatolites in rocks that were 3.7 billion years old. And again, when we're thinking about the search for life on other planets, that gives us an extra 200 million years of window to look for. But you can't just go around saying, I thought I saw a stromatolite. We have to make sure these claims, the bigger the claim, the bigger the evidence we need to support it. So Abby was a little dubious, and she thought, let me get a team together. We'll fly out to Greenland and we'll go look at these rocks again. And we'll kind of find out, are these stromatolites or not? So this is my first time ever in my life I got to fly in a helicopter. So this is us landing at the field site. As you can see, there's literally nothing there. It's just rocks. There's a glacier in the background. It was a really cool environment. And this was the research shack we went up to. This red building here. It's just a one-room kind of hunting cabin. Again, no running water, no electricity, really true wilderness. And I'll never forget the feeling of flying a helicopter, being really excited, like, oh, we're going to Greenland, this is gonna be great. We land, we take all our stuff off, and the helicopter pilot says, okay, bye. And then he flies away. I remember thinking, oh, we are stuck here. Until that helicopter comes back in 3 days, we are in the middle of nowhere, completely by ourselves, and we got to get the job done. So that was really unnerving. It was also pretty cold and extremely windy. As you can see here, these are the tents we slept in. That's mine, this little orange one over here, flapping like crazy. And I remember having to wear headphones just to fall asleep because the wind was just battering my tent. And I had one of those single person coffin tents where you're basically just like a vampire trying to go to sleep, and the tent is just, you know, batting me side to side. So that was pretty intense. But it was an incredible environment. And this is the team here. In the bottom left, this is the first photo I took of myself when I came back after the 3 days in the wilderness. And you can see I look a little worse for wear. No showers, no, you know, no amenities. But my favorite story from this trip is actually in the upper left. I had brought all of these, what are called MREs, these meal ready to eat packages where you just boil water, dump it in the bag, shake it up, and then you have a meal. And I was expecting to eat like that for the whole trip. And I remember I handed them to our host and was like, oh, is there hot water for me to eat? And he goes, oh, put those away. We're not going to touch that. And he proceeds to cook us these incredible candlelit dinners every single night. So here he made some like pasta dish, and there was some smoked fish that he had brought that was from Greenland. And one night he takes out an 18-year-old bottle of scotch. And before he pours it, he says, hold on a minute. And he goes and he hikes out to the glacier with an ice pick. And he starts chipping off ice off the glacier. And he brings it back and he puts, you know, ice in all our glasses. And he starts pouring the scotch in each one. And what I didn't realize at the time was glaciers trap air when they form. And these air bubbles can be, I think, between 100, 130,000 years old. So when you pour the scotch over it, they actually start to bubble because ancient air is being released that was trapped 100,000 years ago. And it was just a surreal thing. I'm sitting in this cabin, it's cozy, there's candlelit dinner, we're watching this bubbling scotch, and I'm in the middle of nowhere, and I just thought, I have the best job in the whole world. So that's my favorite story from that. Here's some other pictures from the trip of just the absolute gorgeous and untouched environment, the glacier, the lakes, just incredible. So I just spent all the days hiking around, taking all kinds of shots. This is some of the team and some of the equipment we had to bring out. And then this is a guy from JPL in the bottom right, working with this cool project called Onsite, which is all about creating virtual field trip experiences. So he was doing some of that while we were out there. So just an absolute incredible time. So that was called Astrobiology in the Field. And NASA decided that, you know, everyone's coming out with these streaming platforms. You know, there's Netflix and Hulu and HBO Max and Disney Plus, all these things. Everyone's got an app for video. And they thought, well, what if NASA made an app for video? So we started our own streaming service called NASA Plus. And at the time, they had enough funding to make the platform, but not really enough funding to make new stuff, new content, new films and documentaries and stuff. So they started finding out who at NASA is doing documentary stuff. And they found the Astrobiology in the Field series. And I remember I got a phone call one day from the head of NASA Plus saying, hey, who's the team behind Astrobiology in the Field? And I remember thinking, like, the team is me. It's just me. And she was like, no way. So she said, I would love for this to be a NASA Plus show, but let's rework the name. Let's think about what it could be called and come back to us with a better name. And because she didn't like Astrobiology in the Field, she wanted it to be more exciting. So I took some time I met with the astrobiology program and we just started wordsmithing, like, what can we call this thing? And we ended up calling it Our Alien Earth. And I really love this name because it speaks a lot, I think, to why astrobiology matters a lot to me, which is, first of all, the word our. I mean, humans, for better or worse, are the stewards of this planet. You know, we've sort of dominated it, and we have the ability to harm it or really put our arms around it and nurture it and be caretakers for this planet. This is our home. Earth is our home. So there's some sort of ownership, and I wanted to bring the audience into it. And the show takes us to some of these most extreme environments on this planet, really strange places that you might not know, but it's still your home. So I wanted to kind of reintroduce people to, this is your planet. Welcome to your planet. Like, look at these cool environments. And for the word alien, in a lot of these environments, you know, for the NASA mission, we go to these environments because they're good analog environments for actual alien worlds. You know, Iceland is kind of like Mars. Greenland is also a little bit like Mars, or maybe the moon, or, you know, we go to the ocean because it might be like an ocean world like Europa or Enceladus. So there's an analog environment aspect to it. But also, some of these environments are so strange that to our daily lives, they appear alien. There are parts of the Earth that feel alien. So that's sort of all the meanings behind the title there. So we rebranded the show. I re-edited the first 2 episodes to fit the new theme, and it is now officially called Our Alien Earth, is the field documentary series that I have on NASA Plus now. So I'm going to show real quick a NASA Plus trailer. So you can see some of the other programs on there.
Ignition. T-minus 10. I've never been more excited about the possibility of discovery.
We are now at the point where we can bring together lots of different types of people.
You talk about grit and determination and resilience.
These are areas that humans aren't designed to go to.
We put together this amazing adventure and mission.
So when I turn it on, decisions we might make could influence other things.
And it's everything. I hope that we can do something to turn this around.
There are many questions raised by the mission that we still need to answer.
The story is never complete.
So yeah, I think this show is maybe the closest thing I have to a child right now. It started very humbly of me just sort of pitching this idea to go into the field and try to tell these stories. And now it feels like it's grown into a life of its own. So once it became Our Alien Earth, the astrobiology program fully embraced the show. And I now have funding to do a couple episodes every year. And we actually built it into our funding structure now. So when you apply for funding to the NASA astrobiology program to do field work, there's a little question at the bottom once you get accepted that says, would you want to participate in the series? And you can just say yes or no. And now my boss basically sends me a little Excel sheet with a list of all the people we fund, all the people who want to be a part of the show and where they're going. And she says, just pick where you want to go and no questions asked, go do it. So now I just I have this incredible privilege to basically go to these incredible places around the world and follow different astrobiology stories in these different locations. So the next episode I had done was Greece, where we went to a research expedition off the coast of Santorini, and it was all about using robotic explorers to explore the seafloor and these undersea volcanoes in one of the most active volcanic regions in the world. So I'll play a quick trailer for you for that.
Greece, a coastal nation steeped in ancient history and mythology. A dynamic, volatile landscape prone to earthquakes and erupting volcanoes. and for some, the perfect environment for developing new techniques to search for life on the ocean worlds of our solar system.
Yeah, so that's Our Alien Earth, Greece. Greece was another fantastic place to go to. I'd never been before, and I again just absolutely fell in love with it. It's these incredible like cliffside towns, and it's just very striking. And it was my first time being on a research expedition. I don't know if there's any if there are any oceanographers in the crowd, but I am so jealous of you, because I think people who figured out that they wanted to be oceanographers understood something way before all of us did, that this is maybe the coolest job you can have. I mean, you live and work on a floating laboratory. You get to cruise some of the most gorgeous places on Earth, and it's fun. And the ships are really nice. There's incredible mess halls and facilities. I remember they have a gym. I was using my Peloton app in the gym on a ship in the middle of nowhere, which I thought was pretty wild. And again, just so many different walks of life brought together, of people who were into robotics or programming, or they were biologists and they were interested in the samples, or geologists who were curious about the rocks and taking cores and understanding the ancient geology and the timeline of how all these environments formed. Just really fascinating stuff. And yeah, as I said, this was a robotic mission. So, and the other thing that really struck me about this episode was exploring the ocean and exploring space are so related. They have all of the same challenges and problems that, when you're trying to communicate with a rover on Mars, it's just as difficult as communicating with a robot underwater. You lose line of sight. It's hard to send signals. You have to build in a certain amount of automation so the robot can sort of think for itself, because you can't directly control it all the time. And you need to use a fleet of vehicles to really get the full picture. So as an example, when we went to Mars, the first thing we do is we maybe use a ground-based telescope to look at Mars, and we're like, oh, that's a planet, I can see it. Then we maybe use a space telescope to look a little closer. Then perhaps we send an orbiter that orbits the planet and does mapping and gets a good global picture of what's happening. The next step is we send a lander that will land on the surface of the planet and maybe have a bit of a look around. And then we'll finally send a rover, which will not only land on the planet's surface, but also explore it, and then hopefully take samples and send them back to Earth. So in this one, it was very much mimicking that process of this ship itself was sort of like that first step, where it's using sonar and these big instruments to kind of do a rudimentary mapping of the sea floor, give us that global picture. Then in the bottom right here, we have these, what they call gliders, which are these torpedo-shaped instruments that have little wings on them, and they're extremely low powered. They use less power than a cell phone, and they basically just use the current and just bob around, and they have all these sensors on them, and they do a much more detailed map of the sea floor. And because this whole expedition was to explore volcanic areas and hydrothermal activity, one of the easiest things to do is look for temperature. So the gliders would glide around, and the second they detected warmer water, they would go closer and then maybe dive a little deeper until they would find these hot spots. And then back on the ship, we have NUI, Nereid Under Ice, which is the bigger robotic explorer seen in the upper left here. And that would get deployed when the gliders detected these cool hot spots. So again, it kind of mimics that orbiter, lander, rover, where the NUI is now going to go to the quote unquote landing site that all the other data basically led us to. And then it's going to go to that site. It's got cameras, it has sampling arms, it has all this cool stuff it can do. Oop, I'm getting ahead of myself there. has all this cool stuff it can do once it gets to that location. Yeah, so that was Greece. And I don't know if you can tell from the photos here, but this is a sneak peek of an episode coming out later this year. This will be episode 4 of Our Alien Earth, and it is Hawaii, which I know, again, I got work to send me to Hawaii. Lucky me. And what we're interested in Hawaii is what are called lava tubes. Lava tubes are basically caves, but they're caves that form from the cooling of lava flows. And you can see we're actually in it right now, and there's what they call skylights. Every now and then the lava tube will have a break in the ceiling where, you know, light can come down. But in the rest of the cave, it's extremely dark. There's very little life. There's no sunlight. If you go deep enough, there might not be that much oxygen. And lo and behold, we still find life in these weird locations, that there are microbes that can live without oxygen, without photosynthesis, you know, these really strange things. And so why does this matter? We look for life on Mars quite a bit. And the problem with Mars is, while it has a lot of good ingredients for life to thrive, you know, there is ice and liquid water. It's a decent distance from its home star, our sun. It has some good characteristics there, but it's also bombarded by intense radiation. So the surface is just sort of irradiated and very inhospitable. And but Mars is also volcanically active. We can see these volcanic features from the surface, and we can see lava tubes on Mars. So perhaps life could eke out an existence inside these lava tubes where it's protected from the radiation from the surface, but it's still close enough to maybe get access to liquid water and other things that life requires. So learning more about lava tubes can help us maybe find out if that storyline is true. Here's some couple of pictures of lava tubes in these crazy cave environments. There's some people doing some sampling and analysis over here. And in the bottom left, this was an interesting group that was using ultraviolet light to kind of see if you can visually detect life forms by using different wavelengths of light. So they would kind of blast the cave in this thing and see if these brighter spots would reflect back, and if those were microbes or not. So that was pretty cool. Okay, and then finally, the sneak peek to the sneak peek is, this is the Great Kobuk Sand Dunes in Alaska, which I just got word that will be my 5th episode. So Hawaii has already been shot, and I'm just in the process of editing it. And then Alaska is our next shoot, which is going to be in this fall. So the first week of September, I'm going to be taking a plane that lands on the sand dunes, and we'll have a base camp. And they're going to be looking at these sand environments. Another similar kind of endeavor to the lava tubes, in that these sand dunes, they've noticed, so sand allows water to trickle through it. It sort of creates a gradient. But they noticed these sand dunes, there's a layer about 10, 15 meters down that is not permeable, that actually traps water. So water trickles down through the sand dunes and gets stuck and creates these sort of underground lake beds. And a similar thought is, if the surface is irradiated like on Mars, but you go down deep enough and there's these pockets of liquid water, could microbial life, again, eke out an existence there because there's some protection, but it also, there's protection from the radiation, but still has all the elements and nutrients that it needs to live. So that's another thing we'll be doing out there, going out to the sand dunes. They're going to use ground penetrating radar to detect these subsurface lakes. And then they're going to take samples and see where microbes are living and, how that all relates together. And so I'm very excited to go check that out. Also, I had no idea there were sand dunes in Alaska. So that was news to me. So this is going to be a heck of a trip. I'm really excited about it. Am I doing okay on time, by the way?
Yeah, it's okay. We have time.
Okay, great. I have a couple more things and I'll take some questions.
Okay.
Great, and I'll just go through some other projects I'm working on that I'm excited about. Again, this is another sneak peek just for y'all. This is a show that's going to debut tomorrow. Yeah, tomorrow's Monday. This is a series called Explain It Like I'm 5. And, you know, I'd done a lot of different things. I did Ask an Astrobiologist, did the Early Career Spotlight series, Our Alien Earth. And I started thinking, I've never really made a kids show before or something designed just for younger audiences. So I thought, what if we took the big NASA flagship missions, all the ones we hear about in the news, you know, Mars, the Mars rovers, OSIRIS-REx, James Webb Space Telescope, the Habitable Worlds Observatory, Dragonfly. What if we did a series that really explained these missions in very simple terms and showcased why they're important astrobiologically and in a short amount of time? So this series is about, it's all under 5 minutes. We use very simple language. There's really kind of fun animations that we put in there to make it engaging. And it's sort of for anyone 5 years old to 50 years old and beyond can enjoy it. So here's a sneak peek of the first one for OSIRIS-REx, featuring Dr. Hannah Kaplan from the OSIRIS-REx mission team.
Hi, I'm Hannah Kaplan, and I am on the OSIRIS-REx mission. I do vis near-infrared spectroscopy.
Cut. Hannah, I'm sorry. Can you explain it like I'm 5?
OSIRIS-REx went to asteroid Bennu. It is a relatively small body in space. It is rocky. It has boulders all over the surface. Some are big as cars. Lots of them are really tiny too. The materials that we're interested in on Bennu are potentially these ingredients that may have combined to form life on Earth. And so these ingredients would have been delivered with material from asteroids like Bennu and impacted onto Earth, and then ultimately been combined and formed into life as we know it. At Bennu, OSIRIS-REx orbited the asteroid. We took a bunch of pictures and a bunch of other data to get a sense of what it was like there. And then we found the place on the surface that was the smoothest, had the least big boulders so that we could get the spacecraft to the surface without crashing into anything. We then took a sample from the surface by touching down onto the surface and essentially sucking it up, which then was deposited into the spacecraft itself. And then we flew that sample back home in the spacecraft and dropped it off at Earth. And now we're studying it in the lab. One of the reasons we wanted to bring the sample back to Earth is that we have all these amazing laboratories on Earth that we can't possibly fit onto a spacecraft. So in the laboratory, we're able to look at the sample in really great detail and try and see those ingredients that we were looking for, those things that combined potentially to form life on Earth. And so we can see what exactly is in the sample that way. This will take us one step closer to unlocking where the ingredients for life on Earth may have come from.
So fun fact on that one, the voices of those kids saying that are all the children of the astrobiology program. I got them all to record their kids screaming that. So I have audio files of all these cute little kids going, explain it like I'm 5. And it's just adorable. So that's a fun new series we're working on. Some other stuff that I'm lucky enough to do. I'm always trying to, I kind of, as you can tell, always like biting off a little bit more than I can chew. And kind of, I'm always throwing myself into strange situations where I'm not fully equipped to do the task, but it keeps me on my toes and keeps me learning and growing in my skill set. So going off of that intro, the Solar System Exploration Research Virtual Institute, also known as SERVI, is a group at NASA that studies the moon and other small bodies in the solar system. They wanted to be a part of NASA's total solar eclipse broadcast last year. So they needed someone to be the telescope camera operator for the feed. And we had different, this was the biggest broadcast NASA has ever done. This is bigger than the moon landing, honestly, because they were linking dozens of sites all over the country and beyond different telescope feeds, different on-camera talent, commentary, and it was like a 5-6 hour long show. So much personnel and so much resources went into this. And the survey group said that, hey, why don't we do a broadcast from Mazatlan, Mexico? So we went down to Mexico, and we were the first site in North America that the eclipse was going to reach before everyone else. So we were sort of the star of the show. We were the first thing anyone saw. And they put on this big event locally, and they invited the public to come view and passed out all this kind of NASA stuff. And then they said, Mike, you have to do the whole eclipse broadcast. That's just your job. So I went there with my camera. I had a 400 millimeter lens. Yeah, just real quick in this picture, the upper left are just the cliff divers in Mazatlan, which I got some cool photos of. Just a gorgeous place. I absolutely fell in love with that town. And then yeah, here's some just shots of what the production was like. On the bottom left, you can see a little external monitor of the camera feed, and that's the partial eclipse starting to happen. And on the right, you can see we have a star tracker, which is what that tripod device is. That basically has a tiny camera on it that can see the sun. So it's got this big, it just tracks the white spot of the sun to make sure your camera keeps pointing in the right spot. It wasn't super accurate because we had some cloud cover, so I had to manually adjust it like almost every minute to make sure we stayed in the center. And yeah, I actually pulled off a pretty great shoot, not to toot my own horn or anything, but this is my first time ever doing this, and you cannot practice shooting a solar eclipse without shooting a solar eclipse. You cannot mimic these light conditions. So all I knew is that I wanted to keep this thing centered and then play with the like the ISO and the exposure and dial that in throughout all the different stages of the eclipse. So you can see I was able to get some of the prominences, which are these like bright purple spots coming off of the sun there. And yeah, this is sped up quite a bit, and it kind of goes real time, sped up, real time, back and forth. But you can see the clouds kind of pushing past. And it was just kind of incredible. It was so fun to experience this, and a really cool challenge, and just so glad it actually worked out. So yeah, that was the total solar eclipse of last year. And if anyone's interested, there are the Webby Awards going on right now, which are awards for different things on the internet. And NASA has been nominated for winning a Webby Award for the solar eclipse broadcast. So if anyone out there wants to go vote, go over to the Webbies, just Google Webby Awards and vote NASA, please. And then finally, just one last project I have coming up, kind of splitting the difference between a kid's show and adult show. We have this new idea called A Newbie's Guide to Astrobiology. And the idea here is, what if we sort of taught like an astrobiology 101 class? What would be the different topics? So we thought, stromatolites are a big thing that comes up a lot. Let's maybe do a full episode just about stromatolites. So our host is Tahira Allen. And the idea is that Tahira is also new to the astrobiology program, like I was so many years ago. So she's a newbie. So she's also kind of learning about this stuff. So the idea behind the show is come along with Tahira as fellow newbies, and let's learn about this stuff together. So I came up with this kind of graphic setup that kind of reminds you of like those old composition books when you go to school and you kind of doodle in them. So that's sort of the idea behind the graphics here. And yeah, I'll just show you a quick little sneak peek of this. This is very much a draft of this show. This would maybe be next year, but this is sort of what we're kicking around.
G'day, newbies! I'm Tahira Allen, and today we're here in Western Australia with NASA to look at some of the most important rock formations for the origin of life on Earth and the search for life on Mars.
Yeah, like I said, very, very sneak peek. That's basically all I have, but I would love to take some questions. And finally, I'd just like to say thank you. And çok Teşekkür ederim. Thank you.
We are really thankful. And for your Turkish also, we are really thankful. It was really amazing presentation, and I had really fun. So also, by the way, we invited Dr. Gramlo last year or 2 years ago. And also Dr. Armando Azobustos was our guest in our first conference. Yeah.
Isn't he great? I love him.
Yeah. One of my favorite show is Ask an Astrobiyology. It's always like that. I really love it.
Oh, thank you. We'll have to have you on sometime.
So I will start to ask questions if you have time.
I love that. Yeah.
Okay, so okay. Cheval asked, your presentation was great. Can you tell me which program you used?
Like for the slides? Yeah, it's just a Keynote. I use Keynote.
Yeah. Okay. Actually, before you start, you thought that. Yeah. How do you balance scientific accuracy with engaging storytelling in your astrobiology documentaries?
It's a great question. Yeah, for me, it's not that hard because astrobiology is so cool that I don't have to hype it up, or I don't have to stray from the science to tell a good story. So the science is always the most important thing. And when I go on expeditions as well, I'm a guest of the expedition, and they're there to do a job. And that's always the forefront of my mind is don't get in the way of the science. So I always try to be very respectful, and I always check with them. Hey, is it okay if I get in here? If I get this angle, can I do this? Or hey, can you do that little move again? That looked really cool. So I'm always letting they're the priority is what I'm saying. And as far as things that are sort of inaccurate, it's only like tiny little details. Like for example, in Greenland, I flew on the helicopter to go to the site, but it would be cool to show the helicopter. So when the next group came, I filmed the helicopter landing and then edited together to make it look like that was the helicopter we were on. So like little things like that, which is just like, it's not like, it doesn't ruin the accuracy, but there's little film tricks like that I'll use. But for the most part, 100% accurate. We never want to fudge the science itself. Yeah.
Yeah. Well, your job requires so much effort also. I really like it. It's cool.
Thank you. Yeah.
What challenges have you faced in translating complex astrobiological concepts into visual narratives for a general audience?
Yeah, this is probably the hardest part of my job. And so what was good when I first started was I also didn't really know this stuff. So it was almost like if by the end of the video I understand it, then maybe you'll understand it because I also don't know what I'm doing. But now I know a pretty good amount of astrobiology. So yeah, what's some of the biggest stuff? I think what's hard to understand is just how big a field it is, that there's so many aspects of this stuff, and that there's still a lot of unknowns. We don't know a lot of, we can't draw a line from our planet being born to life. There are lots of gaps. We don't know what came first. We don't know what sparked what. So how do you convey the idea that this is an ongoing science and we don't have all the answers, but we still have a pretty good idea of things? And it's sort of, I think another way to say it is the idea of what makes scientific theory a theory, and how does that relate to facts, and how are things, they're always, any discovery can be built upon and changed. So trying to tell the audience that this is what we know so far, and when new information comes in, we'll build on that. But a lot of people want to say like, oh, then you don't know what you're talking about. You don't have all the answers. And it's like, well, that's what science is. Science is admitting what you don't know and then building on that. And I think that's a tough thing to translate to an audience, of the actual scientific process itself. Like Greenland was a good example of, we didn't go there to discover something. We went there to sort of debunk something. And the spoiler alert, the end of the episode is they're not really stromatolites. And that's not a very exciting thing, right? To be like, oh, the end of the movie is, it's not real. It's not true. But that's important to the scientific process, right? You have to always validate your claims. And we're talking about the search for life. I mean, there's no bigger claim to make. So when people talk about things, when, like, for example, in the news recently, there was a detection of DMS on an exoplanet, and some of the headlines saying we found life, and it's like no.
Yeah.
You have to be careful about that. So that's another challenge as well. How do you showcase these exciting discoveries, but temper the audience expectations to say it doesn't mean aliens, but it's a step towards finding out that truth. So I hope that answers your question.
Thank you. Okay, so how does knowing during filming that scientists' theories could be disproven in the future affect the narrative? Actually, you also answered this. How do you present information that may become outdated over time?
Yeah, I think we touched on that a little bit in the last question, but yeah, absolutely. I think it's just always being honest, that everything is sort of a time capsule, and just when something changes, we make a story about that, and we tell that story. And it's not about that we were wrong before, it's just that was the best answer we had at the time, and showing that process I think is really important. I don't want to delete that and pretend that never happened. I think that's also a part of the story, and it's important that it doesn't make that work unimportant. It's just a earlier part of the story. Yeah.
Okay. So how does a documentary's perspective affect the viewer's approach to scientific issues? Do you think it will be more effective if the narrator were neutral, or if he or she established an emotional connection, which is more important to the audience?
It's really interesting. Well, I am the narrator of Our Alien Earth, and I will say I do form an emotional connection to the work. So that's been my path. I think it brings the audience in. I think that's why we love famous documentarians like David Attenborough. He evokes emotion. He brings you along with it. He makes the story beautiful. It's not just here's some cool animals, but he really brings you in and ties it back to the human experience. And again, that's why I love astrobiology. It's not just a science to me. It's a scientific approach to a very human experience, and a very life-based experience. So for me, it's inherently emotional. But again, it's not emotion while sacrificing the scientific accuracy or anything. I think the emotion heightens the importance of the science. So that's what I strive to do.
Okay. In your experience, how does visual media influence public perception and understanding of astrobiology and the search for extraterrestrial life?
Yeah, well, my goal is to help educate the audience in a way and bring them in. And if we don't do that work, someone else will. And there's billions of videos on YouTube about, UFOs and misinformation around this topic. So rather than spend our time pointing at all the things that are wrong, I think what we should do is just make our own media about what is correct, what we know, and share that as widely as possible. And for NASA especially, we're publicly funded. Everything NASA does is from the taxpayers of the United States of America. So it's a responsibility too to show the public, hey, this is what your money's being spent on. These are the cool discoveries we've made. These are the cool technologies that have been developed because of space missions, and it's all thanks to you. And this is your money in action. So there's a bit of responsibility there as well. So yeah, I would hope that my work in the future is just helps people learn more about astrobiology, get excited about it, and also maybe want to get involved in the field. And I hope I do get some lovely messages from time to time of so-and-so saw an episode of Ask an Astrobiologist and changed their major, and now they're going to college and studying science. And that always warms my heart, because I do think it's an incredible science. And there's so many ways to get into it. Yeah. Even if you're an artist, you can be an astrobiology graphic artist. Or, even for me, I was making weird beats about video games, and I'm now going around the world doing this crazy stuff. So it doesn't matter where you came from. There's a place for you in astrobiology. I think that's really cool.
Yeah. Yeah. Okay. So first of all, your presentation was really heartwarming and interesting. I had a lot of fun. Do you think a full frame movie can be shot in space in the future? Yeah.
I hope so. Really also, sign me up. I would love to do that. I think absolutely. I think our plans are to continue going into space. The Artemis program wants to establish a new space station. They also want to establish a presence on the moon. And I think it would be great to have a full frame movie on the moon or something. I think would be wonderful.
Okay. Actually, this is not for you, but okay, I will ask. Our presentation, I think she wants to say your presentation really made me laugh a lot. It was so much fun. What path should we as young people follow to become astrobiologists? What do you recommend for these?
Yeah. So our website does have a wonderful resource on this. If you just Google career paths, NASA astrobiology.
Astrobiology,
yeah, there's a lovely infographic. Basically, you just want to pick a science. And then once you start getting towards the end of your degree, just start gravitating and taking some extracurricular stuff that's whatever science you picked plus space. So you can get into space geology, space physics, space chemistry, space biology, and then find people you like and admire and join their labs. I just found a nice comment on that, the video with Batul Kajar, someone that just really resonated with her, and they purposefully went to the University of Wisconsin just to study underneath her. So that's basically what you do. The other part of that is astrobiologists are very friendly people. And that's also why I love this field. It's some of the best community I've ever seen of, they don't have huge egos. They're very available. So if you find someone's work that you like, reach out to them, send them an email. They'll happily give you a suggestion. And I would follow your dreams in that way. And another good piece of advice I've always got is from other people is, it's not so much what you like, oh, I'm really into rocks, or I'm really into microbes or whatever, but it's more about finding your question. What's the question that you want an answer to that really drives you? And then pick a science around that. What's that question that really is in you? Is it about how did a cell become a cell? Is it, is it extreme environments? Is it the origin of life? Is it life on other planets? Find your question, and then it should all kind of trickle down from there.
Yeah, okay, thank you. Last question. Thank you for this exciting presentation. Your job is very funny and exciting for me. Was there any crash out time for you, or did you ever feel bored so much when doing a specific job?
I think that's what made me pitch so hard to go into the field, because I told you I got hired to do video conferencing and stuff like that. So I was in an office a lot, just connecting things. And, I used to wear a tie to work, believe it or not. When I saw field work in astrobiology, I just thought, okay, that's it for me. I need to figure out a way to do this. So that's what really spawned that. But burnout does happen, even in the stuff you love. Sometimes I'll be sitting, editing day after day, and I just can't find the joy in it anymore. So sometimes I'll do a personal project. So there was one time, it was when I was working on the third episode, the Girish episode, I was just in a bad mood. I just couldn't find the creative juices. So I went through all the old photos and videos of my bulldog Mochi, and I made a 1-minute short movie about my dog. And I did a voiceover because I was also getting in my head about recording my own voice. So I was trying to practice that. So I just made a little short film about my dog, and it's on her little Instagram page now. And I show that to people when I'm just if you get stuck, just put that stuff on hold, go for a walk, or just pivot and make something just for you. And then when I came back to the project, I was kind of ready to go again, and that felt good.
Yeah. Okay. Thank you for your kind answers also. And I hope to see you in Turkey, by the way. We have so many caves and so many lakes. I hope maybe one day you can film about our alien Earth, Turkey. I hope.
I cannot wait for that to come across my desk. If I see the word Turkey on that sheet from my boss, I will top my list for sure.
Yeah, thank you so much for attending us today. So
my pleasure.
I'm really honored to have you here. Bye-bye.
Thank you. Bye, everybody.
Bye. Okay, so we will have a short break, 1 minute or less. So after that, we will continue with Professor Ulrich Muller, and see you guys. Bye-bye. And now, for our final session of the evening, we are honored to welcome a scientist whose work brings us closer to understanding the very origin of the life. Professor Ulrich Muller, or Ulay, as he is known to many, grew up in Germany and studied chemistry at the Ludwig Maximilians University of Munich. After earning his PhD from the Munich Gene Center, Max Planck Institute, and the Darmstadt University of Technology, he went on to do postdoctoral research at the Whitehead Institute, MIT in Boston. In 2006, he joined the faculty at the University of California, San Diego, where his research focused on the directed evolution of catalytic RNAs, also known as ribosomes. His main goal to understand how early RNA world could have supported the life before DNA and proteins evolved. Today, Professor Muller will be presenting two fascinating projects. One is exploring the early stage of an RNA world with primitive catalyst, and the other one will be focused on a more mature RNA world with complex ribosomes. So, Professor Muller, we are happy to have you here. So, how are you today?
Good, thank you. Thank you for your kind introduction. Can you see my screen? So you see
I can actually. And you asked me, should I go to present mode in my PowerPoint presentation? Yeah, it could work. But in that way, you will not see us. You will be in the presentation mode, and then you will go on. Yeah, now.
So maybe I go to presentation mode, and then I will just do my presentation. I should be able to hear you.
Yeah, right? You can.
And then I just take your directions.
Okay, let's try. If it's not moving forward, we will try another version.
Okay.
Can you
see my face now?
Yeah, we can. Can you go forward, please? Yeah, okay, it's working. Okay, thank you so much. I will be at the backstage, but if you need help, I will just come and help you, okay? See you.
Excellent.
Stage is yours. Thank you.
Are we recording? Are we online?
We are also recording. So we are in online live, and also we are recording that.
Excellent.
It will be recorded on our YouTube channel.
Great.
Yeah.
Thank you.
Thank you.
So thank you for the invitation. It's my pleasure to be part of this conference, and I loved the talk by Mike Toillon, where I think especially in the Q&A he described how I also feel about how to do science, how to do it accurately, and how to communicate science. And as our organizer explained, my background comes from chemistry. So this is how I grew in this environment of astrobiology research. I started off as a chemist, and then successively I got more and more interested in how can life originate, both on early Earth as well as on different planets. So the focus of what I'm doing is on catalytic RNA molecules. And let me first give you a more general introduction. So first, I will look at geological evidence, chemical constraints, and molecular fossils. What evidence do we have about early life? And then I will have three topics. On one hand, very shortly, how can we study the RNA world, or this hypothetical stage of life where RNA was important? And then I will tell you about two projects in my lab. First of all, I will start with the late RNA world. This is more like what you already may have seen published about RNA world. And the number 4 item is more a new direction from my lab that I think is going to this borderline of the earliest life forms. So first, let me tell you about the general introduction. What we know is about 4.53 billion years ago, the Earth started to have a solid surface. And then we know about 3.5 billion years ago, there is the first solid evidence for life based on these stromatolites that Mike already talked about. And after these 3.5 billion years, life diversified into eukarya, archaea, bacteria, and then organisms like bacteria, snails, and humans. What we know very little about is how did the very early stages of life look like? How can we transition from an abiotic environment to a biotic environment? And this is what my focus is. And I will, on the top left here, you see stromatolites as you see in Western Australia today. And you see both the modern stromatolites. If you take a cross section, you see these layers here. And you can also look at fossils of these stromatolites, where you can go back in time to about 3.5 billion years. And they not only exist in this environment, but also they have the same geological shape, and they have the same, they have the isotope fractionation that you would expect from those early organisms. So we can be quite confident that 3.5 billion years ago, there was life on Earth. And the difficulty is when you look at older pieces of evidence, in many cases, people look at carbon microfossils, and I would be careful with those because there are lots of carbon microfossils that look like cells, like here, for example. But we know from all of these pictures shown here is they are of volcanic origins. They are inorganic processes that go on that form these structures. And we know that also because you can have processes in the lab that simulate conditions that make structures that are very similar, the lab-made structures here, to those that originally were claimed to be microfossils of life forms. So you see, we need to be very careful with the interpretation of carbon microfossils. So I feel most comfortable with saying life existed about 3.5 billion years ago. And the thing is, no matter whether life existed 3.5 billion years ago or 4 billion years ago, there's, in both cases, we don't have surviving molecules, macromolecules, that can tell us about how those early stages of life would have looked like. And to do that, we need to think about what is life. For example, you know that viruses, or for example, in this case, bacteriophages, that can evolve. And you see, for example, this viroid, that's just an RNA molecule, 350 nucleotides in length, that also is highly evolved. But I think when you look at this, you would say this RNA molecule, which is just lying there doing nothing, if it's not in contact with a cell, that's not life in itself. And the reason is it requires a host cell to do all these processes for itself. It requires the host cell to amplify the RNA and make more of it. So in that sense, both viruses and viroids have no self-replication. That's why I personally do not qualify those as life. On the other hand, you have self-replicating system. People have made different self-replicating systems in the lab. For example, Gunther van Giedrowski published in 1986 a paper that's called a self-replicating hexanucleotide. That is just the hexanucleotide replicating itself from two chemically activated trinucleotides. And that replication works. And there's more advanced variants of that system. In addition, Julius Rebeck has generated self-replicating systems that are inspired by those nucleic acid systems. Reza Ghadiri and David Lee have generated self-replicating peptides, amphiphilic peptides. Siebren Otto has shown that you can generate organic molecules that stack on each other and have some form of self-replication. Jerry Joyce has shown that you can self-replicate, have self-replicating cycles of ligase ribozymes that reconstitute themselves from two fragments. And Niles Lehmann has shown, together with Eric Hayden, that a group 1 intron ribosome can regenerate itself, replicate itself from 4 fragments. However, all of these systems, they will do nothing else but reconstitute themselves from fragments that you give them, and they will not change, they will not evolve into something interesting. So with that said, these systems do not show evolution, and therefore I don't feel this is enough to qualify as life. So I feel like for life, you need to have both self-replication and evolution. And so here I'm summarizing to you the how I'm thinking about the first life forms. So because we don't know from fossils how they would have looked like, we need to come from first principles and from chemical and physical principles and try to think, how could the first life forms have looked like? First of all, I'm using the definition that's also used by NASA, which is life is a self-replicating molecular system that is capable of open-ended Darwinian evolution. And we will go into this much deeper in the next slides. Then another very important part is life is constrained by the second law of thermodynamics, which says that entropy always increases. However, when you think about living systems being highly structured systems, they are locally low entropy, which means to self-replicate, they need to have a constant flow of entropy, or in other words, they need to deal with chemically activated food molecules. Like you are taking up food and you're secreting molecules of much higher entropy. And so the first living systems would have to do the same. My third point is, if you think about early life forms, how they could have looked like, you need to think about chemical pathways that are plausible. And which means both, those are pathways that just in general are chemically plausible. And then you need to think about, could they have been happening under prebiotic conditions? So general chemical principles. And then by definition, if you think about the origins of life on Earth, and that's so far the only example we know of, then you need to think about continuity in the information transfer and perhaps also in the metabolism that needs to be compatible from stage to stage until you end up with, for example, humans or snails. So all of these four aspects, I think, are important when you think about how could life have originated. And with that, I want to introduce the RNA world hypothesis, which was developed in the 1960s by Alex Rich, Carl Woese, Francis Crick, and Leslie Orgel. And these people thought today's life forms have DNAs that encode all the genetic information and proteins that do most of the catalysis. How could such an interdependent system where DNA needs the proteins to replicate and proteins need the information of the DNA, how could such an interdependent system have originated? It would be astronomically unlikely that a protein with exactly the matching sequence on the DNA and the whole replication system originates. And they already knew at this point that RNA molecules are somewhere in biology and they are able to store information. And they speculated that RNA molecules should also be able to catalyze reactions and possibly replicate themselves, so that RNA could have started as an RNA self-replicating system. And over the years since then, this RNA world hypothesis has become much stronger and pretty well supported. For example, in the 1982, Tom Cech found that, yes, indeed, RNA molecules can catalyze chemical reactions, which gave strong support to this RNA world hypothesis. And maybe the strongest evidence is when you look at the ribosome, which is this multi-megadalton particle in all of today's cells that generates proteins. You see that in blue is the ribosomal RNA. In white are the ribosomal proteins that are basically on the periphery. And the catalysis, the peptidyl transfer reaction, happens where the star is. In orange and red are the tRNAs that transfer the genetic information on the messenger RNA, this little squiggle down here, into the information of the protein sequence. So you see the machinery that generates all genetically encoded proteins is a catalytic RNA, which makes most sense if you think that there was a highly evolved RNA system before the first proteins entered biology. So this is perhaps the strongest evidence for an RNA world. There is additional evidence, for example, that you have nucleotide cofactors, how DNA synthesis works. So I feel that the RNA world hypothesis is strongly supported with respect to there was a stage in the origin of life before the last universal common ancestor, where RNA was the dominant macromolecule for catalysis and probably for genetic information. However, the problem is, how can we analyze this? How can we study how an RNA world could have looked like. And the most important technique that we have to study that is called in vitro selection. And I have just one slide to describe to you the general principle of in vitro selection. So this here is a general scheme how in vitro selection can look like. You start with a random library of DNA molecule that you order, for example, from a company like IDT. And that company synthesizes a long DNA molecule that has lots of randomized positions. Randomized position means at each position you have 4 possibilities and AGCT, and which means 25% at each position, AGCT, mean that if you have, for example, 150 randomized positions, you have 4 to the power of 150 random molecules, different sequences, possibly, and which is about 10 to the 100. The universe has about 10 to the 90 atoms, and the Earth has, I believe, about 10 to the 60 atoms. So this is way more than we can ever represent in a lab. However, just a tiny portion of such molecules, about 10 to the 14, is enough to make this in vitro selection work. And the way we do this is we take these randomized DNA molecules and transcribe them into RNA molecules. So now that we have this random library of RNA molecules, all these sequences, because they are different, they can fold back on themselves in different ways and thereby generate different 3-dimensional structures. Most of these structures are completely useless for what we want to do, but there are some structures that when we incubate these RNAs together with a substrate molecule, they will covalently attach themselves to the substrate molecule. And the vast majority of RNA molecule doesn't do anything, so we try to discard them. And those molecules that have reacted, we try to use the substrate molecule as a handle to pull those out. Then these RNA molecules are reverse transcribed into DNA, PCR amplified and transcribed. So what you see on the left in blue is just how to amplify these RNA sequences that successfully catalyze this reaction. And then we select again and amplify it again, select again, amplify again, until we are at a point where this library is dominated by sequences that catalyze this reaction. So this is the general principle how in vitro selection works. And I want to tell you 2 stories of how we use this in vitro selection to address 2 questions that have to do with how an RNA world could have functioned. And first, I want to show you an in vitro selection, well, actually 3 stories. First, I want to quickly show you the results of an in vitro selection that was done in the lab of David Bartel and a few other labs. And this is a very sophisticated ribozyme. When you think about an RNA world, and you think about what would be the most important and central activity in a self-replicating RNA system, that would be an RNA that can replicate RNA molecules. So some people call it a replicase, but chemically what you would need is an RNA that polymerizes RNA in a template-dependent manner. So David Bartel in 2001 published an RNA molecule that is about 200 nucleotides long, and here you see a secondary structure of this RNA molecule. What this RNA molecule can do is it can bind a primer in orange, base paired to a template in red, and it elongates this primer by using NTPs or nucleoside triphosphates. Those are the same chemically activated building blocks that are used in every single biological organism. So that would make sense for an early life system or for an RNA world system to use the same activated monomers. And he developed this by a series of multiple in vitro selection projects that we're not going into here. But here you see on the bottom the activity of this round 18 ribozyme on different templates, and he showed it can elongate 14 nucleotides with a fidelity in the range of 98% on average. And this ribozyme has been optimized further or developed further from this original ribozyme that can generate 14 nucleotides to a ribozyme that can generate 29 nucleotides of a hammerhead ribozyme in Phil Holliger's lab, to a ribozyme that can generate about 100 nucleotide in Peter Unrau's lab. He was generating a processivity domain. And I think the most advanced ribozyme currently is the one in Gerald Joyce's lab with David Horning. And they evolved the polymerase ribozyme for 71 cycles, always introducing mutations, selecting better variants. And this is at the stage where currently it can do about 100 nucleotides. Since this ribozyme is in the range of 200 nucleotides, I think we may be getting close to the point where we have a self-replicating RNA system. This, I think, is very exciting, and I think you can expect to see more advances in the next year. I would try to follow Jerry Joyce's lab, as well as perhaps Peter Unrau's, Phil Holliger's lab, and my lab may do some contributions here. So I wanted to highlight this ribozyme to you because I think this is perhaps the most important and central ribozyme in recapitulating the RNA world. But when you think about the monomers, the building blocks that are used by this ribozyme, and you think about, I want to have an RNA world organism that can depend on the prebiotic environment, you need to have another activity. If you need nucleoside triphosphates, you need to have ribozymes that generate these nucleoside triphosphates from prebiotically plausible building blocks. And there is a molecule called trimetaphosphate, which is a prebiotically plausible polyphosphate that can react with nucleosides to form nucleoside triphosphates. And Leslie Orgel showed in 1978 that this reaction can occur at 20 degrees Celsius in 1 hour to about 5% yield to generate nucleoside triphosphates. However, this reaction only works at pH around 12. Of course, this pH is way too high to be consistent with an RNA world. RNA would quickly hydrolyze at that pH. But the important thing is this shows that this reaction is possible. So we were wondering in my lab, can RNAs catalyze this reaction of nucleoside triphosphorylation at a neutral pH, at a pH around 7? And when you think about this, this is a really hard thing to do for a catalytic RNA. And for two reasons. First of all, in previous, usually catalytic RNAs that have been developed in the past, they bind one substrate molecule and link themselves covalently to it so they can be selected. In this case, we would be asking for the binding of two small molecules, nucleosides and trimetaphosphate, to generate nucleoside triphosphate. In addition to that, the product of this reaction would be a freely diffusing molecule. So there is no physical link between that molecule and the successful catalyst. How would you be able to select that? And those two challenges we have addressed in a very complicated selection, or technically very challenging selection system, that I will show you in the next few minutes. So first of all, what we are doing here is we have a randomized sequence, in this case 150 nucleotides, and this sequence is challenged to bind one nucleoside, in this case 6-thioguanosine, to react it with trimetaphosphate and then generate 6-thio-GTP. And I will tell you in a reason why we use this thio modification. Otherwise, we could have just used guanosine to make GTP. So now we have the successful catalysts would have generated freely diffusing 6-thio-GTP, but we could not select them. In order to select them, we couple them to a second ribozyme. So this is a variant of the polymerase ribozyme that we use to tag 6-thio-GTP to the successful catalysts. And by doing that, we are equipping the successful catalyst with a thio modification, so that only the successful catalysts have the 6-thio modification. In order to make this possible, we evolved this polymerase ribozyme to work really well with the 6-thio-GTP modification. And we actually got a 200-fold improvement. So this ribozyme is now really, really good in tagging 6-thio-GTP to the 3' end of those library molecules that have generated this. Now, this took already about 3 years to develop. And there is one hurdle still that needs to be overcome, and which is if you have a mixture of library sequences, most of them are inactive molecules, just a very small number are active molecules, then those active molecules that generate 6-thio-GTP, they would not only tag themselves, because the 6-thio-GTP could diffuse around, and then inactive pool molecules would get tagged. And because the number of inactive molecules is far higher than the number of active pool molecules, you would never get to enrich your active pool molecules. And to make it possible that only your active pool molecules are tagged, we used an emulsion system. And that was technically really complicated. So we took another 1.5 years to optimize this emulsion system. But in the end, we found that we can generate droplets of about 150 nanometer diameter. And when you calculate the volume inside a droplet of 150 nanometer, you realize that if you put 1 molecule in such a small droplet, it corresponds to a concentration of 1 micromolar. Our polymerase ribozymes were optimized such that even a 1 micromolar concentration of 6-thio-GTP, so if 1 molecule 6-thio-GTP is generated, would be enough to tag those library molecules. So with that system in hand, we thought, now we are ready to do the selection. That was about 4 years of work, or 3.5 years of work, just to prepare the experiment. Just to make the emulsion, we use this machine here. It's called a microfluidizer, where we suck the raw emulsion, press it through the cell here. This is how the emulsion looks. This formulation is one that was developed in Phil Holliger's lab. And then after 7 passes, we find by dynamic light scattering that we have a very homogeneous droplet size distribution of those desired 150 nanometers. And together, this is how the in vitro selection cycle looks like. So we generate, from this DNA library, we generate an RNA library. We had about 5 times 10 to the 15 different sequences. We compartmentalize them in emulsions so that each emulsion, or that the emulsion droplets had both the library molecules, these polymerase ribozymes, 6-thioguanosine and trimethylphosphate. Then we incubated them for about 6 hours. After that, we broke open the emulsion and ran those library molecules on a polyacrylamide gel that separates between molecules that have a thio modification and molecules that don't. And by that way, we were able to isolate those library molecules that were decorated on their 3' end with a thio modification. And then those molecules were reverse transcribed, PCR amplified, and transcribed again, such that this is a new library that is now enriched for RNA molecules that catalyzes this reaction. And usually it takes a number of cycles to enrich, which is no different than in this case. And that's one of the scary things when you do in vitro selection experiments. You're working blind for a number of selection cycles, and this is about 3-4 months of work. So for 3 months, you're working really hard, and you don't know whether your system will be successful. So after about 8-9 rounds of selection, we saw the first signs of activity in the library. And then after 12-13 rounds, we saw a really nice spike in activity. After 14 rounds, we thought, now it's time to look at variants of the sequences that may be better than the original sequence. So we mutagenized the library to introduce more mutations and then select again. And then we didn't see any further increase. And then we analyzed all of these selected populations by high throughput sequencing analysis. So what that does is, by high throughput sequencing analysis, you can sequence, for example, 2 million sequences from each selection cycle. And then you process these sequences to see, do we have specific clusters of sequences that enrich over time? And you see here that the sequence cluster 1 is the dominant cluster pretty much throughout. You have another strong sequence cluster 2, and altogether 5 sequence clusters are the ones that make up more than 95% of the sequence diversity after at the end of the selection. After this high throughput sequencing analysis, we wanted to biochemically test, are these sequences active? So we ordered specific sequences, I think 15 different sequences, and we tested them biochemically in this assay, where we had a radiolabeled short primer that was extended by GTP if this ribozyme converted guanosine and cyclic trimetaphosphate to GTP. So you see in this assay, we are not using 6,000 GTP anymore. We are just using GTP. And what you see is this cluster 1 seems to be the most active over from all of these clusters. So we focused on S59, which was the winner of our selection, and characterized this in more detail. And here you see this catalytic RNA. This is the secondary structure of this RNA, and analyzed how does it catalyze this reaction. What we found is that the catalytic rate enhancement is pretty good. The rate with the ribozyme is about 18,000-fold faster than the rate without the ribozyme. So that's a pretty good rate enhancement, and that can also be compared to a number of protein enzymes. However, this ribozyme has a miserable turnover number. So each ribozyme, on average, makes only about 1.7 GTP molecules. So on average, 1 or 2 GTP molecules. And while it's great that we get GTP, and we've confirmed this by mass spec, it's not enough for a metabolism to make only 1 or 2 GTP molecules. And that's one thing we're currently working on. We are trying to generate variants of this ribozyme that generate more GTP. And I hope that if you have this conference again in a year, I'm happy to present again and show you what progress we have made to hopefully have a multiple higher turnover ribozyme to make GTP. So now this was an example of a sophisticated ribozyme that you would see in a late RNA world where there was lots of evolution going on to optimize RNA sequences. However, such long RNA sequences would be very unlikely to originate in a prebiotic soup, like very early on before you had any catalysis going on. And this is what my last part of the talk is about. How could the very first catalysts originate more from a prebiotically more plausible setting? And the conundrum is that when people do prebiotic model reactions, they find that RNA molecules can be generated maybe in the range of 30, 40 nucleotides, but not much longer. So the question is, how can you generate a catalytic RNA system from a prebiotic environment that cannot generate long oligomers? And we were asking a slightly different question. We were asking, can short RNA or nucleic acids, can they come together and form complexes that are able to catalyze reactions? And the way we did this is in this in vitro selection experiment. So here you see we used a randomized sequence that had only 25 randomized positions. Remember, in the previous experiment, we had 150 randomized positions, which can give you rise to very complicated ribozymes. We found in previous work that for the specific activity we're selecting here, 25 randomized positions is the borderline. You should expect to find either one or a few or none of catalytic sequences. So we challenged this randomized library of 25 positions to react their 5' hydroxyl group of that RNA with trimetaphosphate to form a 5' triphosphate. So this is somewhat analogous to the formation of nucleoside 5' triphosphates. However, in this case, the reacted nucleoside or nucleoside triphosphate is covalently connected to the RNA strand, which makes the selection procedure much simpler because you can do it in bulk. So after you have formed the 5' triphosphate, we use a ligase ribozyme and a biotinylated RNA to link the successful catalysts covalently to a biotin. And then we use this biotin via a streptavidin interaction to pull out only those sequences that had a 5' triphosphate, then reverse transcribe, PCR amplify, and then transcribe again to have a new RNA library that is now enriched for those sequences able to catalyze this reaction. Now, I told you earlier that this library of 25 nucleotides would alone probably be not enough to form those sequences. So what we did was we added to this mixture, where the incubation with trimetaphosphate happens, we added to this mixture 256 different sequences of DNAs that were 20 nucleotides long. And the reason we took DNA was just for commercial for financial reasons. DNAs we can buy for like $1,000, 256 DNAs. RNAs, this would be about 1 or 2 orders of magnitude more expensive. So these DNAs were designed to have a nicely random distribution of nucleotide bias and a random distribution of self-folding energies, and we added them to this step. So we were asking, would these very short RNAs, would they start to recruit DNAs in order to form catalytic complexes? And I'm happy to tell you that the answer was yes. So this is again a high throughput sequencing analysis. And out of this library of about 10 to the 14 sequences, there were 1,331 sequences that were enriched enough that we had more than 500 sequences in the selection round 6. And by comparing them between reactions where we had all 256 DNAs present and no DNAs present, we chose 45 sequences for biochemical analysis. And Xu Han, who was doing this analysis in my lab, she went through a massive work effort to analyze these 45 sequences biochemically. So she needed to test which of those 256 DNAs would allow these RNAs to be active. And the reason that I chose 256 as the number was we can separate them out into 16 sets of 16 DNAs. And 16 is a number we can analyze nicely in one experiment. So here you can see, for example, in this experiment, Xu showed that the DNA sets N and O mediated activity of this RNA. And then she looked at the DNAs within that set N and found that the DNA D236 and the DNA 240, they were the ones who were able to mediate activity. Now, this works for RNAs that recruit just one DNA. There were some RNAs that must have recruited more because they were active with 256 DNAs. They were inactive with whenever you tested one individual set of DNAs. So for those RNAs, she tested all 16 DNA sets, but she always left one out. For example, for this RNA, she found if I leave out set F or set I, in both of these cases, I get no activity, which means there must be a DNA in set F and a DNA set I, which are both required for activity. And then she looked into this DNA set F and tested, in the presence of DNA set F, she looked at all variants in DNA set I and found that, oh, in DNA set I, we require DNA 93 to be active. So this is how she analyzed all of those 45 sequences. And she found that when you make a phylogenetic comparison between the sequences that she tested and you correlate them with the DNA cofactor use, then the colors here show you which DNA cofactor they use. And you see that they cluster, the sequence clusters consistent with their DNA cofactor use. So there's 14 clusters in terms of how the sequences are and what cofactor they use. And here you see in this network diagram how closely they are related. You see they are quite isolated. These peaks are quite isolated because it would take about 12 mutations from here to here. It would take 10 mutations from here to here. So basically, in this in vitro selection, she found 14 RNAs that are active with DNAs or without. We have one control that is active by itself. And for 6 of these RNAs that were active only with DNA, she analyzed them in more detail. And these here are the secondary structures for 4 of them. So here you see, for example, one example where the RNA in black is binding this DNA in purple. And this is the active conformation. In this case, the RNA requires 2 DNAs to be active. In this case, the RNA requires 3 DNAs for maximum activity. And here we have a strange example of 2 RNAs coming together to bind with 1 DNA. So we have a whole zoo of catalytic complexes of short RNAs and DNAs that are now allowing us to address in more detail how could the first catalysts in the beginnings of an RNA world have looked like. And perhaps the most exciting example and most exciting result from this study is the following. When we took all these 6 RNAs that required a DNA for activity, plus 1 RNA that was active without DNAs, we changed their length so that we could assay them all in the same assay. And you see that for each of these bands, this is all each of these RNAs that slowly react over time. As expected, when you have the 256 DNAs present, all 7 of them are active. Now, if you add, instead of the 256 DNAs, you add DN20, so a completely randomized DNA sequence of 20 nucleotides, what you find is that in addition to the RNA that requires no DNA cofactor, you find that 4 of the 6 RNAs are still active. What that means is that these 4 RNAs are able to recruit from this incredibly complex mixture those sequences that allow them to be active. And this, in my mind, is a exciting result because it shows us how from a prebiotically very complex situation, you might be able to form catalysts that are active for very specific reactions. So I showed you 2 examples, and this is a complicated slide that just allows you to see how I think about the rise of an RNA world. First of all, you just had all kinds of chemical reactions going on, where in this intermediate phase that people call chemical evolution, you have a lot of enrichment processes going on that generated bias that could form catalysts, and perhaps once you have self-replicating systems, then you can have Darwinian evolution happen. So this stage here of chemical evolution is quite an intense focus of research by several labs. And these nucleic acid oligomers that form catalytic complexes would fall perhaps in the chemical evolution stage, whereas the complicated RNAs that I showed you earlier, the RNA polymerase ribozyme and the GTP synthase ribozyme, they would probably only originate once you have a lot of Darwinian evolution going on. And with that, I just want to show you the people who did the work. So Arvin Akupi was the person you see on the right here. He set up this in vitro selection system in emulsion. That was a massive undertaking. And Josh Areola did the biochemical characterization of this GTP ribozyme. Shuhan was the person who led the study on the fragmented complexes, and she also used Josh Areola to get her project started. And like Mike Toillon, who did the last presentation, I'm also funded by NASA by astro and exobiology grants. So I'm very grateful for NASA to fund this kind of work, because the answers that we find are general answers. These answers not only tell us how life could have originated on Earth, but they also can tell us how life might originate on different planets. And with that, I'm done with my presentation, and I thank you for your attention. And I cannot hear you right now. Zeynep, you're muted.
Oh.
Perfect.
Can you hear me now?
Yes.
Yeah, okay. It was really insightful and fascinating talk. I was saying thank you so much. So it was truly actually a good presentation. I couldn't explain. So if you have time, I will ask some questions from our audience. So yeah, first one. Okay. How can we be sure the microfossils we have is biotic? These prehistoric cell-like organisms are too small. How could they undergo fossilization?
Good question. So while I'm not an expert in that specific field, the question on, so you need to use multiple different aspects to decide whether a microfossil would be biotic. As I showed you earlier, there are tons of microfossils that look like they could have been cells, but of which we know they were not living organisms because they originated in a volcanic environment, which means lava melts at about 1200, 1300 degrees Celsius, and there is no organic chemistry above 600 degrees Celsius. So this cannot be biotic origin. What people look at when they say, for example, these stromatolites must have biotic origin, they look at on one hand at the geologic context. For example, when you see these are sediment layers in the surrounding context, then you know this is not a volcanic origin, this is a sedimentary origin. Then if you're in an environment like in Western Australia, where you find stromatolites today, and you can see them over the last billions of years in the sedimentary record, it makes sense that this just goes back that far. Then when you look at these structures, you see that these sediments, when they have this roundish cone shape, you need to look at it in 3 dimensions. So if you look at it in one direction, it can be just a fold. Lots of these geological layers have been squeezed together, but then you would see that in the 3rd dimension, you would not have also this cone shape. So you would need to see this in 3 dimensions that you have this cone shape. And then very importantly, you want to see that there's isotopic fractionation going on. So that, as you may know, their carbon isotopes are being generated by heavy bombardment, heavy radiation in the atmosphere. And if you have nitrogen in the atmosphere, you constantly generate some carbon isotopes that can then be incorporated into living systems. And if you see that signature, that you have a changed carbon isotope signature, then this is another indication that this is probably has been a living system. So while I'm not an expert in this field, I think you can read some of the important papers and get your own feeling of what you believe is a biotic microfossil. What you believe is a Sorry. No problem. If this is a biotic signature, a biotic microfossil, and make up your mind. So I feel quite confident that there are stromatolites that are 3.5 billion years old that are evidence for life, and that would mean there must have been life originating somewhere between 4.5 billion years and 3.5 billion years ago.
Okay. I will go to the next question. Okay, thank you. Okay, so Professor Muller, we hypothesize the existence of relatively simple catalytic RNAs in the early stage of the RNA world. What fundamental evolutionary innovations and adaptations do you think allowed these early ribosomes to develop more sophisticated catalytic abilities before reaching the complexity of modern ribosomes? Specifically, what specific changes in RNA sequence or structure do you envision playing a critical role in this transition? It was too long.
Very good question. So
yeah,
so when you think about how could the first catalytic nucleic acids have been different than today's biological RNA molecules, one thing that we can be quite confident about is that the nucleobases in very early stages of chemical evolution were much more diverse than today, because today we are dominated by 4 canonical nucleobases in RNA, A, G, C, and U. And when you look at the behavior, the chemical and physical behavior of these canonical nucleotides, nucleobases, you find that they are very photostable, which means you can irradiate them with UV light quite a bit, and they don't react. So they have, when you excite them into an excited state, they don't stay in this excited state for very long, where they could engage in chemical reactions. They very quickly relax. And there's actually very few variants of all possible nucleobases that do that. So from that, I'm very confident that there was a strong selection pressure from very early nucleic acids to incorporate mostly the canonical nucleobases. And in addition to the nucleobases, you also can think about the ribose phosphate backbone. And there are famous articles, why do we need to have phosphate in the backbone? That helps us to have some charge repulsion between the 2 strands, but not too much. And that's quite important, because if you have a too stable genetic polymer, you are tolerating genetic mutations. Whereas if you have a too low stability genetic polymer, you are unable to pair to the other, to the complementary strand. There's some excellent work by Ram Krishnamurti being done, who found, for example, if you have an RNA-DNA heteropolymer, where you randomly have DNA and RNA nucleotides, then you do not form very stable duplexes between one heteropolymer and another heteropolymer. But one heteropolymer forms a stable duplex with RNA. It forms a stable duplex with DNA. And you know that RNA and DNA form stable duplexes. So this is another example of a stage of chemical evolution where you would have identified useful nucleotides and building blocks at a stage before you actually had catalysis going on. Yeah, I hope that addresses your question. There is a lot of research going on, and I suggest look at Ram Krishnamurti's work. He is here also at the Scripps Research Institute. He did a lot of work in this direction.
Thank you. Do you think it would be possible to recreate the RNA world in a laboratory environment today, and what would this gain us?
Thank you. I love this question because this is kind of the long-term goal of the field, to generate an RNA world, a self-replicating and evolving RNA system in the lab. So first of all, I need to make sure that it's clear what we would generate in the lab would not necessarily be the same as an RNA world in early life, because we use very different techniques that could ever have been used in early life. No, there was no experimenter around who went through in vitro selection rounds. But the thing is, once we have a self-replicating RNA system in the lab, we can then just let it replicate and see what happens. And by definition, this self-replicating and evolving RNA system would evolve into something that replicates better. And I'm confident that we are thinking wrong in quite a number of ways. So I assume, for example, that there's better ways, more efficient ways to self-replicate. And what this system would show us where we were thinking wrong. It would evolve into something that works better, and we would learn from that system. And I think within 1 month or 2 months, because we can do high throughput sequencing on every single generation, we would learn from that system, how can you evolve, how can you replicate better? And this would show us, for example, this might show us systems that are simpler and that may be easier, may be able to easier evolve, originate in a prebiotic environment. That's one thing that I'm looking forward to. The other one is you can, in a way, replay the early evolution of life. You can let this system evolve in different environments. For example, an environment that had different amino acids, different cations, different pHs, and you would see under which conditions would you develop into which direction. Would one way develop a ribosome? Would you develop peptide synthesis? Would you develop cell membranes? And so we could replay this tape of life, some people call it, and learn what different ways could there have been to life to originate. Would we always end up in a system similar to ours, or would we have very different systems? And that's in addressing this bigger question that we're addressing in astrobiology, and that's why NASA is so interested in this, is how many different types of life might there be? Because if NASA goes to an exoplanet and finds there must be something living here, but it may have a very different chemistry. So those are things that we can learn from systems. Hopefully we are there within the next 10 years or 20 years to tell us about early origins of life.
Okay. So the next question. Dear Muller, I have two questions. First, how can these studies be used in the development of artificial life forms? Second, do you think it's possible to create lifelike systems based on RNA in the future? Actually, it was similar to previous question.
So it depends a little bit on what you mean with artificial life forms. In a way, it would be an artificial life form, because I don't think that whatever we generate was exactly happening on early Earth. It would always be artificial, at least the first part. If we are lucky, we are able to evolve it into something that was very similar to early life forms. And the study of those systems, I think, would show us, right now we cannot say exactly how life, or we will never be able to say exactly how life originated. But by studying that system, I think we would learn about the constraints on that system. What kind of other systems would have been useful? So this is learning about early life systems. But yes, in my view, an RNA world system would be a lifelike system. And so that means it would be possible to create lifelike systems. And everybody's definition of life is a little different, and I'm open to any definition. Some people say the invention of the ribosome was what triggers for them to call this life. In my view, I don't need the ribosome. I need self-replication, evolution of a molecular system.
Okay. Next one. What question are we still searching for today to understand the beginning of life? Do you think this answer is hidden in the Earth or in the universe?
So there are lots of questions that are completely open. One active area of research for a number of labs. Well, one thing I showed you is the late RNA world and the early RNA world. The late RNA world, I think, is the easiest for us to think about conceptually, because we can think about it like we do about biology. We need to do RNA polymerization, we need to somehow get NTPs from somewhere, and then one big issue in RNA polymerization or replication is how do you separate the strands when you have generated them. But you can't think about this biologically, like biocentric, whether it's wrong or not. So this is a late RNA system. An early RNA system, I believe, would have to function quite differently, because we don't have long RNAs around. We would have to think about self-replication a little differently. And then perhaps even I also touched upon the work of Ram Krishnamurti, for example, and others who look at the very early stages. How can you get molecules that are able to do base pairing? And you may want to look, for example, also at the work of Moran Frankel Pinter and Lauren Williams, who study what kind of prebiotic processes can generate molecules that could have been useful to early life forms. So there's a lot of work going on in this chemical evolution stage, because at this point, we have organic chemists that show us how we can synthesize nucleotides via pathways that might have been plausible, but we don't have a one-part synthesis for nucleotides yet. We need to understand how we can polymerize those nucleotides into RNA polymers, and how we would do something like a selection for self-replication. So all those steps are unknown at this point. And if you follow up on the suggestion of Mike Toillon, that I completely agree on, if you want to study those kind of systems, first you study one of the sciences, and I think chemistry is a very good direction to start with if you want to understand life's origins on the molecular scale. And then you later focus on directions that are more related to astrobiology. So there's lots of questions still open, and I think the questions many of these questions will remain open for many years. So if you want to embark on a career, there's lots of work to be done. You're not running out of questions anytime soon.
Thank you. Do you think there was another information carrier molecule that we do not know about at the beginning of life, and RNA was just its evolutionary winner?
Yes. So as I mentioned earlier on, we can be pretty confident that the canonical nucleobases that we have in today's biology are the winners of a chemical evolution that existed before there was Darwinian evolution. And I am confident that one of the selection pressures in this chemical evolution was photostability. It's just by looking at those 200 or so variants of nucleobases that Nick Hudd at Georgia Tech was exploring, and looking at how many of them are photostable. It's just a very small number. So yes, I'm confident there were many other information carriers, and RNA was the evolutionary winner. The other thing is you can look at the backbone of RNA and DNA, and this is the work of Albert Eschenmoser as well as Ram Krishnamurti, who looked at different backbones. And for example, John Chaput at UC Irvine, he showed that TNA, so threonucleic acid, can work just fine to both transfer information from RNA and DNA and TNA and back, as well as serve as a catalyst. So we know that RNA turned out as the winner, and I'm confident that there were many different information carriers that were in this prebiotic mixture, and that eventually RNA just won out from them.
Okay. So how do your studies on ribosomes inform our understanding of catalytic processes in the RNA world? Hypothesis.
So the polymerase ribozyme and the GTP synthase ribozyme, they are just ribozymes where we think they must have been important in a mature RNA world. This thinking is informed by or is driven a little bit biocentric, because we think about this is how replication needs to go. If you replicate an RNA system, you need RNA polymerization. Now, this is the bias we have, but by studying these ribozymes, we understand how much information is necessary to encode such a catalytic activity. For example, how many molecules need to be present in an environment in order to have 1 or 10 or 100 that would have a certain activity. And you can look, for example, at Irene Chen's work at UCLA or the work of my own lab to see how many molecules do you need to sample in order to find a catalyst. And we published this study, I think 2017, where we looked at a previous in vitro selection that found about, I think, 900 different catalytic RNAs in one selection. And we took that library and we identified what are the shortest variants of this ribozyme. And then we found the ribozyme I just told you, I told you earlier that about 25 nucleotides, this was about the borderline for that specific ribozyme. So you can learn about the sequence space that you need for an RNA. You also learn what kind of chemical reactions are easy for RNA to catalyze, which ones are hard. For example, it is very hard to shield a catalytic site from water molecules for RNA. And when you ask yourself, why do proteins, why do we have 20 amino acids and 9 of those amino acids are hydrophobic amino acids? And one of the reasons is these 9 amino acids can come together like puzzle pieces and shield a catalytic site from water. And that allows them to catalyze reactions that are between hard and impossible for RNA to catalyze, like a carbenium ion intermediate or something like this. So what we learn are the capabilities of RNA, the limitations of RNA, and how much help do you need to give RNA in order to catalyze those processes.
Okay, the next one. In what ways does the PCE3 consortium facilitate interdisciplinary research into the origins of life?
In many different ways. So the prebiotic chemistry early Earth environments, PCE3, they are a group of NASA-funded labs and also not NASA-funded labs who meet and share information. For example, you may know the PCE3 seminar series, and I was co-organizer of a PCE3 workshop in 2021, which I think is very useful, where you can watch videos on YouTube from leading people in the area. So I like this group because those are leading people in the field that are making it relatively easy for the public to see the state of the art in this area of research. When you read scientific papers, that's often a little challenging for somebody who doesn't have a education in chemistry. But I think when you listen to those talks, it's much easier to follow the central ideas. And that's one of the reasons why I like this forum here. I think that makes it much more widely accessible and get possibly people excited into astrobiology research. And it's not only that some of you may be interested in astrobiology and then embark in chemistry, it's also that by getting excited about this, you study chemistry and then you see, oh, actually, there's something else in chemistry I find even more exciting. So it's a little bit like the moon landing. Early on, you get people excited about science, and then you learn about things in science that help both you and the wider humanity.
Thank you. Okay, the last question. What challenges arise when attempting to replicate prebiotic chemical reactions under laboratory conditions?
Great question, and I would classify them in 2 parts. One of them is we don't know what exactly the prebiotic chemical environment was. We have good guesses, but we don't know. And the other one is the conditions sometimes require special setups. So for the first part, what we can be very confident about, and this is based on the work by, I think, James Farquhar from the lab of Mark Thiemens. he found that oxygen, and people who used his technique, they found that oxygen arose in the atmosphere of the Earth only like 2.5 billion years ago, and before, I think 2.7 billion years ago, it was minute amounts of oxygen in the atmosphere, which means the chemistry that we need to think about in prebiotic reactions needs to work pretty much without oxygen, or just other molecules that have some oxidation potential. Then the other thing is, for example, the Stanley Miller type spark experiment, where you have an atmosphere of ammonia, methane, carbon dioxide, and you send sparks as an energy force through it, then you can see what kind of molecules can easily come up, what kind of molecules are very hard to generate. Basically, the first part is we don't know exactly what it was, but for example, one point is, since there was very little oxygen, we can be quite confident that there was a lot of iron in the ocean, because today iron is oxidized to 3+, since we have oxygen in the atmosphere, and iron 3+ precipitates very efficiently. So we have close to 0 iron in the ocean, which limits growth. However, when we had no oxygen, iron was mostly in the iron 2+ state, which is very soluble in the ocean. So to that time, we may have had about 0.1 millimolar iron 2+ in the ocean. And that also means our oceans may have been green from the iron 2+. And also there was no scarcity on using iron 2+ as a iron cofactor. And one thing, for example, is it comes from atmospheric modeling. You may want to look at the work of James Casting, who modeled the early sun paradox, that we know that the early sun was 25% less luminous than today's sun. And when you model that, you find the surface of the Earth, including the oceans, were frozen over. And that doesn't allow you to have exchange between the ocean waters and the atmosphere. However, we also can be pretty confident there were lots of volcanic eruptions that generated carbon dioxide in the atmosphere. And when you generate more and more carbon dioxide in the atmosphere, because there is no exchange of the carbon dioxide, you generate greenhouse gases that warm up the atmosphere until the temperature is high enough that you melt the oceans. So I think of this as a pretty strong evidence that there were always areas of the ocean that were frozen, and there are always areas of the ocean that were thawed during the stages of life's origin. So I'm actually personally going more towards a cold ocean than towards a hot environment, which is pursued by some people. And one last thing I want to mention is, if you want to make chemical reactions in the lab, you often end up with quite toxic environments. For example, you may need hydrogen cyanide as a reactant to generate nuclear bases like adenine. Of course, you don't want to breathe in cyanide because that shortens your life expectancy quite dramatically, or carbon monoxide, for example. So you need to have special setups that allow you to work with environments that may be prebiotically most realistic. I just inherited a glove box for my lab, so I may be able to work under anoxic conditions to simulate it better. But those are things that are technically doable. It just takes some effort, and then you need to ask exactly what question are we addressing, so that you generate the environment under which you can address that question.
Okay, thank you. This was the last question. Also another comment. Thank you, Professor Muller. This was very informative and beneficial for us. I agree with that. Thank you so much, Professor Muller. It was really insightful talk. So it was truly an honor and privilege to hear about your work on the RNA world. I'm sure many of us will be thinking about ribosomes a bit different after this talk.
Great. And I'm glad that some of you may be inspired to pursue this further. And if you have this conference in a year, I'd be happy to participate again.
Yeah. I want to see you also next year, and also not for just this, maybe or other events also. We have some small webinars also. If you have time, we are really honored to have you again.
Of course, I would be happy.
Thank you. Thank you so much.
Bye.
Bye-bye. So, we are incredibly grateful to each of our speakers for joining us and sharing their expertise. Thank you all so much for joining us today. So, I will first take my teammates here. If I have all. Is there any missing one? If I cannot see. Yeah, okay. I think we are all here. No, also this shop. Yeah. Okay, so from Martian nanotubes to ribosomes, from filmmaking to amyloids, today's talks reminded us just how vast and inspiring the field of astrobiology truly is. We have explored science, creativity, and deep curiosity that connects us. So on behalf of MBG Turkey Agenastro team, I want to thank our incredible speakers for their time, knowledge, and passion, and also happy Easter for them. And all of you, our audience, for your questions, your attention, and your shared love for discovery. We hope this conference leaves you with new ideas, new connections, and maybe even new questions to explore. Your passion and curiosity are what keep this field alive and growing. Until the next time, stay curious, keep looking up, and thank you again for being part of this journey. MBG Türkiye Agenastro ekibi adına arkadaşlar, zamanlarını, bilgilerini ve tutkularını bizimle paylaşan değerli konuşmacılarımıza içten teşekkürlerimizi sunuyorum. Ve siz sevgili katılımcılarımıza da ilginiz, sorularınız ve keşfetme tutkunuz için, bugün bizimle olduğunuz için çok teşekkür ederiz. Konferansın gerçekleşmesini sağlayan şu an ekip arkadaşlarımı ekranda görüyorsunuz. Hepsine çok teşekkür ederim. Şu an ekranda gördüğünüz ekibimiz dışında arka planda da çok fazla emek göstermiş olan, ancak şu an uçakta, yolculukta olduğu için veya sınav olduğu için şu an burada olmayan ekip arkadaşlarım da var. Onlara da ayrıca teşekkür ederim. Umarız bu konferans sizlere yeni fikirler, keşfetmek üzere yeni sorular bırakmıştır. Bir sonraki buluşmamıza kadar merak etmeye devam edin. Gökyüzüne bakmayı unutmayın ve bu yolculuğun bir parçası olduğunuz için tekrar teşekkür ediyoruz. Söylemek istedikleri varsa diye ekip arkadaşlarıma sözü bırakıyorum.
Ben bu saate kadar burada dayanıp emek verip çaba sarf eden tüm ekip arkadaşlarıma gerçekten çok teşekkür ederim. Büyük bir tempoydu. Hala yemek yemeyenler de var aralarında. Sabahtan beri oturup masaya, sandalyeye yapışanlar var. Ve sizin de sabrınız için, vaktinizi ayırdığınız için gerçekten hepinize hem sorularınız için hem de ilgi ve alakanız için bir kez daha teşekkür ediyorum. Sonraki etkinliklerde tekrar görüşmek dileğiyle diyorum.
Evet, konuşmak isteyen başka var mı arkadaşlar veda etmeden önce? Sena
sadece yiyecekleri, yemekleri düşünüyorlar bence.
Galiba. Hepimiz açız. Var mı arkadaşlar söylemek istediği olan?
Yok sanırım.
Berra sen devam et istiyorsan.
Tamam, ben
kapanışı.
konuşmamı yapayım. Öncelikle son dakikaya kadar bizi sabırla takip eden tüm katılımcılarımıza en içten şekilde teşekkürlerimizi sunarız. Konferansımıza göstermiş olduğunuz ilgi ve sabrınız için çok teşekkür ederiz. Maalesef her sene olduğu gibi geleneksel 5. Uluslararası Astrobiyoloji Konferansı'nın üzülerek sonuna geldiğini söylemek zorundayız. Umarız siz de bizim kadar eğlenmiş ve öğrenmişsinizdir. Bilimi yaymaya ve teşvik etmeye devam. Bir sonraki etkinliklerde görüşmek üzere. Bilim ve merakla kalın arkadaşlar.
Hoşça kalın arkadaşlar.
Hoşça kalın.